the last day of real-world crypto. Our first talk today is titled Provable Security for End-to-End Cloud Storage. It will be presented by Matilda Backendahl and Miro Haller. Please welcome Matilda and Miro.
All right, thank you for the introduction, Matt. And good morning, everyone, and welcome to this session. As you might have guessed, I'm Matilda, this is Miro, and this talk is going to be based on joint work together with Hannah Davis, Felix Günther, and Kenny Patterson. And in this presentation, we want to share with you a security model for end-to-end encrypted cloud storage and try to convince you that you should use it. But before we get started on that, let's back up the band. So 2 years ago at RWC 2023 in Tokyo, Miro and I presented our takeaways from analyzing the end-to-end encrypted cloud storage provider Mega. And as you might recall from that talk, if you were there, we showed that even though RSA keys are not penguins, using AES ECB for key encryption is a bad idea, and even led to a key recovery attack on Mega. All in all, we presented 5 different attacks, which affected both file confidentiality and integrity, thereby completely violating the end-to-end security guarantees that Mega aimed for. And our conclusion was that securely implementing end-to-end encrypted cloud storage is actually not as easy as it might seem, and Mega faced quite a few challenges. So among these challenges are the fact that users tend to have multiple devices. And since end-to-end security relies on client-side encryption, this means that we need a secure way of transferring keys between devices in order to make files available everywhere. And this leads to a key distribution challenge. Furthermore, cloud storage systems tend to be browser-based, which means that cryptographically speaking, clients are assumed to be stateless. So for this reason, most cloud storage systems use passwords as a root of security. And as we know, passwords are not great for security. Finally, file sharing is an integral part of the functionality of a cloud storage scheme, but this means that there's user-to-user interaction, making the security setting inherently multi-user. So these things and more are what make securely implementing cloud storage tricky. And Mega actually didn't have a lot of help from us academic cryptographers in their attempt to overcome these challenges. But this was 2023, now it's 2025, and we'd like to give you an update on what happened since. So after analyzing Mega, Miro and I were curious about the general state of secure cloud storage. Now, Mega might be the largest provider of end-to-end encryption by default, but they're actually far from the only one. In fact, there's quite a selection of companies out there claiming to offer ultimate security and various other statements to the same effect. In particular, they really like to advertise something they call zero-knowledge encryption or privacy. Now, personally, Miro and I have no idea what zero-knowledge cloud storage means. So in order to try to figure this out and also see which of these very strong security claims that we can actually trust, we, and in particular our colleagues Jonas Hoffman and Kien Tuong Truong, went on to analyze these systems. And it turns out that most of them are actually insecure. And even the ones that aren't broken in practice have blockers that mean that they can't be provably secure. So what's the reason for this sad state of affairs? Well, we claimed back in 2023 that the challenges were key distribution, password-based security, and file sharing. And while this is still true, Mega and the other providers that we studied actually managed to overcome these hurdles, mostly. So we think that, we're probably preaching to the choir here, but we think that the larger problem faced by these providers is that they didn't really know where they were going. There had been no formalization of secure cloud storage, so the cryptographic goal wasn't entirely clear. And in particular, there was no formal model, so it was impossible to design a provably secure cloud storage system. So that's what we set out to change. In our paper that we presented at Crypto last year, we presented a security model for end-to-end encrypted cloud storage, including a syntax, game-based security notions, and a provably secure proof-of-concept construction. So this is also the outline for the rest of this talk. I will briefly touch upon syntax and then hand over to Miro for security notions and the construction. All right, so let's dive into our framework. Now, you might think that modeling end-to-end encrypted cloud storage should be trivial, because this is just file encryption, right? But actually, to capture the complexity of a cloud storage system, we need to model interactive protocols in a multi-party setting. And this starts to sound a lot like key exchange. Now, I know there's a lot of key exchange lovers out there in the audience, so congrats, today's your day, because end-to-end encrypted cloud storage turns out to be even more complex. And we won't even talk about zero-knowledge cloud storage. So what makes modeling cloud storage so complicated? Well, as I said, similar to in key exchange, we need to model interactive protocols between multiple parties. Now, in our setting, these parties are a client representing a cloud storage user and a server representing the cloud storage provider. However, in contrast to in key exchange, there's not just a single protocol running between these two parties. Rather, in our syntax, we capture the core functionality of a cloud storage system with 7 different interactive protocols. And this substantially adds to the complexity of the modeling. So let's take a look at what these protocols do. The first one is account registration, and this is used to register an account with the cloud storage provider, essentially creating a new user in our model. Once a user has an account, they can use the authenticate protocol to log into it and start a session. And a user can have multiple sessions running in parallel, for example, on different devices. Inside an active session, a user can use one of the following 5 protocols to then manage their files. So for example, put to upload a new file. Now, the main complexity of the syntax is that, similar to in key exchange, we wanted to model the fact that these operations are non-atomic in practice. So in particular, this means that our syntax is entirely message-based, and we allow interleaving of messages, both between different users, different clients, and different protocols running in parallel on the same client. Furthermore, as we said before, there's also user-to-user interaction through file sharing, which is captured in our model through the share and accept protocols. And as we also said before, one of the challenges of end-to-end encrypted cloud storage is implementing the secure channel that's needed to transfer key material between different users. Now, in practice, the channel can be instantiated in a multitude of different ways, for example, by relying on a public key infrastructure, using a secure messaging app, or through password or link sharing. But in our model, we chose to capture this through a generic, unidirectional out-of-band channel between the sender and the recipient. And this can both be seen as a simplification, which allows us to focus on the core cryptography of a cloud storage system, but it's also a way to make our model generic and ensure that we can capture all of the different ways in which this channel can be instantiated in practice. So with that, I'm going to hand over to Miro for security.
Our goal for modeling security is to capture the security against a malicious cloud provider. That means that the adversary plays the role of the cloud provider in the protocol, and it can specify all of the messages sent from the server to the clients. Moreover, the adversary also controls all of the operations executed by honest clients through oracles, one for every core functionality that Matilda introduced. So for example, the adversary can use the register oracle to make a client start a registration protocol run and send the first message to the server. The server can then, or the adversary can then reply to that message. And similar to key exchange, the adversary can also make the client execute the next step in that ongoing protocol run using the next oracle. Recall that security is password-based, which means that every user has a password which is sampled from a password distribution that parameterizes our game. And different users could even have the same password. These passwords are unknown to the adversary, but of course the adversary could guess a password, and this will show up as a password guessing advantage in our security proofs. Furthermore, the adversary can also compromise a user using the corrupt oracle and learn their local state as well as their password. And we model both selective and adaptive compromises. We formalize 2 basic security notions, integrity and confidentiality. For integrity, we model this with an int ptext style game, where the adversary wins if at any point in the interaction, it can inject or modify a file sent to the user without that the honest user would notice this. Note that this is not an int ctext style game, because we are using message-based syntax, and so we don't define when the ciphertext is actually sent to the user. In fact, the ciphertext could even be split across many different messages. The downside of this is that our security notions also cannot refer to ciphertexts. For confidentiality, the adversary wins if it can learn anything about the files that are uploaded, except their length, or in addition to their length. And we model this with an int-CCA style game, where the adversary can use the challenge oracle to specify 2 files, which one of them is then encrypted and uploaded by an honest user. And the goal of the adversary is to guess which file was uploaded. Now recall that all of these interactions run while the adversary has full control over all of the other operations that honest clients concurrently perform. And so there's a lot of complexity in formally modeling this, and we need to exclude a lot of trivial attacks very carefully. All right, so let's recap. When we started working on end-to-end encrypted cloud storage, it was an elusive goal that hadn't been formalized in theory and therefore wasn't possible to achieve in practice. Now we've formalized the syntax of cloud storage and defined security notions, making this goal concrete. Namely, we defined confidentiality and integrity, and with these security notions, we can formally capture the attacks against Mega, showing that they fall short of achieving the goal. But we're still missing a construction, a cloud storage scheme that can make it to the goal. So the last thing that we'd like to talk about in this talk is our proof of concept protocol called CSS, which is a cloud storage scheme where we were able to prove that it achieves confidentiality and integrity, and so that makes it the first provably secure cloud storage scheme. So let's see how CSS works. CSS is a two-party protocol that is an interaction between a client and a server. The client takes as input the user password, as well as a globally unique account identifier. And then it runs an interactive protocol with the server to compute an OPRF on these password and account identifier values and derive a key. The server uses an OPRF key that was picked by the client at random during registration. This somewhat unusual choice is because we don't trust the server to honestly generate this key. The OPRF key is then used in a PRF to derive different keys for different purposes. First, the client finishes authentication by deriving a MAC key and then using that to compute a tag on a session identifier that is picked at random by the server. And the server can verify this tag using the same MAC key, which was previously exchanged with the server during registration. If this verification succeeds, the server considers the user authenticated and allows the user to perform file operations. From the OPRF key, we also derive a key encryption key. This key is used to bootstrap the file, the key hierarchy used to encrypt files. But we don't use this key directly to encrypt file keys. Instead, we encrypt a master key that's picked uniformly at random. And then we use that key to encrypt the fresh random file keys that are picked for every file that needs to be encrypted. The reason for doing this is that this allows the user to change their password without that we would have to re-encrypt all of the file keys. Now, the resulting file ciphertexts need to be uploaded to the cloud provider, but we also need to upload the encrypted file keys as well as the encrypted master keys, so that the user is able to recover all of the keys in the end and decrypt their files. All right, so let's conclude with looking at the history or development in cloud storage. Starting in 2022, there were various attacks on cloud storage providers, breaking Mega, Nextcloud, and others. And so we took a step back and formalized the goals that you want to achieve for end-to-end encrypted cloud storage. However, there's still a gap between theory and practice. And while our protocol CSS is an attempt to bridge this gap back to practice, we need your help to truly bring provable security for cloud storage to practice, and in particular to build a deployed protocol with provable security. So there are still a few things missing. CSS currently only exists on paper and doesn't have an implementation that's ready for a large-scale deployment. We're also very interested in hearing your feedback, ideas for model extensions, or crucial features of cloud storage that we missed. Also on the theory side, currently CSS only has a proof in the selective security model, and proving it adaptively secure is an open problem. Our full paper is on ePrint. Thank you very much for your attention.
We have time for one quick question.
Your construction, I guess, uses OPRF, and right now, even though there are a lot of advances in post-quantum OPRF, my understanding is it's still not super practical, even though I guess it's improving this. So do you have any ideas or any modifications to your constructions that could be made post-quantum secure today and efficient?
We have not thought about this. This is a very interesting question. In our construction, we had to specifically use 2-hash Diffie-Hellman to make our proof go through because we relied on the hash functions modeling as them as random oracles. So I think this will be a deeper change to figure this out.
So it's not even generic, yes. I mean, it's a nice framework, but you're saying you instantiated non-generic.
The OPRF is the one thing that we had to not handle generically. The other building blocks are generic, yes.
In particular, the reason for this is that we're in this malicious server setting, and OPRFs aren't usually proven secure in that setting to begin with. So we don't only need a post-quantum one, we also need a post-quantum malicious server secure OPRF.
Thanks.
I think we'll have to cut off the questions now, and hopefully you can catch Matilda and Miro.
Please find us
during
on the hallway.
break. Thank you. Our next talk is Mind the Gap, Secure File Sharing. This talk will be presented by David Balbas and Nicola Dardanas. Welcome.
All right, thank you. Good morning, everyone. We're Nicola, David. We're going to talk about secure file sharing. So we just saw this in the previous talk. Cloud storage is difficult and a bit broken when it's deployed out there. So today we're going to talk about an aspect of cloud storage which is kind of tricky. And as we saw in the slide of the athletics, all these providers were tripping in the file sharing part. So we're going to talk about file sharing and in particular about secure share folders. A secure share folder is simply a system where there is a group of users that upload files and retrieve them later, and all of these should be end-to-end encrypted. So there are many ways to build a folder like this. There's not a unique solution. There's one which is simply, I have a file, I want to upload it, I share it pairwise with everyone, or maybe I share the encryption keys, and that's it. It works, but it creates a few problems, and it's also not too efficient. So the attempts in practice, for example, the thing that Mega is doing is actually having a static folder key that all the members of the folder know, and they agree on it, and then they use it for encrypting the files or for deriving some file keys that will be used to encrypt these files later. However, this presents a few complications. The first one is that if we have a static key and we have some dynamic members, so this is that we have a sequence of epochs where the members of the folder change. This is not good because if I get removed from a folder, I shouldn't continue having access to the files that are uploaded, right? So we need at least some form of key rotation. And the second part, also related to the key rotation, is that this kind of system with a static folder key doesn't provide any security against state exposure. And if we're using this system, well, in general, no, but especially for sensitive data, we may want some resilience against a user having their state exposed. So what we tackle in this work is to build secure share folders based on this approach of group key agreement. And we're aiming for some protocol that has strong security, but is also efficient, and especially that is usable in the real world. So let's see how we do all of this. The first thing I want to talk about is security, and it's more about what is the security notion that we can aim for. So let's see this sequence of epoch keys, K0 all the way to somewhere in the future. These represent group changes or key updates that the members of a folder do. And let's assume that Alice and Bob are at epoch 0 in the folder, then Charlie joins at epoch 1, and then Charlie leaves the folder at epoch 5. So the keys that Charlie should have access to are clearly those in the interval 1 to 5, right? Those are the intervals that should be known, the keys that should be known by Charlie. And this notion of security is simply called, we call it interval security. Now, if there is a state compromise, if Charlie is compromised at epoch 3, what keys can we secure here in the persistent data setting? So as opposed to, for example, messaging where we can get rid of keys immediately, here Charlie must have access to these files persistently or to whatever is encrypting with these keys. So by correctness, we can't avoid the leakage of K1 and K2 because those keys have to be kept in memory. But we can prevent, if we want to, the leakage of future keys that the folder members are using. So this gives us a notion of post-compromise security that is possible to achieve in this setting. Now, how can we do this? Well, there is kind of naive, natural attempt to build this protocol, which is not bad at all. We can leverage a group key agreement like CGK, for example, the one that is used in MLS, where simply the members of the folder run a group key agreement. This group key agreement supports dynamic membership, so we get these epochs and security for like interval security for free. We derive a fresh key per epoch. This corresponds to members being added, members being removed, or simply members of the folder wanting to update their keys at some point to achieve post-compromise security. And we store all these keys. And then we access them when needed. This is nice because of security. TGK is good for this. We also have an MLS implementation available, so we should be able to use this and in the real world. But the problem here is that the state that the users have to keep is going to grow linearly with a number of epochs. And this has a few drawbacks related to storing this state, sharing it later, accessing it, and so on. So it's good to aim for a compact state as we do in the case of messaging as well. So we pose the question of whether we can get a good trade-off. And for this, we introduce Grappa. Grappa is a protocol that takes care exactly of this thing. It takes care of the key generation of a sequence of persistent keys and supports dynamic members. So how do we build Grappa? In a nutshell, we use two primitives. We do use a continuous group key agreement. We do use CGK as an MLS. And then we use a second primitive that we introduce in this work that we call interval scheme. So an interval scheme is essentially a compact primitive that allows a user to derive from a very small state, from a constant size state, a sequence of keys that are bounded to a given interval. From left to right, only those keys and nothing beyond. This gives us this interval security we were talking about. And this interval scheme supports updates. So these intervals can be extended, or they could, with the right implementation, even be punctured. How does this work together? I don't want to get into the details. This is a complicated protocol, but in a nutshell, CGK is used as a transport layer. We're using the CGK keys to encrypt the updates that are sent about the interval scheme. So the interval scheme keys are those that we're going to use to encrypt our files or to derive the file keys eventually. And CGK is only used to have a common communication channel for this purpose. So this is what we presented. We introduced Grappa, gives us strong security for persistent data. Of course, this is a probably secure protocol. We can prove that we get a good form of PCS and we get interval security. We have a compact state. We believe this is useful in practice. And also we find very interesting that is perhaps the first time, I don't know if anyone else has been trying to experiment a bit with this, but it's maybe the first time we're taking CGK to a use case which is not related to secure messaging, and we're studying how it behaves in practice. This is cool because everyone is going to have CGK in their phones, in their laptops soon. So it's kind of natural to see what else can we do with this protocol other than simply use it, well, not simply, but other than using it for secure messaging. So we want to look at the challenges that this supposes. And for this, we did a real-world implementation, or an implementation in the real-world setting that Nicola knows much more about it than me. So he will talk about that.
So thank you, David. Let's talk about implementation. We want to implement this secure shared folder system on top of the primitive that David was talking about, Grappa. And yeah, as you can imagine, things don't work as easily in the reality. The main focus of this part of the talk are exactly those differences that we find between the model and the reality that we call engineering gaps. The first one, so in the model, users are described as letters and state are described as variables, but although this is very neat, in reality, this doesn't happen. We have real users with real needs and real devices that can have very different capabilities. For example, the type of crypto they can run. And another very well-known problem is that, or difference gap, is that the primitives are normally mathematical objects with mathematical properties and guarantees, but those needs to be respected in the implementation. And this requires that the execution platform provides us with some support for those operations. As well as implementers, we don't want to risk vulnerabilities and also to have to do more effort than necessary. So we want to rely on libraries. For example, in Grappa, David was talking about CGK, but in the implementation, we are going to use an MLS library. Now, to solve the problem of having the code running in multiple devices, and also to solve the need of the user to access the cloud application easily from multiple devices, we decided to go and try to implement it, the client for a browser. This comes with the fact that browsers implement the WebCrypt API, which is a standardized API and provides us with those low-level operation and cryptographic primitives that we need. And this is also implemented for other JS runtimes like Node.js and Dino. However, as this, again, in reality, this API is not as neat. For example, we found out that it exhibits no standard behavior in different implementation. This is due to some loose specification. For example, the MLS library that we use relies on the fact that public keys are calculated from elliptic curve, they're encoded private keys when the public key field is missing. The excerpt that you see in the slide is for request for comment 5115. And you can see it states that the public key should be there, but it doesn't mandate it with a must. This leads to the fact that this works in Chrome, but Safari and Firefox will just crash when you try to import the raw bytes, while Node.js requires a workaround that we implemented. Next, the WebCrypt API has the problem that most of the new primitives are not there. It's quite old, and it's quite overprotective. Implementing actually advanced script is not easy. As a simple example, we want to do a key derivation from an HKDF key into another HKDF key. This doesn't work. The workaround is to first derive an HMAC key, then export it back into raw bytes, importing back into HKDF key object. This breaks the API abstraction, but there is no other way to do it. Next, engineering gaps. We are going to shift the focus. So we are going to talk about atomicity of operation in the protocols. As you have seen already in David's part, Grappa is made up of two main primitives, CGKA and an interval scheme. And however, the operation, each Grappa operation is atomic on the state. So either it completes the update or the state is completely discarded. This doesn't work really well in reality, especially when we want to consider resiliency against transient error like network failure or something like that. And we are going to display why. But first, we talk about why MLS is indeed atomic as a primitive by itself. So in this picture, you can see a client that is in epoch 0 with a secret key 0. And the client wants to perform a commit operation. So it builds a commit message and sends this to the delivery service. Now there are two cases. In case of failure, the client can just discard the commit and stay in key 0, no problem. In case of success, the MLS client can process the commit and then advance to key 1. We want to stress here that the process of the commit happens afterwards the communication happened already with the delivery service. Now, okay. Now in Grappa instead, we want to compose MLS and interval scheme. As you already seen, we want to transport the interval scheme update through MLS. So to do this, we actually need to process the commit before add in order to have the new secret K1, so that when we encrypt the interval scheme update as an application message in MLS, we are sure that this is only readable by legitimate group members at the time. Then, however, if there is a failure, we are kind of stuck. We cannot roll back anymore to key 0 because the key 0 is already lost during the process of the commit. But there is no problem in case of a success. We still display this because you can see there is a no operation on MLS that is actually really stressing the fact that the update doesn't happen at once. The interval scheme process update is afterwards, right? So to fix this, what we do in practice, is that we create the next K1 in memory. So we process in memory, and so we maintain in persistent storage key 0. At this point, we can encrypt the interest scheme, and upon success or failure, we can actually either roll back or complete the processing by overwriting on persistent storage. However, this practical use case have also maybe implication on security. So if we want actually to use MLS as a transport layer, our insight is that we need to study and formalize the security of this use case. And with this, we end the presentation, and we are open for questions. Thank you for listening.
I didn't quite understand the point made about sort of which keys are inevitably compromised in the case of a client being compromised, because yeah, if you can go back to that, thanks. So if you assume that a client is uncompromised up to a certain point, then it can delete old keys, delete old versions of documents, delete any documents that are deleted from the folder. So why is it inevitable that that information is compromised?
So you're talking about deleted files, if I get this right?
Well, so if you assume that the keys are necessarily compromised, then that doesn't that prevent you from allowing the attacker to get the old versions of documents from the ciphertext?
So the thing is that we don't want to be re-encrypting the files in the folder, because this is an expensive operation that has to be done locally. So cloud providers are not very happy with this operation, and then the best you can do without re-encryption is something like this.
So it's a bandwidth and performance trade-off rather than an inevitable consequence. Thanks.
Thank you for your question.
We'll take another quick question.
Maybe quick question. So syntactically, what you call interval scheme looks like a special case of something we call compact key storage.
Yeah,
Is a formal connection, or is there something that interval scheme achieves, which is more or less than CKS?
So we built this concurrently. We have a comparison to this. There are some differences, but maybe we can discuss this offline in detail, because it's an interesting question. Thank you.
Okay, let's thank our speakers again. Thank you. Our next talk is CRIP, end-to-end encrypted audio calls, short, and will be presented by Ahmad Adari Bani. Welcome, Ahmad.
Thank you for the introduction. My name is Ahmad. This is a joint work with my colleagues at Nokia. You might remember us from this rock-solid product, if you're old enough. I think there are a lot of old people here. But today, we are building infrastructure for that powers the internet. For example, we are building network routers that can process up to 400 terabits per second. We are also one of the leaders in building and deploying infrastructure for 6G and 5G network, future 6G. We don't have 6G yet. Okay. In 2021, there was this funny situation in which a senior lawyer had this cat filter on. You might have seen this. What would you do if you were in such a call, if you were him? I would switch off the camera and continue the call. But what if the audio was not working and the video was fine? I think we couldn't have the call, right? We would cancel the call. So audio is really important in such a calls and sessions that are sensitive or not sensitive even. For many years, we have been building systems and protocols for end-to-end encryption. We have many protocols like Signal Protocol and also the MLS standardization. But we didn't talk enough, and we didn't care enough about audio from security and privacy and also efficiency perspective. So in this talk, I want to share our results with you from this perspective. If you take your phone and go to the operator setting, there's an option called Voice over LTE. So when you talk to when you call someone, your audio signal goes through infrastructure known as IMS. IMS is standardized by 3GPP. So your audio signal is encrypted, sent to an operator server. The operator server decrypts it, they enhance the audio, they do some operations on it, they encrypt it again and send it back, send it to the recipient. This can be more complex if the recipient comes from a different operator. So the operator server sends to the other operator, they decrypt it, they enhance the audio or do other processing, and they send it to the recipient. This could be even more complex. It can be a conference call. If there are multiple people talking from the same, multiple people are in a call. And if these two people talk at the same time, or if they don't talk even, the audio signal goes to the focus server from their operator, and the audio signal is combined into one stream to optimize the network. And then that mixed stream is transferred and relayed to the next operator server and sent to the recipients, and they can have a call. So this process is called audio mixing. So if I want to generalize audio mixing, Alice talks with microphone captures the audio signal is transferred to the other participants, and the others also in a call, they're talking, the audio signal is captured and sent to everyone else. But as you can see, the network traffic is not nice. It grows quadratically. But we can do better, like IMS. We could send it to a central server, and the central server would mix it centrally and send back the mix stream to everyone else. And we would have linear network traffic, and it's much better. But if you want to have end-to-end encryption, this would not work because audio mixing happens in plain text domain. So we have to have the plain text signal to be able to do the mixing. So this is hard. We are back to square one. Again, we have to, if we want to have end-to-end encryption, we have to encrypt the signal and send it to everyone else. And then locally, each participant performs audio mixing and they can play it back. But we would like to have end-to-end encryption, but this is not good because traffic grows quadratically, as I said before. And also audio synchronization is harder because we don't have central server. So that means we don't have central clock that we can use for synchronization. And now we have to deal with the distributed systems, which is really harder to have high quality audio call. And also some of these enhancing techniques for audio are proprietary, and companies they're reluctant to ship this to the client side. We cannot also perform all of those nice proprietary audio enhancement technologies. You might say, I've been in big meetings that everyone else is muted and one guy is talking. And he talks, you can have end-to-end encryption easily, and then there is no network traffic. But we know who's talking, so there is no speaker anonymity. So we would like to build infrastructure for everyone that at least we can preserve this quality. We can have a speaker anonymity. So this is not something, having no speaker anonymity is not something that we would like to have. But so in an ideal world, it would be really nice to have end-to-end encryption and have some central server there that can obliviously mix the audio stream and send it back to every participant. But in plain text domain, without having a decryption key. So we are in real world crypto. We have to see how we can achieve that. So we looked into the literature to see whether there is any previous attempt to fix this, to solve this problem. We found this paper from many years ago that they use homomorphic encryption to encrypt the audio and also mix it centrally. We found this very interesting, and also there's a thesis that tried different schemes with homomorphic encryption and presented some benchmarks. We thought, okay, let's call this blind audio mixing. That means every participant in a call encrypts the signal, send it to the central server. The central server performs SIMD addition and send back the mix to every participant. But there's a caveat here. In homomorphic encryption, if you take the plain text audio and you encrypt it, you will have expansion. For very small parameters, you can easily have 10x expansion. And if you want to really do more processing on the audio and have more noise room, if you're familiar with FHE, then this number can be easily 30x or 40x. And audio is not forgiving. Real-time audio is not forgiving, because if you want to have high-quality real-time audio, the maximum latency should be at least less than half a second, as you can see. And also, the maximum bandwidth consumption should be less than 1 megabit per second, which is already a lot. But with this setting, this is not going to happen. We thought we can play with the FHE parameters, but then there is a limit. We cannot get smaller and smaller. So we thought, let's compress the plain text signal before encryption. So we compress the audio signal. For compression, you can imagine something like, for example, MP3. And then let's encrypt it, add it with FHE, then decrypt it, then what we get is garbage. Because, yeah, that's fact. Because if you use MP3, the homomorphism of the plain text data for audio mixing, because audio mixing basically is addition of the signal. If you're familiar with audio, this does not work. We thought, okay, let's decompress, then evaluate. We encrypt the audio signal, we compress the audio signal, like before, we encrypt it. In the encrypted domain, we run the decompression circuit with FHE. Then we add it, we decrypt it, and we have the mix. In fact, it works. But we want to be real time. This is not going to work. If you want to compute the FHE circuit of decompression, it's going to be very slow. Maybe with hardware accelerators one day, but we're not there yet. We thought, again, we have to go to the ideal world land. What we want, we would like to have an additive homomorphic compression. You might have seen this paper from Google more than 10 years ago, if I'm right, which is known as Word2Vec, which is about text embeddings. What are embeddings in neural network? Embeddings are vectors of features. Then you fit some data in it. So what they have done, they fit text data to this neural network and they got embeddings. And they observed that linear operations like addition, subtraction, if you have perform these operations on these embeddings, you are again receiving a new embedding which has a meaning in that domain, in the latent space. For example, if you have Paris minus France plus Bulgaria, you would get embedding of Sofia, which is very interesting discovery. We thought, can audio embedding have some homomorphism? We thought, let's try this. But there is also a famous hypothesis, which is known as linear representation hypothesis in the AI community, which states that an embedding is a linear combination of features, F. And if you have two embeddings, if you add them together, you get a new embedding, which is a valid embedding, and it is also, again, a linear combination of features. So there is some notion of homomorphism there, additive, especially additive and additive homomorphism. We thought, let's put this in practice and see what happens. Then we thought we need a neural compressor, neural audio compressor. We found this paper, shout out to people at Meta for writing this fantastic paper and also providing the source code for us, for everyone, and the model and everything. We took this paper. Well, maybe first explain how the paper works. You take the audio signal, the raw audio signal, give it to this block, which is encoder, which is composed of a number of convolutional layers. As you can see, the width of convolutions is getting tighter and tighter. So that compresses the audio. And what you get after the encoder is a vector of vectors. Vector is the number of embeddings that are representing this audio. Then there's the quantization layer in between. What it does is that quantization, if you're familiar, there are code books of lots of different embeddings. And what it does, it checks that if your vector of features goes to certain vector in the code book, they take that index and replace the audio signal with that index. So we would end up with a bunch of indices which represent your audio when we're compressing. Then we thought indexes are not going to be additive homomorphic. You have to drop this part. We take the embeddings from the output of the first block, which is already compressed in time domain and also in amplitude. We take this, and we thought, okay, let's put this in practice to see what happens. We fit the audio signal to the encoder, and we get some embeddings. Then we can even truncate it more because it's audio signal to have a smaller, in this example, 8-bit values. And then we encrypt this. We add this homomorphically. We decrypt it. We do the decoder with the reverse process, and we get the audio. We discovered that audio embeddings have additive homomorphism, and we can have audio mixing with this, meaning that if you're talking, if I'm talking, and we have two signals, if you add them, the final signal we get here is like both of us talking at the same time, which is really cool. But this is even more interesting because we can do more configurations. There's a degree of customizability here because, as you can see, there's a width of the convolutions there, the blue boxes. You can have different size for different width for each block. So that means that we're flexible to have different degree of compression, different rate of embeddings per second, and we can also truncate to different sizes. We can have different number of bits, and that allows us to optimize towards different network environments. For example, we can have low bandwidth, optimize towards low bandwidth settings or low latency settings, or even different quality of audio. And this gives us real-time and flexible, and of course, obviously, secure streams if you combine it with the homomorphic encryption. We thought, okay, let's implement this and see what are the numbers, because we want to see, can they be real-time or not? If you see in the blue line is the mesh architecture that we had, not the mesh setting. But this is network load per user, like how many megabits per second per user. So the blue line is the consumption, is the mesh setting. So everyone is sending audio signals to each other. You can see with more number of users, we are consuming, this is going up rapidly. This is not good. And the purple one, do I have a pointer here? Okay, it doesn't matter. The purple one, that one is end-to-end encryption without any compression. As you can see, this is not more than 5 megabits per second. It's not going to be real time, or the bandwidth is really bad. But the green one is with the compression. As you can see, this is like end-to-end encrypted centrally with compression, and this is almost less than 1 megabit per second. So we can have real-time audio call. And this is a really fantastic result. And for me. But the overall network load is also like that. As you can see, the blue one, which was the mesh, it grows quadratically with more number of users. But what we have to look at here is the green one. Green one is us, and the red is plain text with no end-to-end encryption. Nothing, just IMS, central server. We are almost very close to that one, which is very good. But there are a lot of open challenges. The story is not over. I mean, this is just the first result we have in this domain. So we are real time, but if we want to perform more advanced audio processing, like, I don't know, some advanced processing, it is likely that we cannot be real time. So we need more innovation there in terms of hardware acceleration. And there are some companies working on this. I hope we can have hardware acceleration as soon as possible. But also, we optimize the bandwidth. We can still get better, I'm sure. For example, we can have better transciphering schemes, faster, hardware accelerated. We need more innovations there. We are not there yet. And also, we as Nokia, we are in a situation, we are in a position that we can incorporate FHE in different spec. But as long as it is not standardized, it is not easy to do that. So there is a standardization committee, and there was a meeting, I think, before this conference. We look forward to seeing this getting standardized, that we can use it in real world. But we focus so far on the bandwidth and the architecture, homomorphic encryption, and that aspect. But of course, we need group key management, something like MLS. But this is slightly different. We have different requirements because keys in homomorphic encryption, if you are familiar, there are different keys, and we are not dealing with 40 bytes. We are dealing with hundreds of megabytes or sometimes gigabytes of keys. So requirements are slightly different. This is open. We haven't looked into that. We're going to look into that, and I hope we can collaborate with some of you to make this work. And last but not least, in every country almost in the world, I checked on Wikipedia, there is a law about lawful interception. We have been building apps like Signal, like, I don't know, other platforms that are end-to-end encryption, but we don't care about infrastructure that much. And it's 2025. I think we have to find a solution for this as a community. Just wanted to raise this. Yeah. We have a demo. If you want to see this working, we build a prototype. You can come after the talk with me and my colleague Lode, who's sitting here. We can show you that actually this works, and we can try it together. Thank you.
So if I understood right, you are just doing linearly homomorphic encryption You just add in stuff, yeah?
Yeah.
So why not just throw out CKKS and BFE and whatever and just use Paleo? Because then your bandwidth expansion is going to be really, really small.
Yeah, but
It's not as cool. It's old.
that's true. It's not cool. It's not post-quantum. But first, we want to be post-quantum, but that's one reason. The second reason is that with CKKS, we can batch lots of samples. Audio signals are a lot.
Oh, I see. So you could do a lot in.
Yeah.
Okay.
That's why I dropped the SIMD term there for those that they know what I
okay.
mean, because there are a lot of samples. Boom.
So a lot of the overhead here might be due to the assumption that you need to be able to add the signals from n streams rather than, say, the 3 loudest streams. Is it possible to say, so you have n encrypted streams, but in the FHE scheme or whatever simpler scheme you use, you detect the 3 loudest ones and produce an encrypted version of that? Is that an easier problem than trying to add all of them?
I'm not sure I understand the question. Could you repeat one more time?
So the assumption behind the problem is that you need to add all of the streams.
Yes.
Rather than saying
Sending
add
one.
the 3 loudest streams, which
Right.
in practice will probably be sufficient.
Yeah,
right.
yeah.
And so if you can select the relevant 3 encrypted schemes and then transform them so that an adversary doesn't know which ones they are.
I understand.
It's the similar problem to a mixnet.
Yeah. That's a solution. We haven't looked into that, but it's an interesting avenue for research.
Okay.
Yeah. I think Meta is doing something like this. I was talking to an engineer.
So have you looked into, because the way it looks like the problem is defined, into secure aggregation protocols for this?
Not yet.
Okay,
But-
so because it looks like all you're doing is just the addition of vectors, and it's a controlled environment in a way that I think parties can exchange some keys with each other.
Yeah.
So secure aggregation might be a sort of.
Yeah, it's an interesting pointer. But we would like to do more than just adding, but
Oh,
this
more
is the first
functions.
result we're showing and from the perspective of bandwidth, but yeah,
Okay, awesome, thank you.
thanks.
In the beginning of the talk, you said that speaker anonymity is a desirable property, and I was wondering why.
So political question. We would like to have that, so there's no, some partners require that. I cannot discuss this further.
Okay.
We can
Thank
take
you.
this offline.
So it's quite interesting to add the voice of different people, but how about subtracting? So what about, see if I'm in a conference call with someone in the next door, I can record it and just inject the negative of his voice to the conference.
Yeah, we have results for that, but I couldn't fit it into the slides. So maybe next year, Provable Crypto, we did that. Very good observation.
Okay, let's thank our speaker again.
Thank you so much.
Our next speaker is Mallory Nodal, who will be presenting on how to think about end-to-end encryption and AI, training, processing, disclosure, and consent. Please welcome Mallory.
Hi, everyone. Yeah, thanks so much to the conference organizers. So the title of this talk and the paper is How to Think About End-to-End Encryption and AI, Training, Processing, Disclosure, and Consent. This was a group effort by PhD students and law students at NYU and Cornell. I'm Mallory Nodal. My co-presenter, Daniela Ferrari, couldn't be here. But this was co-authored by Andreas, Jacob, Betty, Derek, Sam, Kyung-Young, and Sanu. Derek and Sam are also here, so hopefully we can talk more afterwards. Our motivation for this was that end-to-end encryption has become the gold standard for securing communications, no question about that, bringing strong confidentiality and privacy guarantees to billions of users worldwide. However, the current push towards widespread integration of artificial intelligence models, including end-to-end encryption systems, raises some pretty serious security concerns, and we wanted to know what they are. 3 products we cover in the second version of the paper are Apple Intelligence, Meta AI, and Samsung AI. These tools already have the capability of processing end-to-end encrypted data, at least in certain situations. And so all 3 that we look at have this capability, but I wanted to just talk about 2 examples really quickly to set the scene. So on the left, this is the sort of notice and consent that pops up if you open WhatsApp and invoke Meta AI in a group chat setting. So people are starting to get their phones out. You can check this out for yourself if you haven't already consented to this. The screenshot on the left then is what you get on your iPhone for the entire operating system. And I think the juxtaposition here of privacy and ChatGPT is really interesting because a lot of us might have intuition these things might be incompatible, at least in the case where you're using an end-to-end encrypted product that Apple offers, such as iMessage. So our question is processing of message content by integrated AI models compatible with end-to-end encryption? And if so, to what extent, under what circumstances? So the talk outline just goes over our recommendations. We have a couple that are really based on security considerations, so training and processing. What kinds of AI integrations are compatible with end-to-end encryption is the question there. Our second 2 recommendations are more legal and normative considerations. We included legal experts and AI experts because we're admiring this problem from a lot of different perspectives. And so we take the security considerations. Given those, we are curious about what clear disclosure and meaningful consent would look like. So I'm going to walk you through each of these. So for training, this is our first recommendation. The background you need here is that models have configurable parameters, which are numerical values that determine how outputs are generated. The goal of training is to tune these parameters over many iterations in order to capture more and more patterns. Models at the scale of commercial AI assistants contain billions or even trillions of parameters trained over months. On the other hand, you have inference. So trained models are used to generate real-time responses to user inputs. One user query is processed through many steps using the model parameters to calculate an output. Continuous improvement is achieved with usually human feedback. This diagram is depicting what we are typically used to seeing in commercial AI on the left. So the yellow represents the service, which is in a cloud, and then the blue is the user's device. So what's important to note is that everything then in the yellow is off the device, which is not typically what we're comfortable with in end-to-end encryption. The end-ness is quite important. So you'll notice the model as well as chat logs, data storage, the training happens, and then the metadata is also all in the cloud. This is again typical, right? But if you looked at a local architecture, all of this then moves onto the user's device. But this includes the model, this includes the training and the processing, which for a lot of end user devices could be pretty challenging from a computational perspective, right? So this leads us to our first recommendation. It's on training. It is impossible. There is no way that we found in our analysis to use end-to-end encrypted content to train a shared AI model in a way that is compatible with the confidentiality and privacy guarantees of end-to-end encryption. And by shared AI model, what we mean is a model that may be used for inference by multiple users or may be trained on multiple users' queries, which is these sort of commercial AI assistants at their very heart. So moving on to the second recommendation, we need to introduce an additional piece of background here. We are not going to cover encryption for this audience, but we do want to invoke a little bit more about what this cloud-based processing and training would look like, and most notably, private cloud computing and other things have been suggested. So we wanted to compare then these trusted hardware goals against the end-to-end encryption goals. Now, I do want to state, like, privacy against third parties, integrity and tamper resistance are definitely goals of both. But end-to-end encryption and trusted execution environments have different, orthogonal, and incomparable security guarantees. So we try to show that in the slide. They're just not the same thing. I think that's the major takeaway from our analysis. And we did actually look at other privacy enhancing technologies besides TEEs, although there have been no big papers or schemes that have suggested you could do this on with commercial AI assistance in encrypted messaging apps. So but we did go through them, right? So we have this evaluation framework, an analysis that looks at these different potential architectures. Maybe we start at the bottom and you can see, server-side plain text inference it's not going to work. It's the most vulnerable. All the way at the top, you have potentially an on-device model that's locally fine-tuned, or maybe you have some server-side interference that uses fully homomorphic encryption. Like, that could also not be super objectionable. But we did notice that some of the things we looked at that are real proposals out in the world fall into this not compatible bucket. This is our second recommendation now, and it's a bit lengthy because it's got a lot of nuance. So processing end-to-end encrypted content for AI features, both inference and training, could be compatible or may be compatible with end-to-end encryption, but only if the following recommendations are upheld. So you want to prioritize endpoint local processing whenever possible. And if processing end-to-end encrypted content for non-endpoint local models, then no third party can see or use any end-to-end encrypted content without breaking encryption. And a user's end-to-end encrypted content is exclusively used to fulfill that user's request at that time and no more. By this, we mean content is not just the message itself, but any derivative, non-trivial function of that content. And then what we mean by breaking encryption, you could do this without breaking encryption with some privacy-preserving technical configurations like FHE. So I'm going to transition now to the last two recommendations, which are if you recall, the legal and normative recommendations. We felt that the security considerations implied that we needed to look at this problem from this angle as well. So in the paper, there are 4 main areas of law that affect how messaging services can be regulated for privacy-related obligations: contract law, consumer protection, data protection, and antitrust. I'm going to focus mainly on the first 3 areas, which are more directly related to our focus. So one thing that these areas of law have in common is the reliance on user consent as an important part of how companies can justify collecting and using user data. So in the US, the notice and choice or notice and consent model is the dominant framework for how the law treats online consent. It's seen as a two-way stream where digital services like messaging apps would give users some form of notice or disclosure of their terms, typically in a privacy policy or terms of service agreements. And users will consent to these terms by signing up and providing their information. They click on an I agree button, or they just continue to use the website, right? There are these critiques though. 1, consumers do not read privacy policies or terms of service. 2, company data practices and privacy harms are hard to understand. 3, there are limited alternatives. If you say no to using one website, where do you go? 4, user preference may change over time and could vary according to the context. And the last one, individual consent does not capture well in group settings. But despite all these critiques, that consent is really a fiction, the fact is these asymmetric contracts determined by the companies are still legally valid and enforceable, in the legal landscape. So what does this mean? I mean, our interpretation in then is that contract law likely can't do much to protect consumers. So what's a more promising way to hold companies accountable to consumers? In the US, it's consumer protection law. The Federal Trade Commission, known as the FTC, is the federal agency that investigates unfair or deceptive company practices. The FTC can investigate security-related incidents as deceptive practices, and the focus is on the disclosures and whether the company's statements are misleading to consumers. There's a good case here. In 2020, the increased use of Zoom by consumers during the pandemic led to the discovery that Zoom was not protecting all video calls with the end-to-end 256-bit encryption that it was advertising. So this and other FTC cases have marked precedents that if a service is marked as using end-to-end encryption, the service must implement it throughout the processing of the data on by default, and has to meet industry standards for what is end-to-end encryption. So, another promising way to regulate companies, Europe has found, is through data protection law. This generally sets rules for the handling of personal data. The US doesn't have a data protection law for consumer privacy at the federal level, even though more and more states are adopting this. Most of them that we've seen are reinforcing the notice and consent model, and they focus overly on opt-out. So talking about Europe, it's more robust data protection landscape, and the GDPR is the most prominent law here. GDPR goes beyond notice and consent. It imposes broader data obligations on companies that offer services to people located in the EU. For example, companies need to have a legal basis for the processing of any personal data. User consent can be a legal basis, but needs to be shown by an affirmative act of acceptance, such as by clicking a button. There are other EU laws beyond the GDPR that touch on regulation of personal data and opt-in consent. So the e-privacy directive regulates the confidentiality of electronic communications and requires opt-in consent for storing or accessing information on a user's terminal equipment. The Digital Markets Act regulates competition and requires opt-in consent for merging data between a company's different products and services. There's also the EU AI Act that's recently reinforced the GDPR and the e-privacy directive's application in the context of AI systems. It's a complex web of regulations. And there's some ongoing controversies. So the EU's data protection regime now applying to AI models, there's some ongoing debate about how this is going to happen. But for the first time, EU regulators have begun investigating whether AI developers are actually complying with the GDPR when they're training AI models on personal data. So one is the Irish regulator questioned Meta for updating its privacy policy to allow for AI training on public data, mentioning issues related to user consent. But so far, the investigated AI models have been training on publicly available data. If AI models start training on private user messages or end-to-end encrypted content, and in the paper we discuss maybe some incentives and reason why that's, I don't know about inevitable, but definitely headed in that direction, this would likely raise far more concerns and legal questions related to user consent. So this is our third recommendation, our first of the norms recommendations, that messaging providers should not make unqualified representations that they provide end-to-end encryption if the default for any conversation is that end-to-end encrypted content is used, either for inference or training by any third party. And then the fourth one is related to the consent feature, and obviously disclosure and consent are very interrelated. Here is a well-implemented consent interface can make a really important difference. Users should be able to consent specifically to add-on features such as AI assistance and the very many ways that they can be invoked differently and in different contexts. And they need to provide a clear and easy to find opt-out mechanism. It shouldn't just be once and forever for all features all the time. So just to go back over again, we talked through these 4 recommendations that all kind of work together. We're really trying to speak to folks who might be thinking about implementing these features and try to help come down on the side of encryption, right? That was the sort of, hopefully, conclusions that you can draw from ours. Again, this is what we set out to, the central question we set out to talk about. There's a whole lot more in the paper. There's some really interesting discussion sections about how this maybe relates to the crypto wars and things like that, as this continues to unfold with more and more products coming out. This prompt was, create an image of AI assistant reading private user messages. Delightful, right? We also wanted to end really quickly with things that users can do. So there are some, I think some things to pay attention to. Again, this is changing rapidly, but you can pay attention to the operating system level app permissions first. You can also then go into the apps themselves and review settings there. As it's always true, as we heard a lot this week, be aware of what you're sharing and to whom. Don't assume that everything is okay just because it's an end-to-end encrypted app. Things might have shifted. I screen cap opt-in of any kind, right? Because it's sometimes hard to find that screen again. So make sure if you are opting into something, you know what you're opting into, and figure out how to opt out, right? As with any confidential communication that you're really concerned about, it's probably important to just be upfront and talk to your contacts about it. Not always is the consent going to go in every direction. So someone you're talking with might have enabled these features and you haven't. So how does that impact your privacy? Just ask. And then I think it's important to raise our voices about why we care about privacy features. I think there's a perception that these convenient AI features are more important or better, or people like them more. And so I think we need to, because they can be somewhat paradoxical, I think we need to talk about what we prefer and what we really care about. So that's the end of my talk. You can find the paper at this QR code link. And just for fun, there's another AI generated image. So yeah, thanks.
So in recommendation 2, if you could just go back to that slide, says a user's E2EE content is exclusively used to fulfill that user's requests, and then you added verbally at that time. So, for example, if a user deletes data that was previously used to train an AI model, should the recommendation also include deleting the effect of the data on the AI model? I know that may be very difficult, but it seems to me that a user would not expect the AI model to then be able to reproduce that data that the user hasn't explicitly consented to be reproduced.
I can see where you're going with this, and I think we agree, and I think we have talked about how removal of data from a trained AI model is really challenging. So we break that down in the paper, and of course we're trying to be as practical as possible with this. So it's not in the recommendation itself, but I'm guessing you'll find what you're looking for in the sort of rest of the paper where we talk about this. Yeah.
It's helpful that we're on this slide. So here you acknowledge that using things like FHE, or I would argue multi-party computation as well, can make processing compatible with E2EE. What I don't understand is why that's not true for training, or perhaps in what way training isn't just like a special case of processing.
Right, so we go into this, and it's again because it's a shared model. So I mean, you could potentially have that whole model on your own device, and then there's not an issue. But if you're training a huge shared model like this, it doesn't seem to us that there's any way to get around that data, just as the previous question was coming back out again. And then we go into detail about why this is, but this recommendation 1 by far was our strongest recommendation. It just seemed to us that there was really no way around this. We wanted to make as strong recommendation as possible.
Thank you.
Some questions.
Cool.
All right,
Thanks.
let's thank our speaker again. Our last talk of the session is titled Breaking and Fixing Leakage in Content-Defined Chunking. Will be given by Keen Tong Tong and Matteo Scarlatti. Welcome.
So Kim, I understand you really care about your new IKEA furniture, but did we really have to bring it with us on stage?
Well, I mean, I thought it was important. And anyway, well, thank you for helping me carrying these IKEA boxes that we have on stage.
Just in time. Okay. Hello, everybody, and welcome to Breaking and Fixing Content-Defined Chunking. This is shared work with Kian, Simon, and Kenny from ETH Zurich, and Felix from IBM Research Zurich. And I'm Matteo. And I shall find a pointer. So let's start with our puzzling title. You probably are wondering, what are all of these words? Well, let's start with chunking. What is chunking? It's the process of taking something very bulky and splitting it up in smaller chunks that are easier to manage and to transport around. Or to jump more in the computer science world, it's something like when you have a very big file, like a super HD copy of Big Buck Bunny, and now you want to split it in a lot of smaller chunks that are of smaller sizes. And why would you want to do this? Well, let's take the setting where maybe you have this file on your laptop and you want to transfer it on your cloud server. Well, instead of moving the entire file in one go, you can send the chunks separately. And so if something goes wrong over the network and one of these chunks gets lost, you don't have to restart again transferring the entire file. You can just transfer the missing chunk. Okay, this is also another nice property of splitting things in chunks, is that if you have two copies of one file that are almost identical, they only differ in one chunk. So maybe you're working at the Blender Foundation and you have two copies of Big Buck Bunny that are almost identical. Well, you don't need to copy both of them over. You can only transfer the missing chunk, the chunk where they differ, and you also save a lot in your storage costs. Okay, so hopefully I convinced you that chunking is very useful, and that's why we see chunking everywhere. Say chunking in synchronization programs, in IPFS, in software patchers like the League of Legends patcher. And naturally, we see chunking in backup programs, such as Borg, Restitch, and Babstash, but almost all of them. Okay, so how do we chunk? The most naive strategy for chunking is to do fixed side chunking. So we start from the beginning of the file, and then we count n bytes, and there we chunk. So for instance, with this example input file, we would obtain these chunks, one chunk per line. Can you see a problem with this? Well, if we just prepend a single byte to our source file, then we do the chunking process again. We start counting from the start of the file, and we cut new chunks. But as you can see, all of the new chunks are different from the old ones. This is highly undesirable because now we would have to transfer them all again, and we don't get any deduplication. So what we do instead is the second puzzling part of our title, content-defined. What do we mean by content-defined chunking? Well, we look at the source file and we define a window. So a small amount of bytes that we look at. And then based on this window, we compute a chunking predicate, pi. And now we keep changing this window, sliding it over the file. This is what's called a rolling window. And we keep evaluating this predicate until we get an evaluation to true. And here we chunk the file. And as you can probably see, now the chunk boundary does not depend on the entire chunk being cut, but just on a local amount of bytes. Okay, so we keep doing this for all the other
bytes in file. And now let's try to do what we did before. Let's prepend a single byte to our file. And if we're lucky, the first window won't evaluate to true, and we will get a chunk exactly in the same position as before. What this means is that if we compare the original file with and their chunks and the file with chunk with the 1 byte prepended, then only one chunk will change, the first one. All the other chunks will stay the same. So now we solved all of our problems. We're happy. Everything is nicely chunked up in files. And yeah, we have all of our boxes lined up in storage. So Ken, what have you got there? What furniture did I even help you transport here on stage? Oh, well, it's a surprise. It's a surprise for our office. So for that, I even removed the labels, so you can't know what's inside.
So I have no idea. But that box kind of looks familiar. It's like, that size, and these are a bit smaller. I bet that you bought a Kallax bookshelf.
Wait, how did you know that? Are you telling me, are you telling me that without looking inside the box, from the size of the box, you can infer the content of the box?
That's it, exactly. So the size of these boxes is actually leaking something. And this is problematic, to say the least, when we combine content-defined chunking with encryption. There are only two possible ways to do this. One is we first encrypt and then we chunk. Well, why is this a bad idea? Well, functionally, that doesn't really hit our requirements. If your encryption algorithm is any good, changing the plain text will completely scramble the ciphertext. And therefore, like, your chunk boundaries will be all over the place. So what we actually do is first we chunk and then we encrypt. But now encryption has, unfortunately or fortunately, this property that it mostly doesn't hide lengths. So we can take a look at the sizes of the chunks, and this will tell us something. What do I mean by telling us something? Well, if we can see this length, then we cannot quite decrypt the chunks, right? We don't have enough information for this. But what if we break into the server of our target user and we can see these 3 chunks with these exact sizes? And now we cannot decrypt these files, but maybe we can make a guess. We maybe want to check whether our target user has some politically charged documents in their backup. How do we do this check? Well, we take the file, and then we can chunk the file ourselves. And then we will see which sizes of chunk we get out. And if we compare the sizes of our chunks to the sizes that we can see on the server, then we can guess that probably the user actually has that file. So chunking and encryption can be a very dangerous combination. How do we solve this? Well, this is where cryptography enters the game. We add keys to the chunking process. So this is such that given a file and a certain key, and a file and a different key, key prime, we obtain completely different chunks. And this means that more formally, we can define our predicate, what I called predicate, chunking predicate before. We call this window evaluation. It's a function that takes a key and the window as before. Now, as before, like, we roll this predicate, we evaluate this all over the file, and we still chunk where the window and the key make this function evaluate to true. What security would we want or expect from all of this? Well, probably I can convince you that if our window evaluation function with the key behaves like a Bernoulli distribution of parameter lambda to the -1, where lambda is the average size of chunk that we want to obtain, then an adversary could not infer anything by just looking at the size of the chunks. But what about the real world? Do we get this kind of security from keyed content-defined chunking schemes in the wild? I will let Ken tell you more about this.
All right, thank you, Matteo, for spoiling the surprise. Anyway,
So let's see, what do they do in the wild? In general, applications that use key content-defined chunking require some performance. So in particular, we want some KCDC that preserves the rolling property that Matteo was telling you about earlier. That is, you can take an evaluation for a window and then compute the evaluation for the next window very efficiently, posteriorly in constant time and not linear in the size of the window. On top of this, you have to remember that KCDC, the window eval function, has to be evaluated once for every window in the file. And that means in the order of 10 to the 9, 10 to the 12 times. So it must be blazingly fast. So how do you do this? You usually use some algebraic structure. Here's a sort of framework for how a lot of applications do it. In the wild, you take a file that is going to be a sequence of bytes. And then you take a window of these bytes, and then usually they compute some polynomial. Maybe you don't see it right now, but you can trust me that this provides some rolling property. And I'm going to provide an example later. The second step is you take this polynomial, and then you compute a predicate on this polynomial. And if the predicate returns true, then you cut at the end of the window. Now, again, this is keyed. So in particular, both steps, both the computation of the polynomial and the evaluation of the predicate, can involve the chunking key. Let me make this a little bit more concrete by showing you how RESTitch, one of the backup systems that we analyzed, works. So RESTitch works something like this. We have a secret key. The secret key is an irreducible polynomial of fixed degree. Let's call this P. And it's a binary polynomial, so polynomial with binary coefficients. And we take a window, and we compute a polynomial Q over it. So you take a window B1, BW, so these are W bytes, so 8 W bits, and you interpret these as coefficients of a binary polynomial of degree then upper bounded by 8W. Now you take this polynomial Q, and you reduce it modulo P, the secret polynomial. And after that, you check whether the last K coefficients for some fixed K are 0. If all these K coefficients are 0, then you chunk at the end of the window. In other words, the condition is that Qx mod Px mod x to the K, that is, look at the last K coefficients, is this equal to the 0 polynomial? Okay, well, this has a lot of algebraic structure. And let me clarify that again. Every time we see a chunk, we get a polynomial Q, okay? A polynomial Q lives in this F2 vector space, gets passed through a linear transformation, which depends on P, the secret polynomial. So this is an unknown linear transformation, but then it gets mapped to 0. Okay, but then that means that every chunk that we see gives us a polynomial which lies in the kernel of this transformation. So after enough chunks, we can recover, with decent probability, a basis for the kernel of this transformation. Now, you have to trust me here that this is actually sufficient to recover the polynomial P. After you recover the polynomial P, then you know all the secrets that have been used for chunking. So now you can do fingerprinting again. We did not do this only for RESTitch. We analyzed other backup solutions. So we have RESTitch, Borg, Duplicacy, Babstash, and Tarsnap. For RESTitch, as I said, you only need to see some chunks. I did not put any other requirement. This is a known plaintext attack. So if we know that the user uploaded Big Buck Bunny, for example, then that is sufficient to recover the secret. For Tarsnap, we had to use a chosen plaintext requirement. That is, you give a file to the user backs it up, and you get the chunks out of that, even though they're encrypted. Anyway, we managed to break all of these. So these are the chunkers. The chunkers are broken, and so they go in the chunk yard. Now, we said that they want a KCDC which is efficient, but what applications in the wild actually want, we contend, is that actually the chunking decision should be pseudo-random in a cryptographic sense. Now, what this means is what Matteo said earlier. So you take a window and you run window eval on top of it, and then you get a decision bit B, whether you chunk or not. Now, this bit B, which depends on the plaintext, should be computationally indistinguishable from just tossing a coin of the appropriate bias. And because tossing a coin does not depend on the file, this says intuitively that window eval does not leak a lot about the file contents. Can we achieve this? The answer is yes, we have the technology. How do we do this? We do the same framework that we saw before. We take a window of bytes and we compute a polynomial, this time using the bytes as a coefficient, as coefficients. Concretely speaking, you take the bytes, or actually some mapping of the bytes into some field where your polynomial lives, and then you compute the polynomial using these bytes as coefficients. Then you can see that this provides the rolling property, because it is sufficient to, if you want to, say, remove b3 and add bn plus 1, to just multiply the polynomial by x, and then remove the higher term coefficient, and then add the new byte as the constant term. And this will result in a new polynomial, which is very efficient to compute and corresponds to the window just adjacent to it. Okay, now we take this polynomial and we evaluate it as secret point alpha. Alpha is going to then be part of our secret key. Then, instead of using the result of the evaluation, we pass this through a PRF. So the PRF has a key k. This is also going to be part of our secret chunking key. And then we compute the predicate over the result of the PRF. Now, intuitively, because it's the result of a PRF, it has some pseudo-randomness property, which gives us the property that we want, that it's indistinguishable from a Bernoulli. But the first part, actually, so all of these we can prove secure according to our definition, but the first part you might recognize as essentially being just a universal hash function. And this gives us a way to generalize this. We can just replace the first part with a universal hash function, right? So now we have the key for the universal hash function and the key for our PRF as our chunking key. But this is good news. So because we actually can prove, and we prove in a paper, that RESTich KCDC is actually not a secure KCDC, but it is a universal hash function. And this is great because it's good to recycle, especially furniture. So what we can do is we can just apply a PRF, say AS, on top of the RESTich KCDC, and we get, well, we do get a slowdown, but at least it's secure. Now, this leads me to a final discussion. So it does incur a 1.5 times to 2 times slowdown. So this is not great, but is this actually necessary to prevent fingerprinting? To answer this question, let me go back a little bit from a slide that we saw before on the attack on RESTich KCDC. And I said here, if we have enough chunks, so if we have exact knowledge about the chunks, we can recover the polynomial P. But sometimes there are some processes, for example, encryption, for example, padding, that does not give us complete information about the chunk boundaries. So if we look at the KCDC scheme, yes, it's broken, right? But a little bit outside of it, we have some noise. So our attack, for RESTich in particular, requires very certain knowledge, very specific knowledge about the chunk boundaries. And if we don't have that, this actually kind of breaks our attack. So let's look at the chunk here again. The question is, what did we break? Did we break the KCDC scheme, or did we fingerprint across the whole backup system? Well, the good news for us is that actually our attack on the KCDC scheme actually extends to some of the backup systems. For example, Tarsnap, RESTich, and Borg. For some of them, actually, the compression or the padding is so aggressive that we can't actually break it in this way. And we can't fingerprint files when we look at the entire backup system. So this leads me to sort of an open question. So we know that padding towards some of our attacks in practice, not all of them. So in some cases, this may be a sufficient requirement, maybe a sufficient mitigation toward all attacks under some condition. However, the problem is that we cannot capture this in our security model. Our security model concerns only the KCDC scheme. So here's an open question for you all. Can we come up with a security model that captures the security of a backup system as a whole, that includes encryption, chunking, compression, padding, deduplication, but at the same time still allows for efficient deduplication with efficient construction? And what I mean by this is that it's very clear that if you do fixed size chunking, you can leak very, very little, but at the same time, as Matteo showed earlier, this is not very efficient for deduplication. I'll conclude with a last open question for the community. Does anybody want some empty cardboard boxes for free? Thank you.
We have time for a question or two.
Can you say more on the threat model? Because when you say like the adversary can download the file and do the chunking itself, are you considering all the files adversary is confused with will be the same size? Because definitely adversary can know whether a particular file a user has just by looking at the size of the file. For example, a particular file is 100 gigabyte, then adversary knows even whatever chunking you use.
Yeah. So our threat model for fingerprinting is maybe outside of like some of the traditional threat models. We assume that we know for certain that a file is in backup. So something like, I don't know, let's say that you're backing up your entire system, maybe some system libraries, something that we can use to like instantiate our attack. And then after we have instantiated the attack, we can fingerprint other arbitrary files. So we can take a big set of target files that we're interested in checking, is this file in the backup or not, chunk all of these interesting files, and then compare them with the chunks that we see in your backup.
So these interesting file has to be similar size, right? Otherwise, it's a trivial attack that, okay, if your one file is way too big.
Right. So for some backup system, yes, there would be a trivial attack. For some others, when you look at the chunk storage, you don't see file boundaries exactly. So like you can see a lot of chunks.
Oh, yeah. Okay.
But then like chunking actually helps you protect against exactly this kind of trivial attack where you can just look at the total size.
But the timing channel will leak the boundary, right? If you are interacting with the particular file only.
Second.
The timing channel, or you are saying only the backup.
Yeah,
so it's like, okay.
Timing channel to leak. Yeah, so there are a lot of subtleties in how much can we infer from just seeing the chunk, and how much can we infer from seeing the total size, like summing up the chunks.
So have you looked into if something can be done for the file to hide the file sizes, something similar to this?
Like
by padding, like by randomized padding or something?
Yeah, I think some padding scheme can help. But this is like, since our model couldn't capture this, so we don't have an official recommendation on how to fix this. Like we think that padding things with some efficient padding scheme like PADME would help, but only in the presence of a strong chunking algorithm.
Okay, thank you.
We'll take one more question.
Yeah. So when you consider the storage system with modifications to files, it seems like fixed length chunking as a baseline leaks some information about this part of the file was changed, this part of the file wasn't changed. Does content-based chunking, even with the use of a secret key, amplify that attack?
So yeah, I think this is another bigger issue. So the presence of the duplication itself is another side channel. And so our analysis is very orthogonal to this. We decided to focus on the sizes of the chunks. But yeah, like a wider model would also need to capture all of the duplication and the time-based access pattern. This makes for a very complicated model, becomes pretty unwidely.
Yeah, this is essentially the open question that we have here, right? Really, can you capture everything about the system, like a backup system? We found it a little bit like there are a lot of difficulties in doing this, but we can discuss also offline if you want.
So something that we are sure about is that efficient deduplication comes at odds with security. So if you always deduplicate when you have the same chunk, then you will leak something to the adversary. And not deduplicating comes at a storage cost. So that's a trade-off.
Okay, let's thank our speakers again. And then please hold for an announcement from Nigel.
And as for the last 13 years, we're going to have lightning talks at the end of the next session. Now, if you haven't been here before, this is how, or if you have been here before and you've got like a memory, like a sieve, this is how it's going to work. You queue up that end, that side of the stage, and I will call you up. If only one person wants to give a lightning talk, they get 30 minutes.
Okay, we're going to get started in a minute or two, so please take your seats. I don't know. Okay, we are officially running 5 minutes behind schedule, but I think it's time we started this session on financial cryptography. We have 2 talks in this session. The first talk is an invited talk, and I'm delighted to welcome Petriccioni Silvia, and he is going to talk about what would it take to operationalize UTXO-based settlement for central bank digital currency. So over to you, Silvio. Thank you. Please.
Yeah, ladies and gentlemen, hello. Can you hear me well? Yeah. So, thanks a lot for inviting us here to the organizers. It's really fantastic to be talking to the cryptographer community. Now, here comes the declaration. I myself, I'm not a cryptographer. Actually, physicist by training, finance in the background as well. But I work on a topic that I think should be relating even much more in talking to the actual academic research community of cryptographers, because I work on central bank digital currency for the Deutsche Bundesbank. And of course, here comes the usual disclaimer, which is that whatever I say here, I mostly here express really my own thoughts, and this is not necessarily related to the views of Bundesbank. Yet I know many of you are currently very curious about hearing, well, CBDC, digital euro, where's that all about? So here comes the one and only slide on digital euro, actually, where this all stands. Essentially, there has been a 2-year investigation phase in which there were the initial concepts defined, in which the ECB put very clear what kind of design more or less they have in mind. There was initial technological exploration, and then a design proposal was made. And now we are looking at the current phase, which is a preparation phase, where basically the scheme rule book is being written together with banks. There's a selection of service providers, and there's learning by experimentation and a deep dive again into technological aspects. And that also includes, in particular, offline digital euro system, which essentially is meant to work by really settling offline wherever you are. You would be able to settle by having a counterparty that as well carries an offline digital euro. Then the next phase will be the preparation for the decision that could potentially result in a rollout. Now, of course, I have to here emphasize, like, the decision whether or not digital euro will be issued will really follow the legislative process. And even after only that has been approved, the ECB will make a decision. So really, at the moment, all of it is just studies. Now, today's talk is not about the digital euro, but rather it is really about a question which is part of some exploratory work, and I like to emphasize here really this is independent exploration work, independent in the sense that you should not walk out here and say, hey, I've seen a central banker talk about UTXO, so UTXO for sure it is. No, I think rather you should understand there's a very broad landscape of potential solutions. And it would be quite negligent not to go in depth into those various possible options and try to understand them all at a certain level of depth. What are the implications? And that's exactly the kind of exploration work that I've been involved on together with a couple of other people of my team. So the question that we asked was, well, what would be the key issues that you run into if you were to emit digital currency? And if you were to just take a relatively mature data model of tokens that we currently, well, most of you are familiar with, I would assume, which is UTXO, which is secured by cryptographic primitives. So if you use this as the basics of a currency, and you just look at the entire regulatory and institutional framework of a central bank that you have to fit, how good of a fit is that? And where are the things that you haven't really thought about yet? And so surprisingly, there are actually quite a number of these things. And so I thought actually, maybe a really good idea is to show you the questions that we ran into without necessarily being able to reveal everything about solution attempts we've done. And I can also tell you we've stumbled also a lot, of course. This is normal, but in some sense, it felt surprisingly new what we ran into. And so that's part of my talk, to basically bring you up to speed exactly on that. So my hope is that this inspires a bit of thinking in the community, a bit of research. And if any one of you thinks, oh, this is all trivial, I know what the solution is, then please step forward. We would love to hear from you. Yeah, so this is really, I'm here in an attempt also to reach out to the community, to have more debate, to be more open than central banks have usually been towards the cryptography community, as far as I can, of course, within my capacities. And so UTXO, just to recap where this essentially would go, imagine you represent monetary values as a triple, where the one part is how much money it is, so that's the value that you have there. Then the second part is an encumbrance. It's a commitment to an unlock condition. So in this case, that could be, for example, in a system that you build very easily, a hash of a public key. And if there's a signature that corresponds to somebody having the private key to that public key, then you're fine spending that. And then in order to make sure that you're not having two 10 monetary value bills on the same hash of the same public key, so a collision of identical things on the same address, you augment this by having a different serial number of each of those. So in that way, you get rid of the problem that you might have otherwise, just yet another assignment to the same address, same amount of value, and now this collides. No, you want this all to be unique. So those three things together, I call this serial number, but there are many ways to construct this. Could be a provenance, could be like this in blockchains, an indicator where in the blockchain and which transaction is which leg you got this payment from. It just needs to be unique. It must be something that doesn't collide. And when you then look at this, that's basically how you would receive money. And any money that you received and haven't spent yet, that is counted as money that you can spend. And so you're basically almost in an analogy to cash. You carry a certain number of digital bills here with you, which you now can join into a single transaction where you're spending those and you get some money in the one leg maybe to pay someone, the other leg maybe as a return funds to you. Those are the outputs of a transaction. So in order to make that transaction go through, all you do is really you need to sign accordingly all the inputs. That shows that you have seen the entire transaction. You give your signature of it for every input you sign over the whole transaction. And then that means you authorize that spending. And now the system is supposed to check that here the value of all inputs sum up to the same as the values of all outputs. So you're neither creating nor destroying money. And now you can declare those new outputs as valid money, and those previous inputs get invalidated. They're no longer unspent. So that's how the system works. And I think many of you have seen this quite alive in Bitcoin and working for many years. So it's something that has stood a bit of the test of time, and we'll get to the idea of maturity of technology in a moment as well. But that is something that central bankers really do care about. So why could this data model maybe make sense for a digital currency, at least at first glance? Why is that interesting? Well, there's one aspect that I find really quite appealing about UTXO, and actually what seems a sideshow is no longer a sideshow when you look at the massive scaling needs that you may encounter in CBDC. Nobody knows how big the adoption will be in the end, and it may be that the adoption will not be so big, and that's fine. But if you were to imagine that just every person in Europe would, on average, adopt central bank digital currency sufficiently to make one payment a day over a 24-hour interval, then you're already looking at throughputs of the 3,000-ish per second. And of course, we know that was highly optimistic to say that's uniform over the day. And if we were to enter a world of micropayments and heavy adoption, then you need to scale like crazy, and you may have even peak events that go far beyond anyone's imagination. So really being able to scale if needed later on is a very important design decision to already have in mind today. And that's where UTXO helps, because you have those immutable objects that have a finite lifetime, and about them there's very little contention, so you don't run into any kind of issues that, for instance, accounts can run into, that some accounts run hot, there's lock contention, stuff like this. The second point is that you have higher privacy, especially when you combine this with further privacy-enhancing technologies, because you already start with a one-to-many relationship between users and addresses. We know very well that this is not enough to prevent any type of potential identification of what goes on in a payment system, but we do know that this is definitely better than having a one-to-one relationship already to start with, and there are far more ways how you can add protection. And finally, you can also implement very flexible spending authorization models and interoperability models with other systems if you're based on a token, and that's really what we think makes it appealing, at least at first glance. Now, this is something that actually has been thought about as well on the other side of the Atlantic Ocean. So MIT Media Lab, the Digital Currency Initiative, has worked out open CBDC and open source central bank digital currency, together with Boston Fed initially, and now also together with others. And they were able to demonstrate, look, you can easily scale like crazy, because as a central bank, you are a trusted central party. So take all the gains of centralization and apply it, and then you can scale like a UTXO settler to like 1.7 million transactions per second. They've also shown that you can reduce what is saved in data by the central ledger to being just commitments about unspent tokens. And so there's very little data actually retained at the central ledger if you want. Now that, of course, can raise concerns, and especially in central bank fields, people would worry, well, then I don't know anymore how many liabilities I've given out there, I've issued to the world. Well, there's the cool thing. So in an extension, they've also shown that basically using homomorphic encryption and ZK proofs, you can actually still add auditability and show that the entire monetary reserve the monetary supply has not been changed, has not been tampered with. And you can do Giro replicated deployment quite well, work with low latency. So what's the catch of all this, right? Looks like a system that we should be interested in, but what could be issues we run into? So what does it really take to make this an even remotely operational system? Now here comes the truth of central bank world. And there you'll see there are a few catches that really one needs to think about quite heavily. Well, the number one is, well, this is not going to be a blockchain, or at least not a publicly accessible ledger. For privacy reasons, yes, that's number one. But also even just thinking about throughput, if you look at a system that made on that other page 1.7 million transactions per second throughput, this is not something where you can propagate block updates to the whole world out there. And of course, latency are other issues as well. So there are many reasons to think about this as a system that more works like a database. And again, when you look what you are a central bank. What are you issuing? You're issuing a currency. What sense would that currency make if you were not a trusted party? It's really, by definition, people would only want to hold your currency, I would assume, if they trust your institution. But then that means you're operating in a space where there exists one trusted institution. And that's exactly where, again, this shifts the whole thing more and more away from operating in a BFT setting where everybody distrusts mutually each other, where incentives are not aligned. And of course, brings gains of centralization, brings, of course, also the issues that come with it, we all know. So now the second part that will be different from what we've seen in permissionless blockchains is a very important one, which is if you just were to build a digital currency with no measures taken whatsoever, how much of it can be used by citizens, then actually we would be basically one swipe away from financial meltdown. So it would actually be sufficient for everyone just to move the bank deposit holdings into digital currency to create the next big financial crisis, because we all do know that in a bank run in the real world, when you go to the ATM and you take everything out, if everybody were to do that, there's going to be a problem. We've seen this last time, 2008, where more than 90% of the damages came not from subprime, but came because everybody was panicking and trying to take money out of an already stressed system. And so that would get even much easier with a CBDC. And so basically the only way to say, well, we haven't built a bug into the system that allows us to kill our current financial intermediation is really you need to have holding limits. You cannot allow for unlimited holdings of millions and millions of digital currency units per individual. And as you will see, this induces a lot of changes relative to the previous landscape that you see, for instance, in crypto in similar UTXO systems. Now, of course, if you cannot have a lot of money in your wallet all the time up front, then it gets very unpleasant to use because you run empty all the time. And that has been recognized. And so there has been a very nice wish by policymakers. Well, why don't we make it like this? When your wallet runs empty, your wallet immediately, if you have decided to link your bank account to it, then your wallet has the freedom to knock at your commercial bank account and say, well, can you please fund the rest of that transaction as well? We call that a reverse waterfall because the money is being drawn from that bank account. And it's exactly the opposite what will happen on the other end, which is imagine you have reached already the limit of your wallet, the capacity is 100%, and now you have 100 euros more coming, then they will fall like in a waterfall into a commercial bank account. They will not stick in your wallet. And so what this means is that excess holdings must convert near instantly into commercial bank money. And that creates extremely complex high-frequency funding and defunding scenarios with a lot of implications. The level of latencies that you can accept is another dimension that is very different, time to finality as well. So we're talking about latencies of milliseconds, hundreds of milliseconds maybe, but not of minutes until you reach finality like the block times in Bitcoin or other slower consensus systems. And then you need to comply with what is the law. This is really a big issue. You need to comply with what is the law, for example, on anti-money laundering. You need to comply also with how you need to measure intermediary liquidity, and that turns out to be not so easy because end of day, there comes one moment where you need to make a snapshot consistently of all your maybe 5,000, 8,000 intermediaries, however, how many you have. And you need to know of each of them how much they hold in their funding wallets out of which they provide funds to end users. That must be consistent. Well, it's difficult when they all run on different systems, have different clocks. You're not going to get a consistent snapshot that way, so you need to think about it in some other way. And all of this you need to manage while only looking at mature technologies, because you can, unlike some more recent trends, even now in rocket deployment, you cannot afford to just fail fast and fail often. This is really something you cannot do this. You need to be absolutely reliable, which brings with it a great hesitation for relatively recent, new, and maybe not yet so well tested things that have not yet stood for a long time the test of time. That's kind of the setting in which you operate. So now that said, I can basically rush through the building of a UTXO settlement engine because this is the easy part. That's the good news. Essentially, the way you do this is you have the settlement logic, and all you do is you write a small little stateless processor that exactly implements that settlement logic on top of a distributed database that can support G-replication, like we found those that come from the spanner paper idea. They tended to go quite well. And so take a distributed key value store, for instance, as an experimentation thing that's open source. You might want to take something like TiKV, but there are many other options. And put those stateless processors on top, run it. within a couple of days, you're running and see 30,000 transactions per second. And that should be enough for you to have solved that part of the problem, because that's really the easy part. Now, here's the hard part. We used to think always about wallets in the context how they have been in crypto, where there was, of course, this consensus object, the state of UTXOs shared by everyone, because everybody sees the full history, sees the entire chain. Now, if you don't see it, wow, even just a simple payment actually becomes complicated. Because yeah, the payer wallet could reach out to settlement via any kind of communication you want to design that would be just a normal, imagine a REST API call or something of this kind. Fine, so you can submit your payment and that's going to work. But you know what's really difficult? For the recipient of the payment who has a one-time address in UTXO, for the recipient of the payment to even get a notification, hey, you got paid. How does that work? It's no longer that all the wallets keep looking at one of the same big object, keep browsing what are the newly added transactions block by block. But rather you're looking here at a fire hose output of like some 10,000s of transactions per second that you need to somehow channel in hopefully less than maybe 200 milliseconds into the right ones out of 500 million wallets that are out there in total. And I think that already tells you that there's a real problem just by scale, by magnitude. But then when you start thinking about it even more, well, how do you know where this needs to go? And here comes the privacy issue, which is, I mean, the payee wallet could, of course, disclose, hey, I am serving the following set of addresses. But if we were to disclose this, then we already kill privacy right away there, right? So you can't really have this type of easy disclosure. And so finding a suitable communication structure for this kind of systems is something that, even looking quite a bit into the issue, we found far less trivial than we thought it would be. And you know, the risk when something's complicated is that if you don't have a solution, you resort to the solution what's in place today. And really, please, let's not have this, because what do we do today? We have a big code that says that's the bank where we have the money. You know, no, we can do better than this, right? You don't want to submit a UTXO with a big code. But then there are either quite complex objects. You need either to come up with a privacy-preserving routing network that somehow, with advanced ways of using Bloom filters, onion routing, and so on, can scale to more than 10 billion addresses and yet be quick and efficient and secure. Or you do what we more experimented with just for the lack of skill of looking at number one, which looked more appealing, but you know, which was, we've looked at what would happen if you provide a DID directory where essentially you can find out to which intermediary you would have to talk, who then knows how to further route towards wallets. Of course, this costs you a bit of privacy because now you know that this address already belongs to somebody who has an account with BNP Paribas. Yeah, it's no longer, couldn't be anyone. It's already a reduced set. But if the bank's big enough, you know, there's still a bit of something. But we don't like that solution very much, and more ideas are highly welcome. Oh, typo. Yeah. And then here comes another example of an issue you run into. So each wallet should not hold more than X units of digital currency at any given point in time. Now you can solve this either the ignorant way. You can say, well, you know, we don't have a better idea how to solve it, so we just find a trusted third party, and then you probably would look at an intermediary, and you would say that a trusted third party will control the wallets that they are never having more than X in holdings. But you know, I'm having a headache with this, not just because I like the idea of having systems that can also work in a trustless setting, which I think is very valuable. But also, additionally, from the economic side, you can imagine intermediaries may have very wrong incentives when it comes to innovation. And so that's kind of a thing I would like to not have. I would like to think of a protocol that's cryptographic and that thinks about how you prove that an inventory of tokens that you're holding, in some of it, stays below the holding limit. And of course, that inventory, you've counted them all. So, and that's the more complicated part, because essentially every transformation of that inventory, as you receive, as you spend something, must prove that you've done a valid transformation of that inventory. And you should break your head about, am I maybe inadvertently still leaking some additional information, especially at the very beginning when my inventory is empty? And so we've tried there are a few things, but I'd love to talk to people. I'm pretty sure this is a solvable problem, but for us it was surprisingly a lot of thinking for not getting as far as we wanted, but put Myrtle trees and put homomorphic encryption in there, ZK, and still you discover, well, you will be troubled with latencies and also troubled with colleagues who say, but there are some ZK things that we don't trust yet fully. So challenge to the cryptography community, just moving the problem out there into the daylight. Maybe we hear suggestions from you, I don't know. Just as a sideshow, and that one very quick, intermediary wallets become also a totally different thing of any wallets we've ever seen. I'm pretty sure even Binance has a super slow frequency of payments out of their wallets compared to what we're looking at there, with thousands of transactions possibly coming out of one single intermediary per second. And so, of course, if you have there the issues of token selection and denomination management, if you solve this poorly, then your return money are always to little cents, and at some point you drown in cents. So we're also working on issues that are unrelated to cryptography, but just have to do with the idea of finding a provably correct, smart token selection way that is also highly parallel and that's able to just sustain a decent wallet management such that the system behaves well on those very crucial parts, just for mention and completeness. And here I come to my very last point. And the last point is the one where I remain the most fuzzy because I think it's the biggest topic. This is like an elephant. I think we all know that this is an elephant, and I think it would be great to just start a discussion about how to address the elephant. So the elephant is the following. As from the economic side, the problem is pretty simple. As you move the speed of these systems to be final in settlement within a second, this becomes actually a perfect vehicle for fraud. And we've seen this happen, especially in Brazil when they introduced the real-time payment system, but also in many other cases, that exactly because money can move at such fast speed, basically fraud becomes pervasive. There will be some ways of fraud, how people get frauded into making some transfers. There may be some kind of malware, all kind of things can happen. And because that money moves that fast and irrevocably, at some point, you risk completely losing control and reputation. So for that reason, being able to have ideas about how to handle fraud is just as important as being able to have ideas about how to preserve here privacy. And so with fraud, we have the difficulty that it's a little bit like a Heisenberg principle of fraud and also money laundering, which is the patterns that represent fraud. They tend to change quickly and continuously because every time you crack down on one, of course, that's exactly the pattern that will be avoided next in the future. So for that reason, there's not too much in public data sources and very little in published academic research on money laundering in comparison to other fields when I look at this, just because you really have not that rich of durable information on what are the exact things that tend to work. But now if you try to think, well, how can I then design something that gives you, on the one hand, privacy, on the other hand, sufficient leeway to eventually respond to potentially dangerous issues of fraud, then this really becomes a problem that, is just immense. So an example is very often you find that in systems like this, global properties, like for instance, graph centrality measures, are very good predictors of certain types of fraud, because a player that is receiving from the whole world lots of things might be somebody up to something. Yeah? But at the same time, in order to see that global picture, you need to unite the data from the various different silos. And that's exactly what you would like to not do, right, under privacy perspective. And so, of course, we're very aware about secure multi-party computation methods that have been devised. And of course, we're aware that for machine learning, there are ways to do federated learning first and build a combined model out of it. But it's exactly the problem of not being sure about what is going to be the right type of models that need to live in this setting that makes it really challenging to even come to the cryptographic community and say, this is the kind of thing we would exactly need, because it may happen that today that's what we need, and tomorrow, oops, we discover that we were discovered. And so I think everybody who works in this field and starts developing ideas and looks into it will greatly contribute to making this a more manageable aspect. I find it very hard. And with that, I thank you very much. And please feel free to reach out to me if you want to be in contact. We'd love to be in contact with the community.
Thank you, Silvio. Let's give Silvio a round of applause. Thank you.
Thank you.
We have just a few seconds left for questions, so please keep your questions brief and to the point.
Thank you for the talk. So the premise of UTXO you presented was that you cannot create and destroy money. And there is a very easy way to destroy money, which is forgetting the private key. So how do you solve that problem? Yeah.
That's an excellent question. I think in 20 seconds, I will not be able to respond that quickly. Let's take that into the next coffee break.
So there's an assumption here that you can make a payment without the recipient of the payment acknowledging the payment. And that seems to add a huge amount of complexity. There's older techniques like blind sign tokens that don't make that assumption and are much simpler. And certain cryptocurrency things don't make that assumption either, but it's pretty rare.
I agree. I think if you had on the recipient side a politician who received $1 million without knowing, maybe that's exactly the kind of scenarios you try to avoid.
Yeah. Okay, I'm going to stop the questioning there. Sorry, we're out of time. I'm sure Silvio will be around and very happy to take your questions over lunch or in the next session. Thank you very much once again for the great talk. I really appreciate it. We'll move on now with the next speaker. And the next speaker is Antigone Polychroniadou, and she's going to be talking about Atlas X equity financing. I'm fascinated to find out what that is. So let's welcome Antigone to the stage.
Thank you, Kenny. Today I'm going to talk about Atlas X, which is a product we have developed at JP Morgan. First, I'm going to introduce some financial terms to understand the use case. Then I'm going to talk about the challenges for the solution. Then I will only skim like super high level of the solution. And then I'll conclude with some experiments. So first, some financial terms. So when we say that the market is bullish, it means that the stock prices are going up. Investors invest a lot. And in general, there are positive news in the market. On the other side, we have the bearish market. When the prices are falling down, then there's not a lot of trading activity, and there are bad news and we have weak economy. So the best strategy that you can do when we are in a bullish market is what is long exposure. Okay, so what do you do here? You borrow some cash, you buy a stock, and then you keep it because you hope that the price will increase more, and then you will get more money, okay? Then you can also make money when the prices are going down, and this is what is called short exposure, okay? So here, what you can do, you can borrow an asset, then sell it, and then repurchase it again when the price is going down, okay? So you are betting that the price of a stock will go down. Let me give an example here. So let's say you want to buy Tesla stock. So let's say you borrow Tesla when it is, I don't know, at $250. Okay, so you borrow it, you sell it at $250, and then you buy it back when it is $200. Okay, so you made actually $50 per share. So that's how this strategy works, okay? It's a little bit convoluted, but that's how this strategy works. And now if you want to either get a long exposure or a short exposure, you go to a brokerage, and JP Morgan is one of them. And ideally, what you would like to do, you would like to have the same long and short exposure, because if we go back, you have to borrow cash or borrow the assets. So you need to have like funding rate and borrowing rate. So you need to account for all of this. So if I can equate them, I don't have to bear these costs, okay? So I reduce the risk. And this is what is called internalization. I have an example here. So let's say we have stock A from different desks. It's not important for the talk to understand what desks these trades come from. And let's say we have 300 shares for long and 100 shares for short, okay? So we can actually match 100 and we are left with 200, okay? And then another match we can do here, we have 300 long and 300 short, we can completely match them, okay? So we have 0 left. And here I have like the summary. For example, we can really like match all of these quantities, but we are still left with some net difference, okay? So internalization is great when we want to actually reduce our risk and not go outside of the market. So if somebody comes to us and says, I want to buy the stocks, we need to go find them, right? But if we can equalize the long and short, we don't have to do that, okay? So this is the benefit of internalization, but we still have some left, okay? We would really like to equalize our long and short exposure. And usually how you can do that, as I said earlier, I hinted earlier, you can go actually to another bank, buy the shares and sell them, okay? So you need to go find them and you pay a fee. But if we still keep doing this internally, so we don't have to go to the market or to another bank, as I have it here, so we find the client that they want to do what we want them to do so that we equalize our long and short exposures, we don't pay any fee, okay? So what do we want? So this list that I had here, what we have left, how all brokerages are doing it now, they publish this list to their clients. And clients here are hedge funds, okay? They're big companies. So they publish this list. And then the client sees from this list what we have, and they come and trade against it, okay? And we hope that from this list, we will be able to internalize more, okay? So ideally, what we want to publish this list, and we do actually, and then the clients come and trade. However, there was a big concern and multiple clients came to us and complained. So if a stock is maintained by usually one client, it's called concentrated client. If more than 50% of a stock belongs to a single client, then they have these concerns that even if this aggregation is between multiple clients, as you see here, and here I have that client A has more than 50% of this stock, and stock B, another client has more than 50%. From leakage and also from regulatory requirements, you're supposed to reveal some information. So they're saying even if this list is anonymous, you can still reveal our trading activity with you. So we want you to remove our positions with us, okay? So if we remove this, then we cannot really achieve this internalization and we have higher risk, okay? And just to give the problem in a more generic way here, so think that we have here 30 days, and now we have like the aggregated positions, they're moving like this in 30 days, okay? So here minus is for sell, okay? So here you're selling, here you are actually buying, so this is the plot that we have. And we have a concentrated client, and this concentrated client holds most of this position. So you see that the green line really follows the blue line, okay? So they go together. So we want to hide this information. If a client is concentrated, we want to hide his trading activity. We don't want to show that he's actually the big holder of the stock, okay? And in general, if you think about it, so this is about buying and selling. So if you didn't understand my introduction, think that we want to buy and sell and we want to match that, okay? Think like that. And there are a bunch of techniques that we can use. The main one that comes to the head is secure multi-party computation. So we can hide what we want to actually offer and also what they want to do. They also encrypt it and then we can match it. And this is actually exactly what we did. We have another product called Prime Match, which is exactly this. So we have the bank's inventory and the client's inventory and we want to match it. And for example, here, I have this example, the client wants to go short 100 and the bank has for long 800, so we can match 100. And nobody knows anything else about the 100, okay? We will not know that at the end of the day, the bank is left with 700, okay? So you could think, okay, let's apply this to this problem. And this is how they came to me, because they knew about the primates and they wanted to apply primates to this use case. But actually, this use case is much simpler. So you don't need to hide all the information. And I have the analogy here with differential privacy. So with differential privacy, you are only hiding a specific information about your data. For example, here I have this picture. So you don't want to hide how many people are in the room, but you want to hide their nationality. Okay, so that's why I made the pixels like that. So the solution that we're going to go for here is differential privacy, because as I said earlier, we want to hide the trading activity of the concentrated client, okay? So whether we have the positions of this concentrated client in the dataset or not, we should not be able to distinguish, and this is what you can get with differential privacy. And differential privacy is used actually a lot from a lot of different businesses. For example, Google is using it for federated learning. Wikipedia and other companies, they use it for telemetry purposes. Microsoft is using it for synthetic data. Actually, differential privacy and synthetic data is a big thing. Apple is using it to find the most popular emojis. I don't know why. And here, what we're going to do, we are applying differential privacy in the finance, okay? For the first time. And as I said earlier, we have two lists. We're going to remove, if you want to remove the client who holds most of these positions, you want to be able to not distinguish whether we keep these positions of the client or not, okay? And we are adding noise. So I'm gonna talk about the first big challenge here. The first big challenge is that this is a time series data. We publish them every day, okay? So if you keep adding noise and adding noise, okay, if you don't add it in a smart way, you're going to destroy all the utility of the data set, okay? At the end of the day, you will destroy all the utility. So this is the big challenge. So we had to come up with a new algorithm that also incorporate this continual observation of the data. And as I'm saying here, this is running live for 2 years now in Asia, Europe, and United States. It's $1 billion business. And then, as I said, we have this new algorithm. And again, so the important thing here was that when you use differential privacy, you need to actually talk, what is the utility, okay? What do we care to maintain while we're adding this noise? And we had to talk with the business, what do they think would be the right metric for that? And I'm gonna talk about the right metrics here that we discussed with the business. And given the solution, so we have maintained our clients, so they don't want now to remove their positions from this inventory. And also we give better pricing because we don't need to go to the markets to fill the orders, okay? So I'm gonna talk about more challenges now for the solution. As I said earlier, you need to decide what is the metric to use. So there's this epsilon parameter in differential privacy, which tells you how much utility you can get. So the higher the epsilon, the less noise that you're adding, and you want to maintain the utility. So you want to balance the two. And also to use differential privacy, there's another big issue here. You need to have a lot of data to use differential privacy. For example, after this, they also came to me to apply differential privacy for other use cases, but they didn't have a lot of data. So it's really important to have a lot of data. That's something that needs to be taken into account. And here, fortunately, we had a lot of data. And the metric that we are using here is something which is called privacy and loss. It's called P&L. So earlier I told you that you need to borrow the asset or borrow the cash to buy or sell. So you need to pay rates, okay, if you borrow money, of course. If you don't have the money and you borrow them, you need to pay rates. So I'm not gonna give you the equation of this P&L, but think that it depends on the borrowing fee and on the funding fee, okay? So we need to find an epsilon value for the differential privacy that has an acceptable P&L, that we're not losing money, okay? And also, we're also measuring the leakage probability. What is the probability when you're looking the time series to tell that the data of a concentrated client is there, okay? And also, to find out the right value of epsilon when we start the product, we needed to use historical data and go over them, like do a lot of experiments to find out what will be the right values of epsilon. I'm gonna talk briefly about this at the end. And there are even more challenges. For example, how do you set the sensitivity of the differential privacy? So we were able to do that. It's important to not make the sensitivity of the differential privacy depend on the data. So we were also able to do that. And then here I have an example of how the obfuscation looks like. What I call obfuscation is when we add the noise with differential privacy. So the blue line is the actual true data that we publish every day. The green one is the concentrated client. So you really see that the concentrated client holds some of most of this position because he really like drives this stock, okay? And now you can see with the orange one is after we add obfuscation. Okay, so you know in differential privacy, you need to have these spikes here, okay? So here is the number of shares and here is the timeline. We publish it every day. This is for 1 year, I think, yeah. So you see we have these spikes here, okay? And at the beginning, they were telling me, we don't want these spikes there. I mean, you cannot achieve differential privacy if you don't have the spikes there. So that was the big argument I had with them. And at the end, what we did, we calculated the P&L at those points, because imagine that we are saying that, let's say we only have 20 shares of Apple, and because of differential privacy, we are showing 1 million shares of Apple, okay, which we don't have. And they will see that, and they will come to ask for this 1 million shares, and we will not have them, okay? So that's what happens in the spikes. So we calculated how much would be our P&L for these cases, and based on what was acceptable for them, we decided on the parameters of the differential privacy, okay? And then the system integration here, to be honest, it was not very hard because differential privacy code and all of that, I mean, compared to secure multi-part computation, it's very simple. And then for regulations, we had to explain to them that what we are showing to the clients is not really what we have, because we're adding the noise here. So it was very weird for them, like, why do you publish this if you don't have it? And then we had to explain that this is the methodology and all of that, because you need to report to the regulators how much you have. And they were seeing actually the difference. At the beginning, when we launched the product, we had the problem, because they were saying, why you don't publish what you have? And we managed actually to tell them about the solution, and now they are okay with it. And then we also have to explain to these clients that they were complaining that this is the solution, we don't reveal your positions and all of that. That was yet another problem that we had to convince them. Okay, now I'm gonna give you a super high level of the solution, and I'm hiding too many details under the carpet here. I just only want to give you the idea behind this. So the naive approach is that, let's say we have 17 days here, and every day we have some numbers that we need to keep adding every day. So this is a simple summation example. It's not like the one we have that it can go up and down. So the naive solution you can do, every day you need to publish a number, you just keep adding independent noise every day, okay? First day this triangle means noise, okay? So every day we keep adding new and new noise, okay? New independent noise. So if you do that, then the error that you will get at the end is proportional to the number of time steps that you have, okay? Where delta here is the sensitivity of the differential privacy, for those of you who understand the sensitivity. So I want to do something better, okay? This is similar to the example I was showing you with the picture that if you keep adding independent noise, you will lose all the utility. So then another thing you can do is you can have a parameter called B, which I call a window. So what you can do a little bit more smarter, you can again keep adding noise, and then when you reach a multiple of 4, you actually forget about the previous noise and you sample new noise, okay? Then again, when you go to a multiple of 4, you delete everything else, and now you have only 2 noises, okay? You can keep doing that. And then at the end of the day, you can actually bring the error to t to the 1/4, okay, which is much better than having the error depending on the number of time steps. Okay, and then we have another algorithm where you can actually bring it down to log t. I'm not going to talk about that one, but think that you have a tree structure, and now how much noise you add is only like logarithmic, okay, in the number of time steps. I will go to the experiments. I will not explain that. So for the experiments, as I said, when we wanted to launch the product, we had to decide what is the epsilon parameter of the differential privacy. So we got the previous data they had for the full year, and we ran a Monte Carlo simulation in the following sense. So at the beginning, we have the historical data for 1 year, okay, and then we decided like, this is what you're supposed to publish every day, and then we added the noise and then we published it. And now, because this is a simulation to decide, right? We had to decide how much the clients are going to consume, okay? Let's say they are consuming 15%. Then we are removing the 15%, and here is what we left, and this keeps going on. So this is how we did our simulation, to simulate 1 year of this product, how it would go, and to decide what parameters to put for the differential privacy. This is how we did it. Here first, I have an example on synthetic data. So you can see I have an example where a single client holds the data. So you can see with differential privacy, like how it moves. So in the short term, you are completely hiding the activity, but in the long term, you do follow the curve of the actual one. So it's important in the short term to hide the information. So these ones are based on the real data. This is the stock. Of course, I cannot say which stock it is. But again, this is the number of days, and here's the number of shares. So again, you can see the true one is the real one. The green one is the concentrated client. You see, he really moves his strategy with the real one, and the orange one is the obfuscated with the differential privacy. This is for epsilon 0.6. For 0.3, it looks like that. I'm just flashing you the plots here. This is yet another stock, and this is yet again another stock. And then here I have, for different epsilon parameters of differential privacy, how much P&L we're going to lose, okay? Because I told you this is the metric to decide on the epsilon. So the epsilon that we put in production is 0.3. And for this one, we are actually losing $1 every day per asset for that one. And here, what I plot is like the P&L difference, whether in the obfuscated data we include the concentrated client and whether we don't include it. So when we don't include the client, we are losing $4. So it's good to include the client and obfuscate, because in that case, we save $4. And the last plots I have here is the leakage probability, how much we are revealing the concentrated client activity. So if you are close to 0.5, is that it's a guess. You cannot guess whether you are buying or selling. So you really want everything to appear in the middle, to be 0.4, okay? And for different parameters of epsilon here, you can see that when you don't add a lot of noise, you're not close to 0.5, but when you add more, you see most of the stocks are in 0.5. The y-axis was the number of stocks, okay? So to conclude, so we have this Atlas X, and think of it, it obfuscates time series data, and it runs in 3 regions. And we have a new algorithm. I didn't give you the details, just the idea of it. And then I gave you some of the challenges that we had with the business. And I want to say in general that using differential privacy, we can hide some particular information about the data set instead of just using full-fledged secure multi-party computation. But also the combination of differential privacy and secure multi-party computation can be beneficial. For example, there's this case, there are a lot of papers on what is called privacy-preserving dark pools. And the most efficient solution for one server is like, is super slow, okay? You cannot really use it for production. So here we have a new work where we combine it with differential privacy and secure multi-party computation, and the running time of this one is very close to the non-private one. So this is something that combining the two, you can actually make more efficient algorithms. Okay, thank you.
Great. Thank you, Antigone. Unfortunately, we don't have time for questions. We're running late, so we'll move on to the next session. Please catch Antigone in the break or over lunch. I think it's time for me to hand over to Nigel. Nigel, welcome to the stage.
Right, so I want everyone to queue up there. And when they come off the stage, for safety reasons, go that way, yeah? Don't, God, the lights are quite bright. Oh my God, there's a gazillions of people already. We're probably down to 30 seconds of talk. Right, I left my hooter in Belgium. So someone kindly got me a swanny whistle. So at the end of every talk, I'll go, and that will be the time for them to get off. Right, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that is about, at the moment, a minute each. Right, so the first one, come up. Come on, speed, 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 speed. Go. Is it on?
Is it on?
Yeah, it's on, yeah.
Hi, everyone. My name is Nadim. I am grateful towards the IACR and RWC organizers for ensuring that this is such a great conference. However, I must raise some important issues that I believe must be addressed. Over the past 2 years, the IACR board has published commendable solidarity statements in response to global conflicts, including on Russia's unprovoked war against Ukrainians and Hamas's atrocities against Israeli civilians. But when it came to issuing a comparable statement for Arab civilian victims of Israeli aggression in Palestine and Lebanon, a statement that used the same language afforded to both Ukrainian and Israeli civilians, the board chose not to do so. An edit to the Israel statement was eventually published, but unlike all previous statements, it named no perpetrator, described no civilian harm, stood in solidarity with no one, and wasn't even specific to any victim group, instead being intentionally vague. And when over 40 IACR members petitioned for a Lebanon statement more than had ever petitioned for any other, the board rejected it. These rejections are difficult to understand given the tens of thousands of women and children who have been killed in the region. This imbalance in statements gives the IACR community the sense that some constituent groups deserve explicit recognition, while others are worthy only of a footnote. This demonstrates a pattern of real or perceived bias in the IACR, both of which are damaging to the community. You can find full documentation of this issue at iacrbias.org. I invite you to read, to speak up for consistency and conclusion, and especially to express your opinion during the vote for the next IACR board members. Thank you.
Next one.
Hi. Hello. Hi, my name is Emad. You know me from the previous talk. I co-organized an event on computing on encrypted data for many years with Nigel and Ingrid, of course. And every year this event is in Belgium, but this year it's in Stanford with Ingrid, because Ingrid is on sabbatical in Stanford. So the theme of this year is hardware acceleration for homomorphic encryption. And the date is June 26. And we have invited many industry leaders in this space, and we are going to invite companies with applications.
Come fast. Come on. Oh, denial of service attack here. Look at that.
Hi, everyone. We're just here to advertise the second edition of the Cryptographic Applications Workshop, which we're running as an affiliated event of Eurocrypt in May this year. And this is our attempt to bring a little bit more real-world cryptography to Eurocrypt. So if you're interested in cryptographic applications, please join us there.
And in case you can't make it to Madrid, we are also going to make a remote participation possible. That will be over our website. So find our workshop on the Eurocrypt website and then register for remote participation.
It's rare war crypto at Eurocrypt. Can you imagine it?
Okay, hello, my name is Lawrence. I work on a thing called Sojin-based cryptography, which is currently not very real world, but there have been some recent developments that could change that, so I wanted to point that out to you. So first, there's a new version of a signature scheme called SkiSign, which has extremely small keys and signatures for the post-quantum setting. So we're talking like 65 bytes public keys, 150 byte signatures, and verification on the scale of milliseconds. One slight downside is very slow, so, well, it just got way faster though. So check out sqisign.org if you want to learn more about that. Second, we also have now faster post-quantum commutative group actions. So if you want to check out more about that, look at ePrint 2025/401. Third, there's going to be a 3-day workshop about it in Lleida in Spain.
Hey everyone, I'm Tanya. This is Jules. We're co-founders of Tinfoil, where we're building confidential AI inference using NVIDIA's confidential compute mode that's available on their latest GPUs. We support all the large models that you know, like Llama, DeepSeek, etc. And we use like Sigstore and GitHub Actions to have transparency so you can verify our security guarantees. Last year, I was here like looking for co-founders, and I found one of them, including like 2 others, yeah.
Yeah, so if seems like everyone agrees 2 years ago that now it was fine to ship a lot of data to third parties. So if you don't like that and you want to use some AI, but you feel a bit weird about sending all your data, come talk to us. Like, we're very curious to hear your problems.
Thank you.
Thank you. Hello, everyone. I'm Silvia Mella. I work at Radboud University in the Netherlands. I actually have 4 announcements, but I will be fast. So the first one is that we have multiple open positions for PhD students and postdoc researchers. If you're interested, just come and talk to me and I can give you more details. But just to give you an idea, at the moment we have open positions on post-quantum, both on the design, implementation, and channel attacks, but also positions on hardware security, implementations, and physical attacks, and AI and security. Then we are organizing some events. So we have an affiliated event at Eurocrypt in May. It's on permutation-based cryptography. So please come if you're interested. And then Radboud, and in particular my colleague, Professor Leila Batina, is organizing 2 summer schools. Yeah. The first, I slow down. Okay. So the first is the ProAct training school. It will take place in Crete during the first week of June, and it's focused on enhancing the security of cryptographic algorithms. And the other is the school in Croatia.
Hello, everyone. My name is Zon. I'm here from the UK. Over the past decade, the UK government has steadily increased its powers of mass surveillance while restricting individuals' rights to privacy and security. This has culminated in the Online Safety Act, which requires all user-to-user platforms to detect and remove certain harmful content. As you know, this is fundamentally incompatible with end-to-end encryption. Regulators will soon force services to implement client-side scanning. UK Apple users have already lost ADP. We fear this is just the beginning. What we need are decentralized, highly scalable, widely available communication platforms that are as simple to use as WhatsApp or Signal, yet have no central individuals or entities that government can pressure. If you think such a service sounds impossible, unfortunately, I kind of agree with you. Regardless if you have ideas or you're already working on something in this area, find me around. I'd like to help connect people who can have an impact and help however I can. Thank you.
Cool. Oh, right. Yeah, cool. Don't know what I'm doing with my hands. There we go.
I will try to give you an opportunity to play it. Hello, I'm Filippo, and I'm here to tell you again about Whiteproof. Whiteproof is a collection of test vectors developed originally by Google, and it's now maintained by the community in the C2SP, the Community Cryptography Specification Project. So you already know about Whiteproof. The new thing is that we've now made it much easier to contribute new vectors to a Whiteproof. So if you have test vectors for a cool attack you've developed, for a primitive that you think doesn't have enough vectors, or if you're a cryptography implementer that is tired of maintaining vectors and just creating test vectors by yourself, bring us your test vectors. And then I'll just talk about something else until you have to play the thing.
You give 20 seconds.
20 seconds. What do you want to tell?
All right, okay. Go queue up again.
Hi, I'm Jack, and I'm here to tell you 3 relevant things about Blue Sky. 0, it's a Twitter replacement. It's great. Go join it. 1, I run the Blue Sky ePrint bot. So if you're on Blue Sky and want to consume the cryptographic fire hose or bulletin board, if that's more your style, follow eprint.bsky.social. 2, I maintain a list of people on Blue Sky that publish on ePrint. If you want to find cryptographers to follow, go to cryptography.social and click on the names there. 3, I use that list to linkify the ePrint bot posts because they include title, author names, and abstracts, and you can click on the author names to go to the profile. So if you're on Blue Sky and also publishing on ePrint, let me know. My handle is in the ePrint bot's profile.
Just to clarify that, the list of people is on cryptography.social as a website, not as a Blue Sky account. Right, yes.
Hi, my name is Aniket Kate, and I like to build multi-party computation protocols, and I really like to build them, use, and get them used in practice. But when I come to RWC regularly, I see FHE and zero knowledge getting much more attention in practice. And one of the key reasons I always come across for that is people find, oh, how can we make this non-collision assumptions? And what we started to look recently is can we do something from game theoretic, something from economic perspective towards reducing the non-collision assumptions on these protocols. So we try to do that for private information retrieval in last year Oakland. We have a paper coming up in Eurocrypt looking at threshold scheme. So the short answer is, if non-collision assumption is only something that's stopping you from using MPC in your systems, I'll be happy to talk to you to see if we can find out something interesting.
Cool. Next one. How do I do that? I got this.
Hello, everyone. I'm Jiwon Kim from the university. I'm a PhD student from the University of Michigan. I came up here to introduce my recent work about anonymous blacklisting that enables content moderation in anonymous messaging spaces, which is really important. In my work, Alpaca, we achieve constant online proving time, proof size, and verifier time. So if you are interested in my work, and if you actually want to deploy anonymous blacklisting system or anonymous messaging spaces, please come talk to me. Thank you.
Okay, before the next one comes up, can we have a round of applause for Deirdre for her permanent, I don't want to, what's a blue sky tweet called? What's a blue sky tweet? Yeah, so live commentary always, there we go.
Thank you. Hi, I'm Deirdre. I'm here to announce the workshop on computer-aided proofs of security, or CAPS, at Eurocrypt. If you have ever tried to write a cryptographic proof and you're like, this is a lot of work, don't we have computers that help me prove things like whether my proof will compile, or if I'm missing an argument, or will it ever complete? And you're going to Madrid. We have a new workshop for you, myself and Sabine and Philip Hasselwater, about what are the kind of tools out there to help me, the working cryptographer, check that my proof is not a pile of crap and have the computer help me do it. Go to caps-workshop.com for more.
Thank you.
Thank you, Deirdre. I'm doing actually not just one workshop, but 2 workshops at Eurocrypt. So I have another one to tell you about. So if you're interested in security proofs on paper, then you can come to Protex on Saturday. We're going to talk about all things security models, proofs, proof techniques for cryptography. You have a program now that's up on the website. You'll find it through the Eurocrypt website. Just search for affiliated events and then Protex. So yeah, we hope to see you at Eurocrypt in May, and come to Protex and also come to CAPS.
Hello, my name is Erin. I'd like to ask you 3 questions. First of all, do you want the cryptography community to be more diverse? Second of all, would you like to be part of a group that is helping to make that happen? And 3, do you like the south of France in June or appearing at events online? If either of these are a yes for you, then you might be interested in attending Decrypting Diversity. Check it out, decryptingdiversity.com, or come talk to me about it. Thanks.
Arctic crypt. Thank you. This is for all you procrastinators out there. I know you're in this room with us. If you want to go to Svalbard in July, you need to register by Monday. Monday, 31st of March. No, I'm not kidding. Yes, that is a hard deadline. Yes, I'm able to be strict. Thank you. Hope to see you there.
Take a bit longer, we've got a bit extra time, okay?
Okay, so my name is Kazumi Sako from Waseda University. And I'm sure many of you in this room agrees with me that zero knowledge proof is a great primitive that should be used more widely in real world. However, in order to do so, not only cryptographers, but ordinary people should understand something like zero knowledge could really happen. So that's why this is what my student created using his own 3D printer that allows elementary school students to verify something without knowing the more details about it. So this device called 9-pin counter.
Do you want me to hold it?
Thank you very much. Yeah, that's
okay.
good. This is going to be used to verify that the student can experience that the answers to Sudoku puzzles, I hope you are aware of it, is correct one without seeing all the numbers, all the numbers for the solutions. The idea behind is that there is a plate, I'm sure you can't see it, but there's something hanging out here, and this plate represents 6. That means if you slide this, okay, you have to hold it like this.
Okay, sorry.
Still, you can hold my mic.
I'll hold your mic, right? You've got about 20 seconds.
Okay.
Ah.
If this counter saw the 6 for the first time, it slides. But what happens if it sees it second time? It stops. And you do that with hiding everything. So without, if every slice, every 9 slides go through, it means, or they are all represent different numbers. And you can stop.
We need to get much more serious about treating governments as adversaries. We've seen the rise of fascism in the US and some other countries. We've seen the UK government essentially trying to limit or control the use of strong encryption in cloud storage. We've seen the UK government also target benefit claimants, and there's a proposal to surveil their bank accounts and mass surveillance. These proposals need to be resisted. Where the large companies that we work for have ties to government, could potentially be coerced to government, by government. We need to have processes in place for whistleblowing, for making sure that cryptographers are able to report cases where they might have been coerced to backdoor a protocol, backdoor an implementation safely. Thank you.
Oh, just on time. Perfect timing. Perfect timing. There you go.
Hello, everyone. I'm Mesa Janabadan from KU Leuven Kosuk. I'm announcing and inviting all of you to a summer school on PQC at the gorgeous location where you can enjoy sun sinking into Black Sea every day, almost every day, with fantastic speakers. I'm standing right outside the exit if you want to know more about it or get the glimpse of the tentative program that we have. That's it. Hope to see you there in the summer.
What was the location?
Albina, the eastern side of Bulgaria, and this is the east, and if you go straight, you'll get there.
Yeah, I suddenly thought that was no rain in Leuven then. That sounded a bit weird, right?
Hi, everyone. I'd like to have some more coffee. That was an intent. But how do I know if any of you have some coffee for me? I ask someone who knows. It's a solver. And the question is, can I communicate my intent to the solver in a way that I don't tell them what I actually want, but they can still produce a binding commitment between you and me? Well, I can tell you that FHE is not going to solve it. So if you're interested in this problem and have some ideas on how to solve it, please talk to me. Thank you.
You're just making more time for the next people, you know, coming up to the time, yeah.
Thank you. A poem by me improved with ChatGPT. Botan is an open source crypto library with security that's far from arbitrary. It's audited by the BSI, so don't be shy. It's tested thoroughly. We won't let it slide by. From IIS to Frodo, Sphinx Plus in the mix, it's packed with algorithms you can pick.
No hassle, no fuss, just dive in and try a crypto solution that'll never pass you by. So remember the name Botan, so pure, like the peony flower, secure and sure. Our work won't fade, it won't be a scam. It's built to last, not thrown in the trash can.
Beat that one.
No, I can't beat that one. At the moment, I think the chat control discussion is a little bit quiet, but it will probably come back probably this year, who knows. But at the moment, we should probably consider calling it something like chat control by Trump, because or something equally derogatory that might discourage it in the European context. Okay, that's the main thing I wanted to say. Also, if you're curious about sharding blockchains or whatever, we have this paper, Search for Elves on ePrint, and it's been running in production since 2021. So if you can break it, you can have some fun. But we have a security proof that's on ePrint now.
Hi, everyone. I'm Mark. I'm with the Ministry of Economic Affairs from the Netherlands. I know we don't do any research. This is very high end compared to what I'm working on a daily basis. I am a researcher in cryptography by background, though. I did my transition last year, and I'm now facing completely different problems, still using cryptography and making sure that the IT infrastructure for the government is also up to date and does not have as many vulnerabilities. I know that for some who might be finishing their PhDs or their postdocs or looking into doing a different change, there are so many opportunities within government to actually make a change also there to improve our IT infrastructure. So if you have any interest in that, please reach out.
Last call if anyone wants to join the end.
Hi, I'm Martin. I'm a professor at King's College London, and together with Kenny from ETH Zurich, we're running a community event at Eurocrypt to discuss if there's anything that we as a community should do, given that the geopolitical landscape is changing, given that kind of like in some countries the national landscape is changing. Does it affect us? So if you want to talk about what we are planning there, we're not there to propose solutions. We don't have a particular program we want to propose. We want to start a conversation. Is there something that we should do? Come find us. We're both here.
Last but not least.
Thank you very much, Nigel. Hello, everyone. I think most of us in this room, we agree PQC is yay and side channels is nay. Therefore, I'm very happy to announce a new tender that is provided by the company I'm affiliated with. So please go to ted.europa.eu and search for the acronym SCA for PQC if you're interested in that. The tender is open until the 5th of May 25, so 5/5/25. I think that's nice as well. My affiliation, please beware, as any lighting comes with some thunder. Some German ahead. I'm affiliated with Agentur für Innovation in der Cybersicherheit GmbH. So watch out and have a good day.
And that ends the 13th edition of the Lightning Talks. We'll see you all in Taipei. Well, I'll see you in Taipei. Thank you.
Great, thanks so much. Hi, everybody, it's good to be here. So I actually wanted to begin by dedicating the talk to my PhD supervisor, Ross Anderson. He actually passed away the week after Real World Crypto last year. So in memory of Ross, if you have a minute on your flight home, probably the best way to honor Ross would be to read some of the many great things that he wrote about real world cryptography, from his classic Why Crypto Systems Fail. Everything in his textbook, Security Engineering, is all really great reading for this community if you didn't have the chance to get to know Ross while he was with us. Thank you. Okay, so in memory of Ross, the show goes on. So I'm going to talk about randomness beacons. This is going to be kind of an overview talk. So what is a randomness beacon? The abstraction at a high level would be some service that publishes randomness that everybody can see. There's consensus on the values. Hopefully it publishes a lot of good randomness. And it should be secure against attackers. So no attacker should be able to manipulate this randomness or predict it, and nobody should be able to block this service from running. If we had that, the first thing you'd think of is that we could have cryptographically verifiable lotteries. So that's a great use case. And it's not just lotteries like this that you buy a ticket for. There's a lot of other resources that are given out randomly that are important. Everything from immigration visas to permits to hunt a moose in Vermont. So all of these could be powered by a randomness beacon, as well as a lot of cryptographic applications that we don't really think of as lotteries. Everything from randomized audits, picking parameters for crypto protocols. You can use them to generate challenges for a proof system. So there's a big variety of applications. And the point I'll stress is that ideally we could just have one randomness beacon even for the whole world, and you could drive all of these applications off of one service. So everybody in the world, for all their different purposes, could use a common source of public randomness. So the state of the art for solving this problem has barely changed for a really long time. That stone device on the left is a claritarion from ancient Greece that was used to randomly select citizens to serve in the Athenian Senate. And it kind of worked by disks randomly bouncing into a hole. Not that different from how we actually generate randomness for high-stakes lotteries today. So this talk's going to be about distributed randomness beacons, which are cryptographic protocols that try to emulate the ideal randomness beacon service. And they're going to do that by having a group of parties interact, contribute entropy, and then publish some public random output at regular intervals. And of course, hopefully it will still be secure even if some of those nodes are malicious. So the classic first thing that you would do is a commit reveal protocol. Use a cryptographic commitment scheme. Everybody picks a random value and shares the commitment. After everybody's committed, so it's too late to change your value, then everybody reveals their values. You combine them in some way, and that's the beacon output. So this works great until you have a malicious node who waits until everybody else has revealed. They can see what the output will be if they reveal. They won't be able to change their contribution because they've committed to it, but they can decline to publish if they don't like the output that's about to happen for the randomness beacon. So you kind of end up with two choices. You can have the protocol fail in that case, in which case it's difficult to manipulate the output, but it's trivial for any one node to block the whole service. Or you could restart if somebody doesn't open their commitment. And then it's trivial for anybody to manipulate the output to induce at least one bit of bias if you control one node. But the service would keep running. So neither of these options looks great. So there's a couple of ways to fix this. In fact, you can kind of look at everything in the literature basically as a patch to try to fix this last revealer attack. So if you have sort of financial capability built in, if you're working, say, in a blockchain setting, you can do a commit reveal punish protocol. So that really just adds some financial deposit. Everybody who commits a value also commits some money, and they only get that money back if they open their commitment. Okay, so now you can still do the attack, but you have some economic notion of security where at least it's going to cost the attacker something. And hopefully, if you know exactly what the value is to the attacker of manipulating the lottery, say it's to win some financial prize, if you make the penalty for attacking higher than that value, then you can convince yourself that you have some security. So this is basically what's done in practice on Ethereum's beacon chain. with their Randau protocol. It's a little bit different because they use a VRF rather than commit reveal to commit each participant to what entropy they can contribute. But it has the same property that you get punished if you don't reveal your commitment. But you can manipulate it. And it's actually been shown by analysis that it's currently in nodes incentive based on the current values of things to do this attack. Interestingly, nobody's done the attack in practice, so it's never been observed, but we sort of know that it's weakly incentivized to happen. Okay, these economic protocols, inherently kind of make cryptographers nervous because they require reasoning about, game theory and money. So can we do something purely cryptographically? And the classic approach here is commit, reveal, recover. So you add to the commit, reveal protocol some secret sharing so that the other nodes have the ability to reconstruct the secret of a node that drops out. Okay, so when you commit to a value, you also secret share it to all the other nodes in the protocol. That way, if you drop off, they can collaborate and keep going as if you didn't drop. So there's a lot of variations of this in the literature, but I'm actually not going to talk about how these are used in practice because essentially they aren't used in practice. So this is kind of an interesting theory versus practice gap. When we were writing our survey paper, we noticed this was the majority of the papers, but they weren't actually being used in practice. And the reason why is probably that n-squared communication cost in each round just ends up being expensive in most applications. But this does at least improve the security over simpler commit reveal protocols. So you can pick this threshold T, the secret sharing threshold, how many honest nodes you need to recover if a node drops off. And that becomes the threshold to actually manipulate the beacon output. Unfortunately, whatever you pick for T, you could say just make T really big, but you have this problem that then n minus T nodes can all go offline and then the protocol won't finish. So whatever you pick for T, you're sort of inducing a symmetric denial of service attack. So, 1 of T or n minus T has to be at least n over 2. Therefore, this is inherently an honest majority protocol. You can sort of pick if you care more about manipulating the beacon or blocking it, but at least one of those attacks, a dishonest majority is going to be able to do. Okay, so more practical approach is what I'd call a pseudo-random DRB. And the reason it's pseudo-random is that all the randomness is actually shared in an initial setup phase, which is really just a distributed key generation. So the nodes are going to talk to each other, generate a shared public key. And this setup phase might be expensive, but hopefully it's only done once. And then you have a lot of very efficient rounds where you just compute a verifiable random function on some round input. And that can really just be an index of the round number. Okay, so every round you just take the round number and compute threshold VRF or signature on that input. So that can be done efficiently if you choose the right threshold VRF scheme. So the individual rounds of output are going to be efficient. Again, the setup is going to be slow. So there's a lot of variations of this in the literature as well, and I'll talk a little bit more about DRAND, which is actually running in practice. But first, I'll just point out the properties of this protocol. So the rounds are communication efficient now, and it's actually not possible at all to manipulate this. The reason it's not possible to manipulate is that there's no entropy being added in each round. It's a purely deterministic process. So even if all the nodes go malicious once they've done the initial setup, they can't manipulate the future outputs. But the flip side of that is that they can predict them, and they can predict them forever. So there's no forward security here. If an attacker manages to compromise a majority of the nodes in any round, they can predict every future round forever, or at least until you rekey. So I mentioned DRAND, which is great. This is, as far as I know, the only production standalone DRB that's actually up and running, and it's been running for a number of years. It uses threshold BLS. Currently, there's 20 nodes. You can see some pictures here. So it's a mix of big internet companies, a couple of nonprofits and universities in the mix there. And they set their threshold that any 11 of these have to be online to sign in each round. And currently, they rekey about every 6 months. So if this did get corrupted, you would have kind of that 6-month period of vulnerability, or I guess you could have sort of an emergency rekey. But like I said, this is basically the best production DRB that we have today. So if you have an application that needs public randomness, this is this is the best place to go that's running today. Okay, so the last family I'll show you that can do a little bit better is reveal delay. So this is actually the simplest protocol. So notice two things. First, in each round, there's no commitment at all now, so we've gotten rid of commitment. Everybody just publishes their entropy contribution directly. So you just pick a random value and publish it. That's basically the whole protocol. The other thing to notice is that we now have more malicious nodes here. So in fact, this protocol only relies one honest node. And we call that node John because it's just one honest node. So move over Alice and Bob. We have a new crypto character on the scene. Okay, so why is this secure? So why can you get away with just revealing, not doing any commitment, and having only one honest node in the protocol? The reason is all the delay function. So you take some combination of everybody's entropy contribution, and you run it through a delay function. And that works because the delay function is too slow for even n-1 malicious nodes to predict what any choice of contributions will mean for the final output. Right? So the malicious nodes can look at the random contribution of the one honest node. They can think about any possible combination of contributions that they might add, but they can't compute the delay function fast enough to reason about what they should actually do. So the insight is that delay functions are really powerful. So if you haven't followed this space, there's been a lot of activity in the last 5 years developing delay functions, especially VDFs, but a lot of other variations as well. And these are kind of special cryptographic functions that are designed to be sort of moderately hard and sequentially hard. So you can usually specify a parameter, and the delay function will take that number of sequential steps to compute. So they kind of exist in between fast and intractable cryptographic computations. Okay, so there's also been some work here embellishing this and sort of adding extra nice properties to these protocols. And one of them actually runs in practice and has been running for a couple of years on the Chia network. It uses this repeated squaring VDF in class groups. So like a couple of exciting new crypto things happening there. And if you add this as a row to the table, it looks really good. Okay, so it's still linear communication in each round. And in fact, it's very simple. It's just a one-round protocol. And you need all n nodes in the protocol to collude in order to manipulate or predict the output. And it's also not possible to block. It has guaranteed output delivery. Okay, so why isn't the whole world switching to these delay-based DRBs? One note on the side there is that there is some added latency, so somebody has to actually compute the delay function. But I think more importantly, VDFs are still a new cryptographic object, and we're still discovering, as you can see from a paper just last year, kind of new cryptanalysis of how good these delay functions actually are. So I think the important steps are to get more theoretical confidence in VDFs, and we also need to invest in VDF hardware. So part of the security model is that the honest parties have access to dedicated hardware that can compute the VDF, which is, the Chia network has put in some work on that, and I think we could use more to have confidence in deploying these. Another question you might ask is that, is it possible to get these great properties without using a delay function, since I just told you that there's some caveats to using a delay function? So this was kind of a question that I was obsessed with for a couple of years. And the answer is definitively no. So we have a paper coming out at Eurocrypt this year that actually proves that if you want to have a DRB that's secure with a dishonest majority, you have to use a delay function. So that's really the only way to achieve this property. And I obviously don't have time to go through the proof here. There's a couple of subtleties here, but I'd be happy to talk offline if anyone's interested in this work, or maybe I'll see you at Eurocrypt. And another question that I think is important to grapple with, is it important to support a dishonest majority? Do we want that strong security property that even if n-1 nodes are dishonest, the protocol will still be secure? And I'd argue that it is worth pursuing. I think it is a good goal. The really powerful observation is that if you can tolerate n-1 dishonest nodes, then you can have your protocol be open participation. You can allow anybody who wants to turn up and contribute entropy to join the protocol, because adding participants can never make the security worse. If you only need one honest node, adding people is only going to increase the probability that you have at least one honest node in the protocol. Okay, so to recap, here's kind of a high-level comparison of the different schemes. Obviously, this is omitting a lot of detail, so I'll show you some links to some survey papers where you can dive into it. And you can also kind of simplify it into a flow chart that tells you what DRB you might want to consider for your application, basically based on what assumptions you're willing to make. So I'll leave you with a couple of open questions. And I'll call out particularly on the theoretical side, if you're worried about what the post-quantum story is for randomness beacons, it's actually quite good. So we know, at least theoretically, how to do certified randomness. So if we have a quantum computer, we can actually build a very strong DRB with just one node that proves, using quantum effects, that the values are actually random. So interestingly, most of the protocols I showed you would fail with a quantum computer, but we can build something even better if we have one. Also, a lot of practical questions around how we would make these easy for developers to build on, VDF hardware, like I mentioned. And the last one, I think the most important one, is the question of how we can actually convince the public that cryptographically generated randomness is actually secure. So I kind of poked fun at how the technology that big lotteries use today is fairly archaic. But I think that it is for a reason, because that's easy for the public to see on TV and understand. Maybe we need to come up with a good way to do a TV show where the cryptographic DRB actually happens to convince the public that this is legit. I don't know. It's an important challenge for the community, I think, to convince the public that this is a good way to solve this problem. Okay, so I'm happy to take questions, and I'll point out there were 3 SOK papers written almost at the same time on this topic, so it was a hot topic, all of which are a good place to go and get all the details on these protocols. Thanks. Yeah.
Hello, thanks a lot for the call out to the League of Entropy. Really appreciate that. I have a question for you. So you said VDFs are the best way to get something better than what we have right now with DRAN and the League of Entropy. So would you prefer, or would it be better to have an imperfect VDF, such as mean root, used in production today? Or should we stick with the current League of Entropy with the current limitations we have until a better VDF is designed?
Yeah, that's a good question. Personally, I think you can use an imperfect VDF because you build in a big safety margin. So you don't, fortunately, randomness beacons aren't a protocol where you need really tight limits on the VDF. So I think we could build something even using the VDFs we have today. I think building hardware is kind of the important step, though, to have high confidence in it. Yeah.
Maybe related, maybe not fully part of it. I thought with verifiable secret sharing, there's a method that you can verify that everyone contributed honestly and potentially could accuse or identify a malicious party. In that case, does it become more like too complicated if you want to like keep eliminating potential malicious actors so you can then actually run the protocol? And
yeah, so it's a good question. Yeah, I mean, I didn't talk about it, but a lot of these protocols have this accountability property where you can identify faults and kick people out, which I think in practice is great. And it's a great way to keep people honest, kind of short of having the commit, reveal, punish paradigm. So yeah, you can do secret sharing that way. I think you can do most of these protocols that way. And in practice, that's like a very good step to take.
Thank you.
Sure.
I had a question. So for the VDF
VDF-based solution, don't you need a bulletin board or a Byzantine broadcast protocol?
Yeah, okay, so, and I think you're gonna say, don't those require an honest majority?
No, don't
Oh,
those
okay.
require a lot of rounds?
They do, depending on what assumptions you make, but I mean, I think the assumption is that you can reuse some existing bulletin board service for it.
Okay.
Yeah. And the question I thought you were going to ask is, why care about a dishonest majority if you have an honest majority consensus protocol? Which is a good question, but there is an argument there, which is that attacking the beacon is usually invisible if it's like a prediction attack, whereas attacking consensus is usually accountable. So there is like a good argument that you might want dishonest majority for the randomness beacon, even if you have honest majority for the consensus protocol.
Thank you for answering the 2 questions.
All right.
Let us
Okay.
thank the speaker.
Thanks, everybody.
The next speaker will be Aniket Kate, speaking about attacking and improving the Tor directory protocol.
Okay, hi, my name is Aniket Kate, and today I'm going to talk to you about attacking and improving the Tor directory authority protocol. This is a joint work with Zhongtong Lu, Aditya Bhatt, Karthik Nayak, and Aditya is in the crowd. In fact, he's the guy who asked the last question, so in case you want to talk to him, you can talk to him. All right, so what I'm going to talk about today, I assume most of you already know about Tor. Tor is a protocol that's used by user to connect to their web services in an anonymous fashion, so that those web services are, as well as a certain level of intermediaries cannot figure it out that users are connecting to this web service. So that's certainly possible with the Tor to a really good extent. And indeed, there are already 4 million users daily that Tor sees, or even more than that, that uniquely getting corrected via Tor service. So how does it do that? So the way the Tor do such a system is that there is a user here, Alice. Alice tried to get information about an overlay network of nodes, which are shown with the plus sign over my screen. They download this information, have this information ready. This information has public key for those nodes, bandwidth, and all other information. And then once they get this information, they're going to collect some subset of these nodes, create a layered encryption circuit, onion routing, these terms you might have heard, and connect to their destination so that they get some good anonymity through such mechanism. So there is a very interesting work that has happened in terms of how to improve this cryptography of this onion routing and other things. But my talk today will focus on one of the first core concept in Tor, that downloading the information about this overlay network, these nodes, in a secure and efficient manner. Okay. So what can happen is okay, the first thing that Tor could did, in fact, that's like one of the first version that they launched in very early time of the Tor, is that there are volunteer servers. The node operators connect to these volunteer servers and say that, hey, this is my information, this is my IP address, this is my public key, this is the bandwidth that I'm offering, and so on. And the client then pick a server and fetch the information they want, and then use this information to form their circuit and get anonymity. Okay, if we can trust such a server for correctness of information, this approach can provide reasonable good anonymity. But if the server is actually malicious, they can actually only give you a subset of information or some incorrect information, and because of that, then user may end up picking, or clients may end up picking nodes so that their anonymity can be broken, because it's already a very challenging problem, and they may pick nodes which are maybe under adversary control or with high probability under adversary control, and privacy and anonymity can get broken. The problem is even harder. Like even when the node is not malicious, it's just that some different node has different set of information. And if an adversary can figure it out, that there is a discrimination in the information as it available as node, and that itself can result into different set of client picking different set of nodes, and based on that actually having weak anonymity or very less anonymity in general. So this problem was certainly understand and appreciated at Tor community. So in the version 2, shortly after that, what they started to do is that to avoid the problem, why don't we ask client to download information from multiple servers and aggregate this information locally? There are two key problems. Let me start with the efficiency problem. The one thing is that if the number of clients grow, the amount of download that's happening here is growing linearly with the number of clients, number of servers, and also the amount of information. So it's a terabyte problem, and it will continue to grow. So we can't do it this way. The another problem is that still partition can happen, that different nodes have different information, and still when you try to aggregate, different node may aggregate it differently, or just get confused because they see some different input coming from different nodes. So what we want to happen in this case is that there is an agreement, means that the nodes agree on the information that they want to propose to the rest of the clients in the system, and they sign it so that everybody know that all these nodes are agreeing on this set of information that they continue to use for their purpose. And indeed, that's the Tor directory authority as of happened today. So some information, there is a small set of 9 nodes of directory authorities. Every hour, they run this protocol that they sign their whatever information that they have collected right now, and they're called their votes onto the system. They send that to all other authorities. And once they collect all this information from all the authorities, they create an aggregate view of this information, and again sign that and send to everybody with the hope that everybody now is agreeing on the exact same information. And the assumption is that this consensus document is a valid document if it is signed by more than half of these authorities. So 5 in this example in general. So this is the protocol that was proposed and is in practice from 2007 onwards. And in a way, one can also call this as the longest running blockchain. It was running certainly running before Bitcoin. But when I tell that as a comment to Tor people, they were not so much amused by my commitment by this. But I think certainly we can call this as the longest running blockchain, at least, for my definition that I can link to. All right, so the question is that then, okay, this is the current Tor directory authority protocol. How does it work, right? So go into a bit more details. So the relays send their information to these directory authorities. These directory authorities then vote this information and send that to everybody. And if you don't get the information from somebody, you try to ask that, hey, give me that information. So they add one more round for that. That's a fetch vote or fetch information. Then they send each other again the information in a signed fashion, so that this is my view, and they send that to each other. Again, if somebody doesn't send you information, you fetch this information, and at the end of the process, the node should have expected to have the same information available, same directory information available for this particular epoch that can be downloaded by any client who want to connect to. Okay. They use more caching and other environment, but for simplicity, I'm not going into there. The core protocol remain as. And the question that we asked is, how secure is the current Tor directory authority protocol? Okay, so empirically, if you see, there are not many instances, but there are instances where indeed this Tor directory authority failed to perform consensus or to achieve consensus. Okay, and there are 2 instances that one of them, in fact, we get to know from the Tor team itself. But many of the things, when they did the analysis, they see that they can be related to network instability, or as well as DOS attack. But more in particularly, lots of requests coming for the directory information that may affect the performance for the Tor directory authority. Okay, we'll revisit that part again, but it's not that there's some issue with the protocol. But the thing is that this particular system did not consider scenarios where some of the nodes can indeed turn malicious and start behaving maliciously. Okay, and to understand that, I want to just explain a little bit of distributed computing theory, which is equivocation attack. Some of you might be already seen that, but if not, it should be very easy to understand. So in my example, there is E, which is a faulty authority faulty node, and there is H1 and H2, these are honest nodes. And H1 and H2 are going to vote 0 and 1, just simple example, bit level example. And what faulty authority does that, just to confuse them, they send 0 to the party who is saying 0 and 1 to the party who is saying 1. Okay, so they are equivocating, they are saying different things to different parties, and they are signing it. And now what's happening, that there is for 0 also, there is an honest majority vote here, which is the 2, and also 1, there is an honest majority vote. And that's the reason there may exist different consensus between H1 and H2 in this such example. And they may just start working with this incorrect information and going forward. They may realize that eventually in some example, not always, but still the ship has already sailed and they may have equivocated or different consensus that document that's getting prepared. That can happen in the protocol that we saw on the previous slide. It's not that problem can't be solvable, and indeed the problem can be solved in distributed computing setting that we come to that will be coming soon. But this is certainly something that's possible. Okay, now how to use this theoretical knowledge to launch attack. And what we observe that once we start looking into the more depth about individual protocol and parts of it, we come across a series of possible attacks that can happen there with inherent different level of difficulty to achieve. And I'm going to start with the most simple thing. So what an attacker can do is that they want to split the votes. So let's say we want 5 votes because there are 9 servers. So we want 5 votes on everything. So what if we can have a split opinion between honest parties, and one malicious party can then just stay there, either don't say anything. And now that means when that happens, that means we don't have any valid document. So single node without saying anything by having this equivocation can make sure that there is no consensus document produced, which result into liveness attack or consensus document not being available. But not only that, they can do more than that. What they can do then is that they can go forward and then actually create, let's say, 2 conflicting messages. One of them they on purpose make public, which get added and form a public consensus. And other sign information, they only don't make it publicly available. They only make it available to selective nodes and have a signature on that from those nodes, but that doesn't appear on a typical document that's available for Tor. And then they use this information to possibly launch attack on a subset of users, so that those subset of users only use that information. Okay. So so we can go beyond liveness and start creating confusion further. But if we, on the other hand, this is just with one bad node, one malicious node. If we are willing to go for even a three node which be turned malicious, especially for the bandwidth case, it is possible to launch an attack which is more devastating. So in that case, an attacker pushes, let's say, a new honeypot relay with artificially large bandwidth, and clients like nodes with better bandwidth, so that such a node can get selected with high probability. So such a node, they artificially create this information, 3 set of nodes. They find 2 honest nodes who they actually find this get assigned to their set of nodes, so that they give a valid document, a signature on that. But they again do not make this information public. They keep hidden for only their selective attack, and leave the other information without this honeypot node, without this high bandwidth node, and collect this information and make it available as a Tor document in general. Typically, this other document will be publicly available and scrutinized, and people can indeed see that, hey, this is, they'll see that there is no wrong over here, but this document with honeypot node will not be available in those public interfaces, and that's the reason attack is successful with 3 authorities. And we have indeed tested that in a testnet example and demonstrated that this can happen, and we have communicated with the Tor as well for that. But not only having a one high bandwidth node, we can also have a Sybil relay node. I mean, the one idea is rather than having one node, add lots of nodes with small bandwidth, and you can also do the exact same thing again. You have the Sybil nodes, and they all get added to the document, and that you serve that document to selected users, and then they, with high probability, use those selected nodes, and their anonymity get compromised. And this is also something that can happen. Again, all these measures that Tor have in place to make sure that such a thing can be detected will not come across this document. They'll see just other document which look much more innocuous. So all these things attacks are possible. So overall, what do we achieve? What do we observe here? So Tor makes heavy use of this public audit mechanism, and attackers can circumvent those audit mechanism with various ways. And the idea is here to target specific users over children. But very interestingly, although we keep on creating this public document, and Tor has a blockchain, as I mentioned, so this is available, these maliciously created documents could be generated in such a way that they never touch the Tor directory log, and attack may have happened and we would have never seen it. So such a possibility can exist in general. All right. So now that we see what can happen, how can we fix the problem or improve the protocol, right? So the first measure I'm going to talk about is simple, which assume that there is some kind of a synchrony in the system, and we'll just try to solve the problem reactively. By what we'll do is that which we call as Tor EQ, or online equivocation detector, where we will ask now all the nodes to send the information that they sign to a particular detector or a web interface, so that anybody who wants to check whether there is such an attack is happening, they can just figure that out by looking at this information appearing on such a chain. And Tor has already found this to be a measure which they can incorporate without affecting or without changing anything in their system. And they have incorporated that in this consensus health monitor system. And the idea is that as long as you keep checking such a monitor system, you will be able to see that attack is happening, because at least one honest node has to be involved for attack to be successful, right? So, and we created obviously an example to demonstrate that how it can work, and which is available over here. But this measure is good. We demonstrate that we can have a performance that we can generate these reports in 5 minutes, and with the 5-minute delay, such a report can appear on Tor consensus health document and can be employed. But there are limitations here, right? The one thing is the client space now trust on this detector. Again, that website goes down, or the new user do not check it. All of the things are still possible there, and all bets are off again once we go in that scenario. But what we can certainly do is to solve the problem at the root, right? That means, can't we have a protocol which still make the same assumption as Tor and is still secure? And the answer is obviously, yeah, we can solve this problem in this regard. And to work towards this problem in a methodological manner, the first thing to understand, build your threat model, your system model, right? So Tor assume bounded synchrony. That means they work in rounds, and every round is 150 seconds. A pretty big round, because it's meant in 2007 system, right? And they actually assume attacker to be Byzantine. So the malicious model that we discussed is a valid model from Tor perspective. And they target honest majority, or this 2f+1 setting, where f is the number of bad parties. And this is exactly model from Tor. In fact, our aim was that we follow the exact model as Tor, because that way we are more closer to the reality, and our protocol have higher chances of getting accommodated, right? So once given that setting, what problem are we solving, right? So the problem we are solving is that we want to produce a consensus document or consensus among the node given set of inputs. So every node has an input, and we want to agree on the inputs that are sent by that. Problem is more nuanced. We don't actually, it's fine if we don't output all the inputs. We can do some more computation and only output some aggregated information. But there are just so many different rules that solving that to individual for bandwidth and other architecture, a guard node or other thing, can become a very challenging problem. So that's the reason the best, simpler idea is to just make sure that we collect input and we produce a document with all those inputs into such a setting locally, and then the clients now know what information they need to work, the authorities now know what information they want to work on, and they work with that information. This problem in distributed computing setting has a very interesting name with a holistic called interactive consistency problem, where informally every server is going to output the same set of values given the inputs that are coming from the clients. Okay, and you want to make sure that the information from a correct authority is available into such a document for sure, and it's not that the information from correct party is somehow not considered. And the way we implement that with a primitive called Byzantine broadcast, where you make sure that information from every node is available to every other node, so that then they can run this interactive consistency locally and have an exact same document available. Okay, so that's the setting. There's some more particularities that we come across for Tor. That Tor has 9 nodes, and generally, so that means my n is not much high. Documents are quite big in general. We can't assume randomness or other services because and have randomized protocol, because at least so far it's not easy to incorporate that into the setting. And the idea is to have an optimistic protocol which works when there are no node failures, and minimize and only have a pessimistic phase when things go wrong. And given that protocol, we provide a Tor Directcast, a new Tor Directory Authority Protocol. It is a cubic complexity protocol, but our n is small, so it doesn't affect that much in that respect. We have implemented that, and we introduced some interesting new measures such as compression and only sending the diff among the 2 documents. And what we observe is that while providing security as compared to the current state-of-the-art protocol, we are able to get almost similar performance as the current Tor Directory Authority. So moving on, then the idea is that we work with the Tor community on this extensively. In fact, we got opportunity to also communicate this one-on-one, and We reported them, they acknowledge that, we get opportunity to talk to one-on-one to really understand what is their real attacker model. So they are much more worried about single node launching attack than 3-node coordinating, stuff like that we understood. And they worked with us once the such measure was available to incorporate that. But a proactive measure is still not included because they're still working on their network library and improving that. But we hope that to work with them towards including the proactive measure. The last thing we want to talk about is that looking at this problem, somebody who's not so much fan of the bounded synchrony assumption, this bounded synchrony assumption was always something that we find challenging. And we asked that, is that really a reasonable assumption? And what we question that, do we really need this rather steep bounded synchrony assumption in setting? And we observe that actually it is not satisfactory for some scenarios, and we can launch DOS attack, which may look like a real networking scenario where such weak nodes can actually become non-responsive, and because of that, there'll be at least liveness attack or further attack. And we suggested that it's better to go for non-synchronous assumptions such as partial synchrony and provide a solution so that the protocol works in partial synchrony to achieve the Tor consensus. And we have communicated that, but let's see what happens from there onward. All right, so summarize, we have seen some vulnerability with the Tor directory authority. We have communicated that with the Tor. They have already incorporated a reactive mechanism that can be used by users. And we also propose a proactive mechanism to stop the attack in the first place. And we look forward to possibly work with Tor community for that. Thank you.
Unfortunately, we are out of time, so I suggest you take the questions offline. Let us thank the speaker again. So the next speaker will be Daria Kaviani, speaking about Flock, a framework for deploying on-demand distributed trust.
Hi, everyone. My name is Daria, and I'll be presenting our work Flock, a framework for deploying on-demand distributed trust. This is joint work with Sijun Tan, Praveen Govindankanan, and Raluca Adapopa. So what is distributed trust and why is it useful? Well, suppose a user, Alice, has a secret to store. She can store it on a server, but what if that server is malicious or compromised? In this case, the server is a central point of attack. Enter distributed trust. Under the distributed trust paradigm, Alice splits her secret into several pieces and distributes it among several parties. In this case, distributing the sensitive data avoids a central point of attack because adversaries must now compromise all N servers in order to compromise the secret. So even if one server or even up to N-1 servers are compromised, Alice's secret is still safe. Many distributed trust applications are enabled by a cryptographic primitive called multi-party computation, or MPC, where several parties are going to compute some joint function f on their inputs, and the key property of MPC is that the parties do not learn anything about each other's inputs other than the final function result. A key example of the need for distributed trust is in the application of digital asset custody, where a user, Alice, has maybe the Coinbase wallet application on her client device, as well as a signing key that she uses to sign transactions and, say, post them to a blockchain. But this begs the question, where can Alice store her transaction signing key? Unfortunately, to date, billions of dollars have already been stolen by compromising these very signing keys alone. That's why many of these applications have already turned to distributed trust, where Alice is going to instruct these parties to conduct an MPC for signature key generation in order to produce shards of the signing key. Next, when Alice wants them to sign a transaction, she's going to send copies of it to each of the parties. Next, they're going to engage in another MPC in order to produce a signature on the transaction. And finally, as usual, the transaction can be posted. Even if one of the parties is compromised, the secret share reveals nothing about the overall secret, and so Alice's secret is still safe, and the system doesn't have a central point of attack. And this is just really the tip of the iceberg. We actually manage a growing community-owned hub of MPC applications at mpc.cs.berkeley.edu. So there are a lot more distributed trust applications, but unfortunately, a significant challenge still precludes the mass adoption of distributed trust. And this is that a large class of prior work simply assumes that N non-colluding trust domains already exist. But this is far from the truth. And it brings us to the deployment dilemma, which is how can an application provider, which is inherently a single trust domain, go ahead and deploy a multi-trust domain system? So let's give this a shot. For our first attempt, we'll just have the application provider deploy N servers, okay? And then Alice is gonna share her secret and distribute it among them. But clearly, if the application provider is compromised, then so are all of the parties that it deployed. So this clearly won't work, and it brings us to today's model of traditional distributed trust, where the application provider is tasked with forming business relationships with N-1 other entities. But unfortunately, this has been pretty tricky in the real world. Whether it's Meta's private advertising, Signal's secret key recovery, Google and Apple's private analytics, or Coinbase's digital asset custody, real-life deployers of MPC have found that it is difficult to convince MPC parties to deploy, run, and maintain your application workload. And so imagine how hard this is for your everyday application developer. And so our goal in this work is to enable anyone to automatically deploy distributed trust, even just a single developer. And so the key insight of our work is to fundamentally rethink how we think about distributed trust deployment. Because in the traditional model, it's the application provider's job to find the parties, form the business relationships, deploy the code, and then the user, Alice, is going to interact with the parties. We propose the following alternative. Yes, the application provider can run a party, but the user, Alice, is the trusted owner of her own sensitive data, and so she can actually help with the conducting of her deployment for the other N-1 parties. And this results in an automatic deployment paradigm that we call on-demand distributed trust. Our system Flock is for deploying on-demand distributed trust through user-driven deployment by using cloud providers as trust domains. So first, we'll discuss how we reverse the approach to deploying distributed trust by taking the onus from the application provider and leveraging the user at the core of the deployment. And second, we'll show how we design a practical end-to-end system to realize this vision in a way that's both cost-efficient and secure. We also port 8 different distributed trust applications spanning 5 core cryptographic modules in our work, and you can learn more about these in our paper. So before we dive in, we'll discuss who we can trust and who we can't. A key assumption of our work is that at least one cloud server is uncompromised. We would hope that AWS, Azure, and GCP don't all get attacked by the very same attacker at the very same time. Also, we have malicious security if the application that's deployed on top of Flock is also malicious secure. We assume that client code is trusted because we assume that code is open source and therefore community scrutinized. And a nice property of our model is that compromised clients cannot affect uncompromised clients. Okay, so how do all of these pieces come together? Well, for our first try, let's just have Alice, the user, deploy N-1 VMs in N-1 distinct clouds. And the application provider can do an MPC execution with these VMs. Unfortunately, we run into a bit of a scale issue because this might work great for one Alice, maybe even 2 Alices, maybe even 3, 4, 5, 6, or 7 Alices, but try tens of millions of Alices or the number of monthly active users of an application like Coinbase. So the harsh reality is that 1 VM per user per cloud is just going to be prohibitively expensive for these ephemeral workloads. To solve this problem, we turn to serverless computing in order to scale Flock. Serverless computing is stateless compute that exclusively incurs cost at execution. And fortunately for us, most major cloud providers offer a serverless computing offering. There's 2 really great things about serverless that are great for Flock. The first is that serverless incurs no cost when the user is not actually performing an operation, and serverless containers are executed on demand with very low startup time. So how would this work? Well, the Alice is going to go ahead and deploy S1 and S2 serverless instances in distinct cloud providers, and the application provider is going to do the MPC execution. To make this more concrete, maybe Alice deploys an AWS Lambda instance and a Google Cloud Run instance, and the application provider can run in the other cloud, Azure. But this brings me to our first main technical challenge, which is that in MPC, you need the parties to be able to communicate over a secure connection. But unfortunately, serverless instances, especially those in distinct cloud providers, do not inherently accept incoming connections because they're in distinct network address translations. And so our question was, how can we establish secure peer-to-peer serverless connections? The insight here is that, yeah, we can't trust the application provider for security. That's the whole point of this work, but we can trust it for availability because it is the entity that wishes to offer this service. So what we do here is we actually leverage the application provider to run an untrusted relay to securely route messages. And this solves our connectivity issue because the serverless instances can just connect to that central relay. And so we have to actually create a new two-phase TLS establishment protocol that allows us to establish an end-to-end secure TLS connection over 2 consecutive TCP sockets. Great, so we've solved our connectivity challenge. We can now do MPC among these different serverless instances. The second main technical challenge of our work was in authentication. As you can see, the system architecture we have on the right here is far more complex than your standard application. And the problem is really that user-driven distributed trust introduces new attack vectors all across the stack. So the question we have to answer now is, how can a provider secure a deployment it just doesn't control? So like a usual application, an attacker could attack at the application level. But in our case, it can also attack at the cloud level or at our more complex network connections. So our task was to design a comprehensive authentication suite sort of spanning all of these layers. To secure the application layer, we used MPC auth, which is a cryptographic protocol that allows a user to authenticate to end parties with the work of one. To secure the cloud layer, we used cloud IAM access keys for invocation purposes. And for the network layer, we used certificates. So parties authenticate with user-signed certificates to one another whenever they're forming their network connections. And another challenge that you can read more in our paper about is in resource protection. So how can the provider protect the deployment without controlling it? And for this, I encourage you to take a look at our paper. Great, so now that we've solved the main challenges, I'd like to bring us to the original example of digital asset custody to see how all of these moving examples come together. Recall that we have a user, Alice, with a signing key, and she wants to sign a transaction and post it. How can we do this with Flock? Well, first, the application provider is going to go ahead and provide the code to the user's client device. Next, the user is going to programmatically deploy the application in serverless instances S1 and S2. She's going to take a PIN that we'll later use for authentication and distribute it among the parties. Next, we're going to have these parties engage in the MPC we talked about earlier for the signature key generation, so they now have shards of the signing key among them, 2 of them at the serverless and 1 of them at the application provider's VM. Now Alice wants transaction signed, so she's going to take a PIN attempt, which should be equal to the original PIN, split it into pieces, and distribute them among the parties. Next, they're going to engage in an MPC over their secure connections for an MPC auth to check whether the PIN attempt is equivalent to the original PIN. And if it is the case that this check goes ahead and passes, now Alice can send her transaction over to the parties, and then they're going to engage in an MPC in order to do the signature generation, and we're done. We now have a signed transaction, and we've successfully used Flock. To make this crystal clear, I'll also give us another example with another example application of secret recovery. So what is secret recovery? Well, in many end-to-end encrypted applications like Signal, a user Alice downloads the app, and say another user Bob does the same. And what they want is to have an end-to-end encrypted communication channel where they can send messages back and forth. And so similarly to our other application, this begs the question, sort of where can Alice store her encryption key? Well, she could store it on her client device, but what happens if that device is lost, stolen, or broken? I mean, she could store it on the server, but again, that server could be malicious or compromised. She could also have another alternative where she encrypts it with a 4-digit PIN, sends that ciphertext over to the server, gets that ciphertext back, decrypts it with a PIN attempt, gets her key, but this is susceptible to a brute force dictionary attack. So as an alternative, I'll propose that we use Flock for this. So how can we do this? Well, first, Alice is going to get the code from the application provider. So in this case, Signal is going to somehow provide the code to Alice's client device. Next, she's going to programmatically deploy the application to serverless instances S1 and S2. She's going to take both her PIN and her secret key, distribute it among the parties. And now, suppose that she wants to reconstruct her key. She's going to take her PIN attempt, split it into several pieces, distribute it among the parties, and then again, they're going to establish their secure connections and do MPC auth to see whether the PIN attempt is equal to the original PIN, and if the check passes, Alice can successfully recover her key. Now we'll talk about our implementation and evaluation of our system. So starting off with the implementation, like I said earlier, we implemented 8 different distributed trust applications spanning 5 core fundamental cryptographic modules here. This was implemented in 2,000 lines of Go, Python, and C++ each. And for our evaluation, we really wanted to ask, is Flock's performance comparable to traditional distributed trust? What is the downside of using Flock? Is it the same as before? And so for the baseline, we deployed VMs on the distinct cloud providers, one in Azure, one in AWS, one in GCP. And for Flock, we deployed the application provider in Azure and then serverless instances in the other two clouds. Overall, we found that our latency on average across all of the cryptographic modules we evaluated was about 1.05x the baseline. And it was quite a similar story for the throughput. So we saw that we had comparable throughput across the board with these different applications. We also conducted a cloud cost comparison to see the dollar cost difference for an application provider. So this was a bit tricky because in terms of a cost model, VMs have a fixed hourly cost, whereas serverless cost is actually per request. And so we actually estimated the server's per request cost from the module's maximum throughput. And these were our results. You can see that for signing an application that is a bit more compute intensive, because there's an upcharge for serverless compute on the clouds, there was about a 2.5x cost overhead, but something like decryption, which is more network intensive, was only 1.3x overhead. But what I'd like to emphasize is that this cost, Flock's system cost overhead, is really negligible when it comes to the cost of setting up these business relationships. So if you ask any of the MPC deployers in the room, I'm sure they tell you that they'd rather spend a little more cloud cost money and solve the non-collusion problem. So zooming out to a bird's eye view of Flock, Flock combines the security of the clouds and reverses deployment to leverage users at the core of the system. And in doing so, we provide the first way for an application provider to automatically and immediately deploy distributed trust. Here's where you can learn more about our paper as well as our code, and I'm happy to answer any questions.
We have plenty of time for questions.
Thanks for the talk. So, okay, you illustrated a scenario where Alice is a customer of, I guess, Coinbase, roughly, right? But Alice now presumably also needs to be a customer of like AWS in order to deploy Lambdas, right?
So she's going to have to, basically the way that our system works is we use a web page automation framework so that the client device sort of takes one password and then automatically navigates the creation of the different cloud accounts and programmatically deploys the serverless instances. So yes, she will behind the scenes have an account with the cloud providers, but it's not like she's going to have to go manually set up that process on her own. We actually integrated this and have, you know, the multi-factor authentication for the cloud providers built in.
And a quick second one is, am I right in thinking that this setup rules out secure aggregation?
Yeah, so we really outlined in our paper, but the distributed trust applications that this works for are those in two categories. One, where the sensitive data is owned by one user, or if you're computing on public data. So this would work fine for PIR on a public database. It would work great when there's like a secret key. Maybe you're doing like a collaborative kind of snark or anything where the secret sensitive data is that of one user and the MPC is for one user. But like you're saying, when it comes to something like private analytics, the sensitive data is the combined data of all the different users. And so that's actually a problem that, you know, we're still thinking about how to solve in an on-demand deployment model.
Thank you.
Thank you for the talk. Could you elaborate on that line of NAT between the two serverless functions and two different cloud providers? Because typically you would run these things behind API gateways, in which case they can just talk over TLS.
Yeah, so we actually found that, you know, the different cloud providers, I mean, we were able to do a sort of TCP hole punching approach to get Lambdas within the same cloud to communicate, but we found that, you know, there's kind of some NAT and firewall configurations that are not exposed to end users. So using a more direct approach to establish those connections was quite difficult across clouds. And so in order to provide a solution that was really foolproof and could work across the board, any cloud, any sort of NAT configuration, any firewall configuration, we opted for the relay. But you could definitely have another way. It just might not be as general as the relay approach.
Thank you. And sorry, a quick follow-up question. Do you consider relaxing your threat model a little bit, say, to a single cloud region being attacked? So you could actually do this within one cloud provider?
Yeah, so, you know, if you trusted the fact that, you know, if you consider the different AWS regions as different trust domains, then you could totally do that. And maybe it would make the networking not require an untrusted relay or something of the sort. But we thought it would be stronger to say, okay, let's make it the case that Azure, GCP, and AWS, all three of those are not going to go out at the same time. But yeah, if you wanted to consider the different regions as different trust domains, then you could do that. Thank you.
Hi, great talk, and thank you for the talk. I have a question. How did you actually measure the latency? Because like in my opinion, if you deploy new function for every transaction, doesn't that require additional latency that is significant for every transaction?
Yeah.
Or how did you kind of measure the latency itself?
Yeah, so we actually don't deploy a new function every time. So when you are setting up the system, in the very beginning, Alice is going to programmatically deploy the serverless instances. But later on, because we have all these authentication layers, you actually use the previously deployed instances and you just invoke the serverless instances. Now, there are challenges with cold start, which is why we have to use, specific, we couldn't use things like AWS Fargate, which have like a slower startup time. And that's also why we had 1.05x the latency. It's a little bit slower, but you're not deploying every time, you're invoking every time.
Oh, okay, thank you.
Yeah. Of course.
One last question.
Yeah, sorry. In the Signal example, what happens to the cloud credentials if I lose my device? Like, do I need these to re-authenticate, or are those stored somewhere else?
Yeah, so at the cloud layer, we really wanted to prevent a situation where an attacker who doesn't have the application layer authentication factor just would drain funds by just invoking the instances. So we do have that cloud layer of authentication. It's one of our 3-tier authentication factors. And if you lose that, then you do need to go through the cloud and re-download a new one.
Okay, so in a certain sense, you're partially depending on the cloud for your security model there.
So not necessarily, because even if that was compromised, you're still not going to be able to get into the application because you still have the application level authentication.
Assuming you can't.
But if you lost your device, you would need to just, get a new IAM access key.
Okay, thank you.
Let us thank the speaker again. So the final talk in the session will be given by Jonas Nick, who will be speaking about ready-to-use distributed key generation.
Thanks, Lenka. All right. Yeah, so this talk is about distributed key generation in the context of threshold signatures. In practice, implementing threshold signatures and distributed key generation has required a lot of guesswork because of unavailable, insufficient, and complicated definitions. I am going to talk about how this has led to real-world vulnerabilities and present a solution, a DKG protocol for frost threshold signatures with ready-to-use specification. This is joint work with Tim Ruffing. First, let's briefly recall what threshold signatures are. In a T of n threshold signature scheme, any T signers out of a set of n signers can collaboratively produce a valid signature. And importantly, T minus 1 signers should not be able to produce a signature. The primary application we are interested in is in the Bitcoin space, and there is quite a range of applications. For example, in Bitcoin, you can use threshold signatures to secure a personal wallet, for example, with a 2 of 3 hardware wallet setup. And that way, you don't lose access to your coins if one device is lost. Threshold signatures can also be used in more complex setups, like wallets split across multiple entities that are connected through some network and where the signing keys are stored on highly available servers. Because we are primarily interested in Bitcoin applications, we focus on a very specific kind of threshold signature, namely the kind that works directly with the standard Schnorr verification function that is supported on Bitcoin. This function expects an ordinary Schnorr public key. So if we want to use threshold signatures in this setting, we need to generate that public key using an interactive distributed key generation protocol, a DKG between the signers. The function also expects an ordinary Schnorr signature, and producing such a Schnorr signature for the threshold public key requires an interactive signing protocol. The benefit of Schnorr-compatible threshold signatures is that they're indistinguishable from ordinary signatures on the Bitcoin blockchain. That means there's no privacy loss or extra transaction fees when using threshold signatures. The state-of-the-art scheme for Schnorr-compatible threshold signing is Frost. FROST stands for Flexible Round Optimized Schnorr Threshold Signatures, originally proposed by Komlo and Goldberg, and since refined by several follow-up works. Round optimized here means that FROST only needs 2 rounds of communication for signing. And crucially, FROST does not require the majority of signers to be honest. So it supports dishonest majority settings for unforgeability. And this is important because requiring an honest majority would exclude a 3 or 4 setup, for example. That's because in a 3 or 4 setup, we assume up to t-1 equals 2 signers to be dishonest, but that means there are only 2 remaining honest signers, and that is not a majority. Okay, so this sounds all very promising, but when we look around, we see that there are almost no real-world deployments of this. And why is that? So let's take a step back and look at what we can call the idealized real-world crypto stack. Layers from bottom to top are papers and security proofs, standards and specifications, implementations, and deployments. For FROST signing, we have established papers with thorough proofs such as the original FROST paper and follow-up works. There's also a high-quality specification of FROST in the form of an IRTF RFC. And there is a growing list of implementations of FROST. So this specific collection of implementations was already presented at RWC 2 years ago. So there is a spec and there are implementations, but there are very few deployments 5 years after FROST's publication. So our thought was, let's increase adoption by implementing FROST with distributed key generation in our Bitcoin crypto library, because this is a library that Bitcoin devs are already familiar with. By the way, that library is called SecP256K1ZKP, and it's a fork of the library used in Bitcoin Core and supports more advanced primitives. As we've seen before, if we want to implement the entirety of FROST, we don't only have to implement signing, but also distributed key generation. So the natural place for starting an implementation would be to look at the FROST RFC. We cannot use the FROST RFC directly because the Bitcoin protocol uses some optimizations that are incompatible, but that's no big deal. We could account for that. The problem is that the RFC considers key generation, and in particular distributed key generation, out of scope. So it's just not specified. And going back to our cryptography stack, for the DKG part of FROST, there are papers and security proofs, but there's no specification. So you now realize, okay, this project will take more work, but okay, let's implement the DKG as defined in the papers. What does DKG for FROST look like? There are, of course, many DKG protocols in the literature, but for full compatibility with FROST, we narrow our focus to protocols that support dishonest majority settings, and the DKG should work in an asynchronous network. And with these requirements, we are basically left with variants of PETPOP, Patterson DKG with proofs of possession, which was originally designed for FROST. It runs in 2 communication rounds, and while it's not a general purpose DKG, it has been proven secure in combination with FROST. All right, so when you want to implement the PETPOP DKG as described in the FROST paper, you will find that the DKG requires sending messages between signers using a reliable broadcast protocol. So what does that mean exactly? There are countless flavors of broadcasts whose security and availability guarantees differ slightly, sometimes significantly, and often subtly. The first thing the implementer needs to realize is that reliable broadcast is more than just regular network broadcast. And there is no obvious lightweight or off-the-shelf implementation for such a broadcast, especially one that supports a dishonest majority setting. Okay, so the implementer needs to build a broadcast protocol themselves. So first attempt, vibe coding. If you haven't come across this term yet, this refers to relying almost entirely on artificial intelligence for coding. I tried various experiments with current ChatGPT models and found that ChatGPT interprets reliable simply as guaranteed message delivery and overlooks malicious senders entirely. So if we would use such a broadcast protocol coded by ChatGPT, the resulting DKG would be horribly broken. Right, second attempt, do more research. And what you may find is documentation from a Frost signing implementation, and it instructs users to provide a suitable broadcast channel themselves in order to run the DKG. It lists a bunch of informal properties the broadcast channel is supposed to have. I'm not going to go through them here, but the bottom line is the implementation asks the user to find or implement a broadcast protocol that satisfies a set of rather imprecise requirements. Now, the really sad state of affairs is that even if you interpreted those requirements correctly, the resulting DKG protocol is still broken because one crucial requirement is missing, and let's take a look at why exactly. So this diagram depicts part of a 2 of 3 PETPOP DKG. I haven't described at all how PETPOP works, but I hope you can bear with me anyway. The only important part here is that in this protocol, it is possible for a malicious participant to send valid message to one signer and an invalid message to another signer. The signer who receives the valid message believes the DKG succeeded and might go ahead and send actual money to the resulting public key, for example, using the Bitcoin protocol. But the other signer who received the invalid message considers the DKG to have failed. So what's the result? In this 2 of 3 setup, 2 signers are either malicious or have failed. There's only 1 signer left, which is not enough to produce a signature. And that means that the coins sent to the public key are lost forever. So let's recap. Our goal was implementing Frost with DKG. But even if you carefully study the Frost papers, obtain the right definitions for the flavor of broadcast needed, interpret them accurately, and correctly implement broadcast, secure channels, and the DKG protocol itself, the result is still broken. And the solution that we propose is ChillDKG. ChillDKG is a protocol and a specification designed specifically for Frost and with all the hard parts built in, like reliable broadcasts, secure channels, and all the little edge cases that are easy to miss. And we're going to very briefly walk through how ChillDKG solves the problems we've just seen. The design of ChillDKG is based on simple PETPOP, which is a variant of the original PETPOP protocol. One main difference is that simple PETPOP replaces the broadcast abstraction used in PETPOP with an interactive equality check protocol, EQ. The EQ protocol takes some input and either succeeds or fails. Simple PETPOP requires 2 properties from EQ, which I state informally here. Integrity, if some honest signer succeeds, then the input values of all honest signers are equal. And agreement, if some honest signer succeeds, then eventually all honest signers will succeed. So how does the EQ protocol that is specified in ChillDKG actually work? This protocol is a signed variant of a very simple echo broadcast protocol. Here's how it works. Everyone signs their input and sends the signature to everyone else. And when a signer receives valid signatures from all n signers, this signer's EQ succeeds. So extremely simple. And this satisfies integrity because if a signer succeeds, they hold signatures from everyone on the same input, meaning that every honest signers had the same input. What about the agreement property? From the protocol description, we can see that whenever a signer's EQ succeeds, they've collected signatures from all other signers, and we call this list of signatures certificates, or a certificate. And that certificate can be sent to another signer to make them succeed too. And fortunately, this satisfies exactly the agreement requirement that we need. Now, back to simple PETPOP, it has the important property that if there's agreement in this EQ protocol, then there's also an agreement in the DKG as a whole. And that means if one participant in the DKG succeeds, they can convince every honest participant to succeed as well. And this directly prevents the failure mode we saw earlier, where an adversary could trick one signer into thinking the DKG succeeded while the others fail, which led to a loss of funds. And this works in an asynchronous setting and does not require an honest majority. ChillDKG comes with a bonus feature that makes it even more practical. We extend the input to the EQ protocol with essential parts of the transcript of the DKG protocol. And the difficulty here is to keep the size of the input in O of n. We solve that using homomorphic encryption and other aggregation techniques. But the crucial part is that then this extended input and the certificate allows any signer to recover their DKG outputs from a single per device secret seed, for example, when the device is wiped or broken. And what this means is that the per DKG backup is just public data, namely the input and certificate, instead of secret data, which is what you would usually have to back up from a DKG. And we believe that this significantly simplifies backing up Frost signing keys because the recovery data is the same for all participants and it can be stored by an untrusted third party. All right, to wrap up, takeaways. DKG is integral to Frost, but securely implementing it has been notoriously challenging. And one reason is that unclear requirements, especially around broadcast, lead to subtle and sometimes devastating vulnerabilities. ChillDKG provides a ready-to-implement specification that addresses these issues, and it offers more practical features that we didn't have time to cover. The full specification is available at this URL, and we'd love to hear your thoughts on it. Feedback is very welcome. And last but not least, we are hiring. So if you're interested in cryptography on Bitcoin, and I can assure you that there are many interesting real-world open problems on Bitcoin still, and you could imagine working with us, then please reach out. All right, thanks for your time.
We have some time for questions. Maybe while you think about, let me ask one. So what would you say, what could the community have done better to prevent some of the issues that you have found in your journey?
So I guess one of the original problems was perhaps that the requirements in the paper on the broadcast, they were never really clear. It was sort of hand-waved away. And maybe if that had been stated more clearly, that would have already been helped. But I think maybe it just takes time for a relatively complicated interactive protocol like Frost to transition into the real world, because you really need those specifications that are open and that people can look at and see if they actually break, because there are many edge cases where things can fail.
Thanks.
So for the case of multi-sig wallets that are like 1 of 2 or 2 of 3, are people always using a DKG, or do people just use the model where like one factor generates the key and sends shares to the other, and it's secure as long as they're not all hacked when you start?
Sorry, I don't really understand.
Well, it's like you don't necessarily need a DKG to set up a multi-sig wallet. Some people just generate a key, kind of just have one factor of the 3 generate the secret key and then send shares to the other.
You mean the traditional multi-signature model in Bitcoin where you have multiple public keys?
No. Even with a thresholded key, you just generate the shares centrally, right, on your phone or whatever your second factor. Like
the trusted dealer model.
Yeah,
is that what you're referring to?
Trusted dealer, perfect. Yeah. Is that still like popular for threshold wallets, or is this?
I'm not sure if people actually do this, but it seems like it would defeat the point, right? Because then you have your single point of failure. If the trusted dealer is,
I guess it's only a single point of failure during the setup. So
right.
Yeah, so it's better than nothing, right?
Right. Yeah. So that part is kind of specified in the RFC. It's in the appendix.
Okay, thanks.
Hello, great talk. This is really important. We also had issues with this, so I'm glad that you're working on standardizing this. My question is, for DKG, you also need to encrypt the message, right? So I'm wondering if ChillDKG also specifies how the encryption is done?
Excuse me, sorry, I couldn't hear it.
Does ChillDKG also specifies how the encryption?
Yes,
okay.
Yes, ChillDKG specifies that. So one way to think about ChillDKG is that it's sort of built in 3 layers. On the bottom, you have simple PET-POP, which doesn't specify any encryption. And then on top of that, we built what we call Encrypted, which specifies how to do the secure channels. And on top of that, you have chill DKG, which adds this equality check protocol. So
Cool.
yeah, it should be ready to use, including the secure channels.
Cool. On top of that, I have a suggestion. Some uses of Frost also requires encrypting the message for the signing.
Mm-hmm.
So it would be good to also have a kind of standard, which I guess would be like probably the same thing from the 2DKG, that how to encrypt and authenticate the message during signing, not during the DKG. I guess could just reuse the same structure.
Yeah, you might not be able to use this DKG for different protocols because it's not a general purpose DKG. It's not simulatable. One signer can bias the result, but it works for Frost.
Yeah, thank you.
Let us thank the speaker again.
Thanks.
This concludes the session, and we will resume after the break at 15:45.
Hi, everyone. We're going to start the next session in about a minute. So if everyone could grab their seats. All right, welcome to the last session of RWC. It's time to get started. And so our first talk is on ZK login. And yeah, welcome. Yeah, Tini and Deepak are going to give the talk. Floor is yours.
All right. Hello, everyone. Thank you, Dan, for the introduction, and thank you, everyone, for making it to the very last session of RWC. So today we're going to present ZK login, which is a novel method for authenticating users in Web3. I'm going to do the presentation jointly with Deepak, and this is work that was developed at Misten Labs, which is the cryptography research team behind the Sui blockchain. And just to get your attention from the very first slide, let me tell you that ZK login is one of the very few examples that has actually successfully deployed ZK proofs in practice. And right now, as part of ZK login, we have roughly 10,000 ZK proofs daily. So if the clicker works, good, all right. So let me start with some motivation about why do we need a new method for Web3 authentication. And let me tell you that right now, we have roughly 500 million Web3 accounts. So if we try to contrast that with the number of accounts that we have in the traditional Web2, we're going to see that there is a very large gap. So in Web2, we have several billions of user accounts. So there might be many reasons for this big difference in the numbers. Maybe not every Web2 user wants to have a Web3 account as well. But one of the reasons that we see such a big difference here is that actually creating an account in Web3, onboarding in Web3 is quite different. And it can be quite challenging, especially for users who are not technical. So let me walk you through a little bit of how onboarding looks like in Web3. How does it look like if you want to create a blockchain account? And we're gonna focus in this talk in accounts that are non-custodial. So basically in accounts that do not place trust into a third party for handling their keys. So when you're trying to create a Web3 account, one of the most common approaches is to start by downloading some sort of browser extension. One of the most popular ones are MetaMask. And this application is going to help you to create your cryptographic keys, a pair of secret and public key. And it will also help you to create a mechanism in order to remember these keys, because remember that in the blockchain space, forgetting your secret key literally means that you're going to lose your assets. So if you try to play with MetaMask and create a Web3 account, it's going to ask you to create this secret phrase that consists of 12 words, and you need to write it somewhere down because this is your only mechanism to recover your funds if you lose your key. And it's going to ask you to repeat this, and only after doing this whole process, you can actually start doing transactions and signing using your cryptographic keys. So this process looks very, very different from the typical Web2 account opening, and for many users, it can be rather frustrating. So what we want to claim is that mnemonics and keys are actually not going to get Web3 into mass adoption. And ideally, we would like to have a way to create accounts in Web3 that looks pretty similar to account creation in Web2. As a matter of fact, a very common approach the last years in account handling in Web2 is to not even create new accounts for every single service that you want to use. And instead, reuse your existing long-time accounts with Google, Facebook, GitHub, and so on in order to authenticate and log in other services. So the goal here is to do exactly the same for blockchain accounts. So the end product, as I said, is ZK login. And the goal of this end product is exactly this, to make onboarding very, very easy. And ZK login has been actually, as I said before, implemented and deployed in the SUI blockchain. And this is how the SUI ZK login wallet looks like. So the idea here is that the user can just log in using an existing, let's say, Google account, and the process looks very, very easy. They can just pick their existing Google email address and access their funds and do transactions this way, which looks, much more familiar to the average user. So let's get a little bit more technical. Let's see how we actually can create a service like this. So ZK login is going to combine OAuth tokens with zero knowledge proofs, with the goal to create an authentication mechanism for Web3. As I said before, our focus is to not rely on any third party, so the solution is non-custodial. We want to have a very user-friendly experience, so it should be very, very easy from the point of view of the user. And because now there's no third party and everything is going to go on blockchain for verification, we also need to be mindful about the privacy of the users. So in order to explain how ZK login works, let me briefly remind you how OAuth tokens look like. And in particular, for ZK login, we're going to use a popular extension of OAuth 2, which is the OpenID Connect. And the part of OpenID that is very useful for us is the fact that there is this ID token, which is a signed token that includes attributes over the user, for the user. So if we take a closer look at how such an ID token looks like, and if we just look at the decoded part, we can see that it consists of three parts: the header, the payload, and the signature. Most of the signatures in this token are actually RSA signatures, but the standard can also support ECDSA signatures. And the payload is the part that it's really the most important part for us. So this, and I should say that this ID token is basically a GWT token. So if we take a closer look at a particular example of a JWT token issued by Google, and we focus on the payload, we're going to see that there are various attributes here that are going to be particularly useful for the design of ZK login. We see that there is an ISS field, which basically denotes who is the issuer of this token. We're going to see that there is this audience, AUD field, that denotes who is the intended recipient for this token, who is the intended content for this token. And we're going to see that there is this subject field, which is basically some sort of unique information about the user. What is even more important, though, is that there is this field that's called the nonce. And this is actually a field that allows the user to whom the token will be issued to import, to embed some information of its choice. So having said that, let me pass the torch to Deepak to explain how these nonce can be particularly useful for the creation of ZK login.
Thanks, Futani. I'll take you here for the rest of the talk. So let's get into the technical meat of our work. Right, so really the crux of the challenge is, how do we take this JWT looking like thing and somehow authorize blockchain transactions with it? And as Futani kind of hinted at, the key trick really is to use this nonce in a way to allow us to do this transaction authorization. So in particular, what we do is to embed freshly created, so we first create a fresh key pair. I call that the ephemeral key, and we embed the ephemeral public key into the nonce field of the JWT. So this is all happening on the user end. So the user just creates a key pair, inserts the public key, and sends the token. So it sends the request to Google or whichever OpenID provider the user is using. And at the and at the end of the OpenID Connect or OAuth flow, the user has a token with a signature of the OpenID provider over the whole token. And in particular, note that what we've essentially kind of done is got a certificate over the ephemeral public key from the OpenID provider. And we're going to use this certificate later to kind of authorize transactions. In particular, what we're going to do is take the corresponding private key and use that to sign transactions. So that is how, at a high level, we're going to authorize transactions. A second challenge is to identify the user in a way that is privacy preserving. What do I mean by that? As you might know, blockchains, in particular SUI, the blockchain we're building this for, has completely public information. So whatever transaction information you post on chain is just completely public. Now, a user presumably is going to return across sessions, and we need a way to identify the user across sessions. Now, thankfully for us, there is a field, as Futini said, the subject identifier, which is a unique identifier of the user. We could directly use that to identify the user, but we don't want to reveal something. So what we end up doing is introduce a randomizer called SALT, which is a secret the user generates at setup time. So when the user is onboarding to the wallet, they generate this. We generate this random value. This needs to be saved. Saving this is important because otherwise you kind of lose access to your account. And this salt is essentially what helps us unlink the blockchain address from the Web2 address that the user has. I want to also quickly note that we could here, in theory, be using other fields. Like if there was email in this JWT token, we could have derived user addresses from their emails. If there was some other field here that uniquely, again, identifies the user, we could use that. So this would, in theory, allow us to create email-based wallets or other identifier-based wallets pretty naturally. A key question is, well, who maintains this salt? As Futini kind of alluded to, the premise for our work is to kind of make it easy for users to onboard to blockchain. So we don't want users to remember the salt and have the burden of doing that. But of course, that is definitely one option. So there's plenty of options in kind of who maintains the salt, but at a high level, the idea is someone kind of needs to remember it. Either the user does it, or we make it easy for the user to do it by doing some tricks on the device. Or there is a salt service which kind of manages the salts for the user on behalf of the user. And there's plenty of variation in how you can build such a salt service, from a simple salt service to an enclave-based one to an MPC-based one, and so on and so forth. zk-login is broadly speaking compatible with any of these options. The server options are more, let's say, comfortable for the user. Lastly, we also need to, we actually do need to prove that this JWT token is somehow well-formed. And again, going back to the previous point I was making, you can't post the JWT directly on a chain because, again, everything is public and you don't want to reveal something as sensitive as this. So what we end up doing is to leverage the power of ZK snarks for us. So we build a ZK snark that allows us to prove that a JWT is valid. In particular, what that means is verifying that the signature verifies with Google or whichever OpenID provider we use their public key, checking that the ephemeral public key is properly inserted, checking that the address derivation is done correctly. Note here that the public key, the Google's public key and the ephemeral public key are both public inputs. So these will then be used by the blockchain validators to make sure that this is sort of the right public key of the OpenID provider. The end-to-end system looks something like this. The user requests a JWT from the OpenID provider. The app front end this could, for example, be an extension or a mobile device gets the JWT. There is a salt and zero-knowledge proof generation, and finally, the transaction submission happens. At the end of the day, the zk-login signature looks something like this. It sort of has two components to it. A zero-knowledge proof, which proves validity of the ephemeral public key, and the corresponding ephemeral private key signed transaction. I want you all to note critically here that this a single zero-knowledge proof could be used to generate multiple transactions. because you can keep the first part same and use the second part. As long as the ephemeral private key is there, you can continue to sign different transactions, which is a key optimization. Last but not the least, we want to finish the proof generation fast. By fast, I mean it should finish in, let's say, 3 or 4 seconds so that the user doesn't experience this. For this reason, we went with Groth 16, also because it has small proofs, which is always nice, especially when you're posting the signature on chain. We want the signature sizes to be very small. Even though we use Groth 16, these proofs are fairly slow to generate on user devices, at least on many user devices. And so expecting users to kind of generate these proofs wasn't enough for us. So here we again we leverage a key trick. Basically, if you go back, there are 2 components to the signature. So even if the first part is delegated to a third-party service to generate the zero-knowledge proof for you, as long as the ephemeral private key is on the user device, the system is safe and secure. So that is what we kind of do. We delegate the proof generation to a third party, but keep the ephemeral private key on the user device. The circuit has about 1 million R1CS constraints. SHA-2 takes the dominant role in the costs. I won't go into the circuit details in the interest of time, but at a high level, we had to implement specialized parsing tricks so that we kind of don't parse the full JWT within the circuit and only selectively parse the relevant parts of it that we need. These are the end-to-end benchmarks of ZK login. A ZK login transaction takes about 3 seconds from start to finish, meaning to create the ephemeral key pair, get a zero-knowledge proof, produce a transaction, and actually submit. These transactions were submitted on the SUI blockchain. So this is sort of the end-to-end time. Again, I want to note that these numbers correspond to only the first transaction of a session. So if the ephemeral private key is remembered, then the user kind of doesn't face this every time they're signing a transaction. A few trade-offs I want to briefly highlight. As I've mentioned, there is a prover service that some providers can set up to run to kind of generate the zero-knowledge proofs. One downside of this option is that the prover service sees the JWT and is therefore able to link the user's Web2 and Web3 identities. Another worry we hear from some users is the fact that you'd be trusting someone like Google or Apple or whoever you use too much. One option people take in those cases is to kind of create a 2 out of 2 between Google and Apple, which is also possible. We can create like a multi-sig between Google and Apple with ZK login. Similarly, the SALT service also can see the link and can link the Web2 and Web3 identities. There are ways to mitigate this, which I can go into if you're interested. So as Swatini said, we've deployed this on SUI since about a year. As she has kind of already shown before, this is how it looks today. One thing I want you all to note here is when we click send here, a real zero-knowledge proof generation is actually happening in the backend. So as you can see, it's not taking too much time, and the system actually works. So in production today, we have many OpenID providers, including Google, Facebook, Twitch, and Apple, and many others are also supported on DevNet. It's been about 1.5 years since we launched this on mainnet. We have generated over 7 million ZK login transactions. As I've noted before, a single zero-knowledge proof can be reused across transactions. So the number of unique zero-knowledge proofs is slightly lower at about 2.5 million. And these were again generated from about 500K ZK login addresses. So this has seen real traction for us. With that, I'll take questions. Thank you.
Yeah. Thank you. We have time for a few questions.
Yeah, so you put the zero-knowledge proof is generated by a separate server. Did you think about using zero-knowledge proofs which have EVMs which could run on the local device like Licero, and you could then compress that into Groth 16 with just doing the verification of that? So that would then remove that need for the server.
Yeah.
The server would only have to just compress the Groth 16 if you
Yeah.
do that offline.
I think at least at the time we were doing this, that wasn't as popular an option. This has become a popular thing to do more recently. One concern with that would be if the end-to-end latencies are still good enough as what we have. If they are, then that would definitely be an option to consider.
Mutu was here. You should have asked him when he was here.
Hi, so I don't understand if you forward the token to the prover service, then the prover service can impersonate the user. So how do you prevent just impersonation from the token?
So the prover service doesn't have the ephemeral private key. So the prover service just sees the JWT, but the JWT just has the ephemeral public key in it, right? So it can't impersonate the user because it doesn't have the ephemeral private key, which is also needed to sign a transaction.
But I can generate my own private public key pair. I can also impersonate it towards other Google services that would accept Google tokens.
So if you create your own ephemeral key pair, you won't be able to get Google JWT signed over it, right? So the user's extension or whatever it is doing the key pair generation, embedding, and getting the signature from Google.
But what about presenting the token to some other service? Yes.
Sorry, I don't think I fully understand your
So
question.
you could forward the token to some other service to pretend you are the user, and I'm wondering what you do against that.
So you can give the token to anyone you want, as long as the ephemeral private key is stored safely on your extension or mobile.
Okay, let's discuss.
So basically, if it helps, in order to sign a transaction, you need to do two actions. One is a zero knowledge proof over the token that you got from Google, let's say. And the second is actually a signature with the ephemeral secret key, the public key of which is embedded in the token that you got from Google.
So I get that.
So you cannot play with a different pair of keys because you need like both pieces.
No, I get that it's secure for your service, but I'm wondering about other services that might accept a token signed by Google for authentication for some other purpose.
So you're saying some other service could use this token? Yeah, indeed, that was one reason we were thinking of instantiating a prover service within an enclave. This is something we are considering doing, but we haven't done yet.
Thanks.
Actually, we are out of time for questions, so maybe we'll take the rest of the questions offline. Let's thank the speakers again. Very cool application of zero knowledge. Okay, so our next speaker is Xiangzi, who actually can't be here. So this is going to be a pre-recorded talk, and he's going to talk about deploying TLS oracles using interactive ZK. So can we play the tape? And then he'll be here to answer questions, so we can still line up and answer questions just as before.
Yeah, hi everyone. My name is Xiangxie from Pharmacy Labs. Yeah, I'm sorry that I cannot give you the presentation in person because of visa issues. So now today, my presentation is about deploying TLS oracles using interactive knowledge proof systems. So I think you may heard a lot about ZK TLS or web proofs or TLS oracles. I think they are all the same thing that we are talking about. So first of all, the background. So what is TLS oracle? What is ZK TLS? So in this case, the client has access to a server that can get the response from the server end. And the motivation is the client want to prove to the third party that this kind of data or encrypted data is actually from the intended server. The thing is that we want to do it without any modifications on the server side. And this is the most difficult part, because as long as we can change server side, the server can just sign everything and verify it. So yeah, this is the most difficult part. And in this case, we are considering the transport layer security TLS 1.2 or 1.3. And for example, the kind me who has a Coinbase account, I want to prove to another party that I have enough ETH actually in Coinbase, so without any help from Coinbase itself. One thing that is interesting is this problem was actually introduced by Dan from the Library about 10 years ago in a Bitcoin forum, that they are thinking about proving fire transfers for P2P exchange of Bitcoin. And after that, a lot of academia papers came out to solve this problem, like Tom Creer, like Jacob, and our paper, Gabardine Proof. So all of these papers are trying to improved efficiency in different trust assumptions, in different mode, and in different scenarios. First, let me briefly introduce the TLS protocol. So basically, TLS protocol has two phases. The first one is a handshake phase. In this handshake phase, the server has a certification, and the server and the client established a shared key using Diffie-Hellman key exchange and using PRF or KDF to expand the shared key to different session keys. And as long as the client and the server have a shared secret key, shared session keys, they can communicate with each other using encrypted, using this different cipher suite. And here we are interested about this AAD cipher suite, or more specifically, AES-GCN. In general, so there are a lot of different ways to solve this problem. Like different people are trying to use TE, and in this talk, I mostly focus on cryptography modes. So in the industry, or what I'm talking about is more about this MPC TLS or proxy TLS. So MPC TLS means that the verifier and the client run a 2PC protocol to simulate a TLS client and talk to the server. In this case, the server actually cannot tell the difference if it's MPC simulated as client or is it just a real client. And in the proxy model, the verifier actually sits between the client and the server, and the verifier forwards the transcripts, TLS transcripts between client and server. So the verifier just watch the ciphertext and record the ciphertext between the client and the server. So let's dig in a little bit of these two protocols. So first of all, in MPC TLS, I think the computation of circuits the verifier client want to compute into PC is more about the key exchange, and here 2PC on the key expansion or key KDA functions, which are a bunch of like shard circuits. The other thing, when they go to the handshake, when they go to the record parts, if the client want to send encrypted data, then the verifier and the client has to run 2PC on AES-GCN, because in this time the client and the verifier client does not have the entire session key, so he has to run this 2PC protocol with the verifier. And at the end of the protocol, especially when the verifier get the ciphertext from the server, the response from the server, the client has to run a zero proof system on the KDF and AES to prove that he know everything, all the secret related to this kind of circuit. But this time, before they run the DKP, the verifier has to send back his key shares to the client, so the client had all the witness. So this is actually used by different papers, like Deco paper. They are using maliciously secure 2PC protocols, which is authenticated Gabor circuit, and then they're using ZK snarks to prove the KDF and the AES. So we improve a lot on that paper from that method, and then we observe that only half gate Gabor circuit is sufficient, or only semi-honest Gabor circuit is sufficient, and including like we're using Quicksilver, which is interactive zero proof system, to prove KDF and the AES. So the result of this Gabor improved system is that it's much efficient than the Deco paper in terms of computation cost and communication cost, and even memory cost. So in the proxy model, in the proxy TLS, so as I said before, the verifier sits between in the client and server, and this time the verifier get all ciphertext. between transfer between client and server using AES GCM or other substitutes. So here, the client only need to prove in the knowledge and show that he knows the secret related to all these ciphertext. And different papers are proving different circuits. So like in our garbage and proof protocol, we approve the KDF and AES with Quicksilver, which is very, very efficient. And the other paper, like they're proving AES circuits with SNOX, or proving KDF and AES, or char-20 with SNOX. So it somehow bring more computation cost and memory cost. So here are some comparisons of two modes. So in terms of trust assumptions and efficiency, for both MPC TLS and the proxy TLS, we have to trust the TLS server. Otherwise, you cannot do anything. Yeah. And the other thing that there should be no collusion between client and verifier. Otherwise, the verifier can cite anything, and the client provides. And one more trust assumption of this proxy TLS protocol is that the verifier has to make sure that he is actually connecting to the TLS server, the correct TLS server. Otherwise, a malicious client can then sit between the verifier and the test server to conduct a man-in-the-middle attack. In terms of efficiency, it's apparently that the MPC TLS has to run a two-piece protocol for KDF and AES, which probably is the main bottleneck, efficiency bottleneck in a lot of products and protocols. And our benchmark will show that our product will show that it's actually the bottleneck when the user want to use it. So the proxy TLS protocol can be much more efficient than the MPC protocol. So there's always a trade-off between this user experience and the trust assumption. So why, in this case, interactive zero-knowledge proof system is the best choice? So first of all, the protocol does not need to be fully online interactive. So TLS protocol itself is interactive, and the purpose is that the client proves will verify that the data is actually from the server. So interactive zero-knowledge proof system is totally suitable in this case. The second reason is that in both modes, the client has to prove KDF AES, which are all represented by Boolean circuits, and all these circuits are not zk-SNARK friendly. And in this case, actually the witness or the private data is actually owned by the client. So all these kind of client may deployed in different like resource limited environments like browsers, mobile devices. And the last one is that current zk-SNARKs have high proving time and memory use. And when the clients are deployed in a resource limited environment, then this may pose a major challenge in terms of like user experience. The client cannot wait for a long proving time, and it's always running out of memory, which is bad user experience. So yeah, we are using Quicksilver. Quicksilver is published back to 2021. It's an interactive zero-knowledge proof system, and it can prove Boolean circuits and arithmetic circuits. Especially, it's super efficient in terms of memory, in terms of proving time, and in terms of communication cost. So some numbers say that you can just in a very normal machine, you can prove 1 trillion AND gates within $2, which I think is amazing for for products. It's basically the cost is basically nothing. It's negligible for us to deploy this kind of system into our product, especially for like browsers and the mobiles. And in our global proof system, we actually conduct a series of global scale experiments. So we deploy worldwide experiments in like 18 areas in the world, and we test when the users want to prove their data from Coinbase and Twitter. So all the numbers show that is quite efficient, and there's no like timeout problems issues when they connected to the data server. And we also prove that prove is proxy TLS using our like quicksale-based proxy TLS to prove very large content from large language model. For example, we can prove a 200 KB image that is actually generated from ChatGPT within 2 minutes. And this is experimented in the browser extension, not native machine, not mobile, not PC. So it's quite efficient. And when we deploy it to like mobiles or PCs, it should be much more faster. And this is the first one. I think this is the first scheme that can prove such a large amount of content from TLS server. Also, we built a zkTLS benchmark framework, which is already open source. And in this framework, we trying to benchmark all existing open source zkTLS implementations across different platforms and network conditions. And after we finished the benchmark, we found that our global proof system is up to 10 times faster than other MPC TLS protocols. And also our quicksale-based proxy TLS is up to 30 times or 145 times faster than alternatives. And the test library, which is maintained by PSC, Israel Foundation, and a lot of zkTLS startup are using them, is now transitioning to Quicksilver, and I am one of the co-contributors to implement this Quicksilver library. So we actually have a lot of products to support TLS oracles or zkTLS. So first of all, before that, we also build this tool, what we call is a developer hub, is to enable the developer to find any data from any website they want to prove using our zkTLS SDKs. So it's very easy for you guys, of developers, to find, okay, I want to prove my like account. I want to prove that my social account. So it's very easy for you to get the web API and feed them to the SDKs. Of course, we have a bunch of SDKs, different SDKs. We have web SDKs to enable the developers to build these web proofs, web applications. And also we have mobile SDKs that if you have like apps in mobile, iOS or Android, you can use our SDKs to build that. Also, we have backend SDKs for like, you can use it to do like a verifiable agent, and this can be run in a server or in the backend in a PC. Yeah, we deployed our product for a few times. So we already have like more than 360K successful attestations. The users just make it as prove their data. And 160K of these attestations are submitted to blockchain systems, like different blockchain systems, Ethereum, Linear, BNB, Scroll, Monad. And there is kind of more than 540K downloads of our Chrome extension, and over 4K developer hub users to use it. And when we deploy our product, we do have a few challenges. So in order to bring better user experience for the users, our verifier or our server has to be globally distributed. The reason is that we want to enable the verifier to be positioned close to the client, because at this time, latency and the bandwidth are the main focus, or the main bottleneck to bring a better user experience. And then the other challenge is that, as I said before, there is trust assumption is about the collusion between client and verifier. So to mitigate this risk, and the best practice to trade off the trust assumption and the user experience is that we deploy the verifier within a TE. So it may bring some cost, but the cost is kind of negligible for us. But it also provides better user experience and to mitigate this kind of risk, and to make it much more, to reduce the risk, make it much more secure. Yeah, that's basically my talk. And thank you for your listening. And if you want to reach out to me, you can just scan this QR code and we can talk, offline. Thank you so much.
Great, thank you. So is the speaker online to answer questions? Are you available to answer questions?
Yeah, hello, can you hear me? So yeah, I'm online and be able to answer questions.
Great. Are there any questions on TLS oracles? Can you say which one was actually deployed when you pushed these proofs on chain? Was it the proxy method or the MPC method?
Actually, both of them are used, but our default method is using the proxy method because it's more, it's much more fast. But we still have other options, like people or developers are using this MPC model. But yeah, it depends on the applications.
Mm-hmm. Yeah, makes sense. Well, all right. If there are no other questions, then let's thank the speaker again. Thank you very much.
Thank you so much.
And we'll move on to our next speaker. So our next speaker is going to talk about exploiting vulnerabilities in ZK in Ethereum. And Oana, the floor is yours.
Thank you very much. Welcome to my talk. Today, I would like to discuss a couple of vulnerabilities we have encountered together with my fellow auditors from Open Zeppelin, and they relate to real-world implementations of ZK-based cryptographic schemes, which are found in the Ethereum ecosystem. Right. Okay, so with the advent of blockchain, we have seen a surge in research and implementation related to both cryptography in general, but also specifically to ZK schemes in particular. Also, there was an increased interest in making sure that the related security proofs, both on a theoretical level, but also practically in implementation, related to those schemes that are deployed. Along the years, we have seen a wave of security vulnerabilities, some of which were more on the theoretical side. For example, notable ones are the Zcash counterfeiting vulnerability. But also recently, we have seen a quite successful and important attack against the security of Fiat Shamir when applied, for example, to the GKR protocol and certain circuits that implement hash functions. Besides these theoretical attacks, there have been some concrete practical vulnerabilities, and I'm thinking here about the attacks against the Fiat Shamir transform encountered in certain implementations, as well as the recent attack against a Nova folding scheme implementation. So I was mentioning Fiat Shamir transform a couple of times, both relating to theory and practice. I will go into more detail about that, but first let's see what is Fiat Shamir and where it is used. Just a brief reminder. By default, computing proofs or arguments involves an interactive system between a prover and a verifier. Now, if we want to obtain a non-interactive system, what is being used is a quite simple and elegant solution, which is the Fiat-Shamir transform. This is usually applied when the verifier is public coin, and this means that the verifier only needs to compute random challenges. And in that case, what happens practically is that the non-interactive prover does the same computation as the interactive one, but on top of that, it computes its own challenges as the hash of the complete transcript up to that point. And by a complete transcript up to that point, I understand the fact that both the public keys, the public parameters, and the entire definition of the problem is included, as well as the public inputs. And of course, the same challenges, according to the same rule, are computed by the non-interactive verifier. There is an entire history of attacks on the Fiat-Shamir transform, both theoretical and in the real world. And just to name a few such related attacks, there have been contrived attacks on cryptographic primitive secure in the random oracle model, which were proven insecure as soon as the instantiation of the random oracle model was taking place by any hash function. Again, I'm mentioning here the recent attack on the Fiat-Shamir transform applied to the GKR protocol. And finally, there are some practical vulnerabilities we have seen along the years, and they relate to adaptive soundness attacks against Fiat transform implementations when, for example, the public input is not included in the transcript when computing challenges. However, what has not been considered so far was the following special case. What happens if a deviating verifier omits from the transcript certain components which are different from the public input? This is what we are going to concern ourselves for the remainder of the talk. And we are in particular interested whether practical attacks are possible. And we are going to show a couple of positive answers. So first, let's remind ourselves the setting in which we are working. And then we are going to see a general framework in which this attack works, plus a couple of concrete instantiations, which we are going to call the last challenge attack and the Fiat-Shamir array inputs not transcribed, for short LCA and feigned. And if there is time, I'm going to get into the details of an attack on something else, which is statistical zero knowledge. And to start with, the setting is the following. We would like to scale Ethereum. Hence, we assume a layer 2 ZK rollup, which executes transactions off-chain. Now, this rollup assumes a snark, and this implies a prover, which provides a succinct proof onto layer 1. This succinct proof testifies, or should testify, that certain transactions took place and they obey certain rules. There is an embedded corresponding snark onto layer 1, which should verify the correctness of the proof sent by the prover. And if that takes place, then the corresponding state of layer 2 onto layer 1, as well as the state of the layer 1, gets updated accordingly. And with all this context, I would like to introduce a new type of attack on the soundness of the Fiat-Shamir transform for certain implementations. We are going to assume a deviating verifier, which omits hashing from the transcript other components than the public input. And we are going to show how a malicious prover can choose some public input, hence the attack is an adaptive soundness attack. This attack works in 6 steps. In the first step, the prover simply simulates the underlying commitment scheme and chooses all corresponding inputs. In the second step, the prover chooses freely all the components of the proof, apart for those components that were actually ignored by the deviating verifier. We call this the degrees of freedom of the verifier, or simply the degrees of freedom. On the third step, using the public input chosen so far and all the other values, the malicious prover follows the steps usually computed by the regular prover and instantiates a system of equations where the only unknowns are the degrees of freedom of the verifier. Now, most of the times, the malicious prover is able to actually solve this system of equations. And if that is feasible and it happens, it fills in with the corresponding solution the remaining empty slots in the proof. And guess what? With probability 1, if we reach the final 6th step, the deviating verifier will accept this fake proof as valid with probability 1. So we are now going to look at 2 concrete instantiations. The first one relates to a concrete attack, which we call the last challenge attack. The context is that of pairing-based snarks. And in order to make the attack as concrete as possible, I'm going to very briefly aim to review the snark in which we found this attack. This is a KZG-based plonk, and I have simplified it here to put it on one table. This table contains rounds, and in each round we see the challenges which have been computed so far, the transcript computed during that round, and the challenges which are computed at the end of the round. We see, for example, in the first round that the transcript should include the public parameters, the public input, and everything that has been derived in that round. This is how the rounds in Plonk look like, and this is the proof size and shape in Plonk. Now, correspondingly, there is a KZG-based Plonk verifier, and correspondingly, this verifier computes the FS challenges and does a few verifications, among which the most important is the final pairing check. Note that in the final pairing check, the last challenge U is very important and present. And now, with this verification in mind, let's ask ourselves the following question. What if a deviating Plonk verifier omits part of the full transcript? In particular, when computing U, it omits to include TR5, which is the last part of the transcript. Is soundness still preserved? We are going to assume such a deviation, and we are going to show then an attack is possible. And the attack has the following 6 steps. First, a malicious prover is able to simulate honestly a KZG commitment scheme, which is the underlying scheme for a Plonk snark. And it's going to simulate this honestly, and in the end, it's going to keep the computed values A and B for later use. Now, the same malicious prover is going to choose freely all public inputs and proof components, except for the 2 proof components that were actually ignored by the deviating verifier. So those were the degrees of freedom of the verifier. Those are not chosen for the moment by the malicious Plonk prover. And in the next step, following the honest computation of a Plonk verifier, the Plonk prover computes does some intermediary computation necessary for the following step, which is the most involved, and in which we actually have a system of two linear equations with two unknowns. These unknowns are in fact the missing elements of the proof we would like to construct. Everything else in this system is actually fully determined by now, and it's based on everything we have determined in steps 1, 2, and 3. And all these equations are derived from actually the important pairing check that the verifier has to perform. So if the prover has reached this step, with very high probability, he is able to solve the system, obtain a solution, and include the solution into the remaining empty slots for the proof. And guess what? With probability 1, the deviating verifier accepts the false proof. Hence, the disastrous consequences can happen. Similarly, there is a very related attack, which we call the Fiat-Shamir array inputs not transcribed, meaning that certain input is not, a certain array is not included in the transcript. I will go over it at a high level. I will just say that this is related to a variant of Plonk, namely Flonk, which looks quite similar. You just observe here that the size of Flonk is slightly larger than Plonk. And we also observe here that, for example, if a deviating verifier omits checking the length of the evaluation array, which is TR3, then challenges alpha and y are affected. And moreover, all these evaluations in TR3, we observe they are also included in the Flonk proof. So very similarly, actually, to the attack observed before, in this particular case, if one omits from the transcript the set of evaluations, then an attack is possible, and the steps are quite similar to what we have seen before, taking into account that the new degrees of freedom are these inputs, these arrays. And quite similarly, a malicious prover is supposed to solve a system of equations which is well defined and in which the only unknowns are exactly these degrees of freedom of the verifier. With some creativity, actually it is possible to quite easily solve such a system with probability 1. Hence, the prover can fill in the missing spots of the proof and succeed in his attack. And I would also like to discuss a attack on statistical zero knowledge. This is orthogonal to soundness, but this is also quite interesting. So very briefly, zero knowledge protects a honest prover from a curious malicious verifier. When we talk about zero knowledge in the context of polynomial commitment schemes, then we have polynomials as witnesses, and we should blind those polynomials with random polynomials of degree at least the number of opening points for the commitment, the polynomial commitment scheme. This ensures statistical soundness, and this holds when there is only one witness. What happens when we have multiple such witnesses? Well, we still have to blind every witness polynomial, but we have to do more. And on this slide, I'm simply showing the blinding that should happen for a quotient, so-called quotient polynomial that is obtained in round 3 of Plonk. If this blinding is not followed, then an attack, a theoretical attack exists, and this has been published quite recently. But what is even more interesting is the fact that we have seen such missing blindings in a concrete implementation used in the context of Ethereum. So to conclude, we have discussed and I have presented 2 new attacks against the soundness of the Fiat-Shamir transformation in practice. And I have also highlighted a subtle attack on the zero knowledge encountered in a snark implementation. Overall, please mind your blindings and your Fiat-Shamirs.
Great, thank you very much. You just say that the soundness vulnerabilities, are those in deployed systems or are those more hypothetical?
We found the attacks obviously before the systems were deployed, so not in. Hopefully, there are no
About
more.
to be deployed, and then you found the issues and you told them about it and they fixed it.
Yes, part of an audit. Yes.
Okay, excellent, very good work. Thank you. I think we're actually out of time for questions, so thank you very much, and we'll move on to the next talk. So let's thank the speaker again. Okay, and our last talk of the conference, exciting talk, is going to be about analyzing key derivation functions. Theo and Sebastian are going to give the talk. The floor is yours.
Hi, thank you very much for the introduction. My name is Sebastian, and I'm here with Matteo today to talk to you about a very fundamental primitive, the key derivation function. But not any key derivation function, but key derivation functions that take as input multiple secrets to combine them into one single output secrets. And we will discuss the lessons we've learned when analyzing real-world constructions of this primitive. But first, let's back off a bit and talk about what the key derivation function is. On the left, you see a very basic Diffie-Hellman key agreement protocol. You have some user which sends a shared G to the X to the server, which responds with a shared G to the Y, which they can then use to get some element that looks uniform within the group. However, it only looks uniform within the group and is not a uniform bit string. Also, protocols like to add some additional information into the derived key, like context binding to increase security. This is where key derivation functions come in. Over time, key derivation functions have converged on the following inputs. So they take a secret, the G to the XY that we just discussed, some label which handles additional information, and a length output which ensures that the output key has the correct length for the cryptographic application that wants to use the key later. Also, from extractor theory, there is a salt value that is input in the KDF, which job is to smoothen the entropy of the final key to ensure that it is uniform. However, when we looked at what constructions that are deployed actually do, we realized that basically none of them use the salt value as it is intended, but just put some fixed string in as the salt input. As a consequence, we've come up with a model to analyze these key derivation functions without relying on the salt value. So as you all know, with the quantum threat advancing, the Diffie-Hellman key agreement that I've just shown you really no longer does it. So in practice, you would probably have a protocol that is more like this, where in addition to the Diffie-Hellman key shares, you now also have some CAM key agreement. So now client and server have a G to the XY and also some shared secret lowercase k. Now the KDF already has all its inputs satisfied, and there's not really any place to put this additional key and this additional context that might come up as part of the CAM key exchange. So in practice, constructions have had to deal with this and have come up with solutions. I've brought with me here 2 examples for multi-input key derivation functions that are deployed in practice. And they kind of do well in exemplifying the 2 design paradigma that we have observed. The first is the MLS PSK KDF, which is used in MLS to combine the pre-shared secrets. It uses an iterative construction and loops over the input secrets, calling HKDF multiple times on each secret. In contrast, there's CAT-KDF, and it was proposed by Etsy, which does not iterate over the secrets, but concatenates all the secrets and then using them as one big input to HKDF. On the topic of interfaces, we can also observe that they deal differently with the label input. MLS does not take a user-defined label input, but uses the empty string and fixes this to the string MLS-derived PSK, while Etsy CAT-KDF lets the user choose an arbitrary label. So this leads me to this discussion on labels and contexts. When we first started analyzing key derivation functions, and especially key derivation functions that combine multiple input secrets, we were quite confused by the notion of labels and contexts, and also the notion of an info field, which sometimes appears, which also somehow gets input into the KDF. So we have come up with the following logic. We say multi-input key derivation function should have one single label that is somewhat associated with the final key. For this purpose, we can call it the real-world cryptography encryption key, or MAC key, or whatever. And in contrast to this one single label, we have multiple contexts. And to be precise, we have exactly one context per input key. So for our example, we would have two contexts, one for the Diffie-Hellman part and one for the CAM part, where the context consists of the transcript that can be observed, but also like public parameters, the CAM algorithm, or any other metadata that should be included in the protocol. And now to highlight why this is important, if you look at the Etsy KDF, again, as I've shown you before, you see that it does take this label input and then uses it as an input for HKDF. However, HKDF doesn't really expect a label input, but more of a context input. So the label is used as the salt input to HKDF, which can lead to a problem. If we look at how HKDF works, it first performs an extraction step with the salt, which is now the label. And if we look at how this extraction step is defined, it uses HMAC, which is a key primitive where the key is the salt, which again is the label that is provided to the Etsy KDF. And actually the first step of HMAC hash is to append zeros to the end of the key, which is the salt, which is the label, until the desired length is reached. As such, it is very easy or trivial to generate labels that yield to the same output of HMAC hash. So you can have different labels that, when input into the multi-input KDF, result in the same key. Now this can relatively easily be fixed by just fixing the label length, but we've also found constructions where the issues are bigger. Now I hand over to Matteo to tell you about his analysis of MFKDF.
Yeah, so as you've probably seen, multi-input KDFs are hard to get right. And even if no boxes were harmed in the production of these slides, I will try to talk to you about another attack that we discovered on this MFKDF construction proposed at Usenix 23 by Nair and Song. What they want here is to derive one key given multiple inputs. So we're clearly in the multi-input KDF settings. And so let's abstract away a lot of the details of MFKDF. Just look at this schematic diagram. We have several inputs, each with like different entropies. And so for instance, in this case, we have a password and some HOTP, TOTP factors with 40, 30, and 30 bits of entropy. What we would want to have at the end is a key with at least 100 bits of entropy. MFKDF does this, but not just this, also more. They also provide a threshold variant. So you can set up MFKDF with a 3 out of 4 threshold, and then you should still get at least the entropy that the set of the minimal set of 3 factors should provide you. So in this case, still 100 bits. How does MFKDF do this? Well, they start by sampling a random final key, and then they secret share it in n shares. So in this case, now I switch to 2 out of 3 shares just to make the things fit in a slide nicely. So now we have 3 shares, and if you haven't heard about Shamir secret sharing before, what this gives you is that you can pick any two of these shares and rederive the key. Okay, so any combination of the shares will give you back the key. But how do we factor this Shamir secret sharing implementation into the bigger picture of MFKDF? Well, we take our factors, we derive a key from each factor, and now we plug in the bottom part, so we take our final key, secret share it, and then we can encrypt each of those shares with a key from each factor. Okay, and now we have encrypted shares, we can put them in a public state and upload this public state somewhere in the cloud, so that when we want to rederive the key, all that we need to do is input our original factors, derive key from these factors, retrieve the state from the cloud, decrypt the shares, and rederive our key. Okay, so pretty neat, right? Are you convinced by this? Well, turns out that, I mean, probably I wouldn't be asking this question if everything went right. Well, let's look at decryption. So we would expect to get 60 bits of entropy out of this. But what if we took a guess for the password, and then we did trial decryption of a share? Now, the output would either be something that looks like a share, Shamir secret sharing share, which is, by the way, not uniform in most cases, or something that looks like uniform randomness, or even a bottom if we were using authenticated encryption. And so what this means is that we can brute force factors separately. So for instance, we could brute force all the 2 to the 40 possible passwords and all 2 to the 30 possible HOTPs. And this would give us an entropy of 2 to the 40 plus 2 to the 30, which is much smaller than 2 to the 60. Okay, so clearly something here went wrong, because like we get a security level much lower than what we would have expected. Now, I must tell you that this bug is a bug in the specification of MFKDF. There are actual reference implementation as other bugs that cancel this one out. So we don't have a practical proof of concept exploit. Like my paper with Matilda Backendal and Miro Haller actually finds a lot of other problems with this idea of deriving keys from authentication factors. So we have a lot of attacks in our papers. If you find it interesting, check it out. To the defense of the MFKDF author, though, we must say that this primitive that they were trying to implement of having a threshold NKDF, so multi-input KDF, is actually something that is not well defined in the literature. They were trying to build something new and something for which we don't have a model yet. And therefore, they didn't even have a security notion to target. And so what is a secure NKDF? Well, to answer this question, I will give the floor back to Sebastian.
Thank you very much, Matteo. Yes, indeed, we ask ourselves, how does a secure multi-input key derivation function look like? You see here the syntax that I've discussed before. So we have multiple input secrets, up to n in fact, and each input secret has its associated context. Then there is a label value and a length value. For simplicity, I will, on the following slides, only talk about KDFs that take 2 inputs, but everything I say basically extends to the n input case. So in our security game, we basically want that with these inputs, we get an output that looks random. And now we want that it looks random, not only if all the input secrets are secret, but we allow an adversary to compromise actually some input secrets. In this example, the second input secret, the associated context, the label, and the length are all adversarially controlled. So there's only one good input secret left. And for this, we want that the output of the KDF still looks random. Actually, KDFs are deployed in a number of places. There's stuff like extendable and non-extendable output functions. There's keys that may only be used once. So it's a bit complicated, and we have different predicates that you can use to deal with this in a formal analysis. But there's also two major settings that I want to highlight here, in which KDFs can be analyzed. So the first one is the hybrid setting, as I've discussed in the very beginning, where you have some established primitive with a proven implementation and something new that is used in a hybrid manner. Now, with such a system, you would expect that either like the quantum computer arrives and all your Diffie-Hellman secrets are broken, or that there's some issue in the implementation or the math of the newer schemes, and all the new stuff gets broken. But importantly, it's always the same input that is either good or bad, and there's no mixing in between. This is what we call the hybrid setting. There's also the more general setting, where you do not fix a single input to be either good or bad, but the adversary can adaptively choose which input secret he wants to learn or even control himself. Note that for security, obviously, we always need that at least one of the input secrets remains unknown to the adversary. And in these two different security settings, you get different security bounds. So we took this model and actually applied it to a few constructions that we have found in the wild. One is the pre-shared key combiner used by MLS that I've shown before. And we can actually show that the MLS combiner is a good combiner for pre-shared keys in the way that it is used at the moment. We've also looked at CAT-KDF as it is proposed by ETSI and have found the issue with the label that I've shown earlier. However, it is important to point out that CAT-KDF was never really meant to be a general purpose multi-input key derivation function, but it's more tailor-made for the case of a hybrid key agreement. However, other agencies like the BSI reference these standards, and the interface kind of gives you a more general construction than what is advertised. And with the restricted label set, you can actually use the ETSI CAT-KDF outside the scope that they advertise and have it as a secure multi-input key derivation function. Lastly, we looked at Signal and the way they use a KDF in their X3H key agreement, and also found that this is a good use of a multi-input key derivation function. Throughout our analysis, we have seen that the way these multi-input key derivation functions are built follows some kind of a generic blueprint. Analogous to the extract and expand paradigm that you have in HKDF, for multi-input key derivation functions, you have more of a combine and then expand paradigm. And importantly, the combine step only takes the secrets and associated contexts, while the expand step takes the label and the length on some pseudo-random key that is output by the combine step to give you your final key. And this modularity actually allows you to have a look at both pieces individually. And for the combine step, you actually need a simpler primitive, which we term a combiner in KDF, where you do not need to worry about either labels or the output length. And for the expand step, you can just use a PRF with variable output lengths. This primitive is readily available. You can, for example, use HKDF expand or shake for this. So this leads me to my lessons learned. To recap, we have seen that this actually has pitfalls if you try to design a multi-input key derivation functions. Now you can use formal analysis to actually validate your constructions and gain trust into the constructions that you have deployed. Using this model, we've been able to give positive results on Signal and MLS. This talk was based on two papers. The MFKDF part was published at Usenix last year, was called Multiple Factors Knocked Down Flat. Check it out if you want to learn more about MFKDF. If you want to learn more about key derivation functions with multiple inputs, have a look at Encrypted this year, where our paper will appear. It's not yet on ePrint, but will be very soon. This concludes my talk, and we're now very happy to take any questions.
Great, thank you.
Thanks for the talk. One question about CAT-KDF. So if I'm not mistaken, it runs the extract function on the concatenation of secrets.
Yes.
And as far as I'm aware, HKDF wasn't proven secure in that sort of hybrid model where you have a concatenation of secrets, one which can be sort of maliciously chosen. Do you have analysis as well that sort of validates that use of HKDF extract?
So we've analyzed etc cat KDF and shown that you can have malicious inputs. Let's discuss HKDF offline.
Thanks.
Great. Any other questions? All right. In that case, let's thank the speakers. This concludes the session and also concludes RWC. So actually, one more round of applause for all the speakers of RWC. With that, I'll hand it over to Mariana to conclude for concluding remarks for RWC. Mariana, all yours.
Okay, so it's time to wrap up the conference. I sincerely hope that you have enjoyed the content and the city and the food. Okay, so wait, where are my slides? Where is the clicker? Did somebody take the clicker? All right, what is the final tally? We had 664 attendees, registered attendees, and 205 of them were students from 47 countries and 228 new ICR members. I think this is a witness, the fact that our community is growing with new members is a witness of the importance of the work that is done here. And I hope this kind of trend continues. Of course, we have to thank for the wonderful program, our PC and our program chairs, Martin and Nick, and I will give the floor to both of them to have some remarks.
We each enter from different sides of the stage. Okay. I have a bunch of people to thank here, so let's hold the applause to the end. First, we'd like to thank the steering committee for trusting us with putting together this program. This was a great honor, and we're really happy to have been able to do this. We'd like to thank all the submitters, everybody who submitted a talk this year. We would have loved to have included everybody, but it's really great that there's so much interest in this conference. We'd also, well, specifically like to thank the speakers. We thank the speakers before, but also the invited speakers for sharing their own unique insights to this conference. And sort of the biggest round of applause so far for the program committee. So the folks who were on this program committee did so much work, and we're so grateful to all the time that they volunteered. So thank you to the program committee. And sort of our last big thank you, and this is not just from us, but this is from everybody, is to Mariana, our general chair, who's done an amazing job pulling this all together. We couldn't have done it without her. So thank you, Mariana.
Of course, this organization would have been impossible with a lot of other people. So I just want to call out some of them. I want to thank my partners from the Insight Institute, and especially Konstantin, who has been running the ground operation for the last 1 year. So without him, I would have been lost. So I also want to thank the staff of the new event management company that kind of coordinated so many things going on. Of course, our audio and video technical support staff who made our presentation smooth and nice. The catering staff that kept us fed, and the support team from this venue, which I think offered some nice space for us all to interact. Just a round of applause for all of them. Of course, this conference is supported by a number of sponsors that we are very grateful to. And I hope that if you're considering being a sponsor, you are now convinced that you will have your money will be put to a very good use. And please contact Peter, who is the sponsorship chair, or any of the steering committee members, and we will be happy to put your money to great use. Like, for example, the 100 student stipends that we gave away to students from 47 institutions. So thanks to all of our sponsors. So now, if you are eager to continue your attendance in IACR conferences, what's following is Eurocrypt, which is happening in May in Spain, and registration is open. Then we have PKC in Norway, also registration open. And then we continue with crypto in Santa Barbara in August. And of course, the question, what's up for RWC next year's? So I'll first invite Boyan to tell you about 2026.
So thanks for having me here. And I'm here to welcome everybody to the Taipei Marriott next March for Real World Crypto Symposium 2026. Taipei is a very friendly city, and it's known for many things. The 101, good food, like the Palace Museum, many nice things that you should come and experience. I hope that you will enjoy RWC 2026 the same way that you enjoy 2025. Thank you.
And then Matt will tell us about 2027.
Hi, I'm Matt Campagna, and we'll be, went the wrong way. There's only one arrow and I pressed it. I'm delighted to be hosting Real World Crypto 2027 in Seattle, and a little bit frightened seeing all the hard work that you've done. It'll be in downtown Seattle at Amazon's meeting center. We've tentatively locked the dates for the 5th through the 7th of April. I'll be running the general chair and hope to have a smooth conference. So hope to see you there.
All right, so I think that's the last slide. I wish all of you good trips back home. And if you're staying around in Sofia, enjoy the city. Thanks, everyone.